Welcome to the 2024 NASA STEM Enhancement in Earth and Space Science High School Internship Science Symposium. SEAS is a collaboration between NASA and the University of Texas at Austin's Center for Space Research. Former SEAS interns have gone on to major in STEM in college, interned at NASA centers and space contractors, and have been hired by NASA working on missions such as Cassini, Europa, and even launches at Kennedy Space Center. In 2024, we received over 3,000 applications. 1,861 of those were completed, and we selected 108 11th grade students for the on-site program and 125 virtual students as participants who were assigned to 23 different Earth and space science projects. Research was conducted in Earth and space science, environmental studies, climate research, mission design, and technology. To say these students are amazing is an understatement. Each student conducted 60 to 90 hours of research in Earth and space science modules, Python coding, and project-specific work prior to starting their project. Interns heard from 10 NASA subject matter experts that highlighted NASA missions, opportunities, and careers during the course of this internship as part of the SEAS Speaker Series. You are in for a treat as you hear from these amazing young people, our scientists and engineers of the future. On behalf of Selena Miller, Laura Tomlin, Angelica Cruzinga, and myself, Margaret Baggio, the program coordinators of SEAS, welcome to NASA SEAS 2024. Today, we have 20 teams and individual project video presentations. We will divide today's sessions into 3 groups with 2 20-minute breaks. Project video presentations will either be 5, 10, or 20 minutes in length, followed by a 5-minute Q&A. Please post your questions on the Slido app or the website and use the code SEAS 2024. We will divide the day's presentations into 3 sessions. This is session 1, session 2, and session 3. We will have presentations by teams followed by the 5-minute Q&A. We will invite each team presenting to turn on their cameras and their mics to answer the questions posed by those listening. During the 20-minute break, we invite you to watch the video highlights of the student intern produced products as part of the Earth and Space Science and the Python coding projects. Our first presentation is from the astronaut photography team, Observing Earth from Space. Their mentor for the team is Rosina Miller, a Jacobs contractor working at NASA's Johnson Space Center in the Astromaterials Research and Exploration, ARES, division as a research scientist in the Science Engagement Office. The project assistant for the astronaut photography group was Flor Gomez. Please join me in welcoming the astronaut photography team with their project, Hydrosphere and Change Over Time.
Hello, thank you so much for your time today. We are NASA SEAS interns and we are part of the astronaut photography group. Today, we are presenting our research on the hydrosphere and change over time. I'm Clarissa Contreras from Brownsville, Texas.
I'm Kirby Brandon. I'm from Dripping Springs, Texas.
I'm Savannah Banky, and I'm from Brownsville, Texas.
I'm Quinn Hughes. I'm from Minnetonka, Minnesota.
I'm Amelia Jones. I'm from Brooklyn, New York.
I'm Jackson Morris from Braun, Texas.
I'm Aparajita Shimpi. I'm from Jersey City, New Jersey.
I'm Brian Villanova, and I'm from Brownsville, Texas.
For this project, we were tasked to learn more about astronaut photography and how it can be used to observe topographical change over time. We each chose 2 unique locations related to the hydrosphere where change over time was observed. For each location, an article describing the observed changes and possible impacts was written. These articles will then combine into a single research project which we are presenting today.
Our goals for this project were to learn more about the changing hydrosphere and how researchers and civilians can use astronaut photography in various ways.
In our approach to this presentation, we used a variety of online public resources given to us by our mentor, Ms. Rosina Miller. Resources included the Gateway to Astronaut Photography of Earth sites that we used throughout our time at SEAS.
For today's presentation, we'll start off with some background information, then we'll dive into change over time, and finish off with conclusions and reflections. First, let's begin with some background information and cover some topics we will be discussing throughout the presentation.
What is astronaut photography? Astronaut photography is photography taken by astronauts. The majority of photos are taken from the International Space Station, also known as the ISS. While on missions, ISS astronauts are asked to take photos of different parts of the Earth, such as lakes, cities, oceans, weather events, and even natural disasters.
What is the hydrosphere? The hydrosphere is the total amount of mass of water on the Earth. This includes oceans, seas, lakes, rivers, groundwater, ice, and snow, and it can be in the form of liquid, vapor, or solid. A healthy hydrosphere is essential for life on Earth, and monitoring it is crucial to climate change research.
What is change over time? Throughout the presentation, we are looking at changes over time, which are changes that can be seen in the Earth's topography, climate, landforms, and any other observable factors. These changes can impact humans, animals, or the environment. Next, we will begin to present the changes over time we have observed in our research.
One major application for astronaut photography is modeling urbanization. In the images to the left, depicting Corpus Christi in 2002 on the top and 2019 on the bottom, one can observe the city's expansion over time. Now, as the population grows, cities must make room. Astronaut photography can be used to model the city expansion. Using astronaut photography, city planners can create safe urbanization through prominent waste management and planned growth. With the expansion of the human population, local agricultural industries are forced to expand and work overtime. The quick expansion of these agricultural industries leads to poor practices like increased use of fertilizers and pesticides. Many local ecosystems, including freshwater and saltwater regions, are impacted as human habitats expand. The expansion leads to habitat destruction and forces communities of animals to disperse. With this hasty growth, many cities don't have adequate waste management, increasing the amount of waste and pollution dumped into freshwater and ocean ecosystems.
Observing the cryosphere, which is all of Earth's snow and ice and a term under the umbrella of the hydrosphere, can tell us a lot about the extent to which climate change impacts our planet. The direct ramifications of global warming decrease glacial ice and snow coverage, specifically at the poles, northern hemisphere, and peaks of mountains at higher altitudes. I focused on two locations to contrast snow coverage over the last 2 decades, Mount Fuji and Kilimanjaro. Mount Kilimanjaro is a volcanic massive, a geologically distinct mass of rock, forming the peak of a mountain range, located in northeastern Tanzania, near the Kenya border. Astronaut photography from the ISS visualizes snow coverage differences between 2008 and 2021, both taken during the summer. There are visible distinctions of more coverage in 2008, even after considering climate contrasts. Mount Fuji, the highest mountain in Japan, is located near the Pacific Ocean in Yamanashi and Shizuoka. Mount Fuji is notable for its iconic snowcap. However, in recent years, snow accumulation at the top of the volcano has been dwindling or is absent around the winter season. The images taken on the ISS show a progressive decrease in the snow coverage of Mount Fuji, Japan in January 2001, November 2013, and February 2021. There was a visible change in the snowfall cover that blanketed the entire volcano and surrounding area in 2001 to just the peak and radius around it in 2013, and finally, an even smaller coverage of the peak in 2021.
Sea level rise has been a consistent topic in our lives. However, this is not only a problem for future generations. It will have a measurable impact in the present day, with coastlines expected to rise 10 to 12 inches in the next 30 years. Over 40% of U.S. citizens live near the coast and may be observing slight changes over time. One city that illustrates the change over time caused by sea level rise is Galveston, Texas. Galveston is located on a barrier island southeast of Houston and is part of a chain of islands that go all the way down to Mexico. Both photos were taken around the same time of year and time of day, but 34 years apart. The photo on the left shows a clear and distinct shoreline, while the photo on the right shows a shoreline that has become indistinct due to rising sea levels. This change has happened in only 34 years, and if sea levels continue to rise at this rate, it will have devastating effects. By 2050, it is predicted that many parts of Galveston will be fully submerged underwater at least once a year. This will cause lots of economic stress to fix and adapt to being submerged. But not only this, tourism, one of Galveston's main sources of revenue, will be affected due to decreased beach size. People will no longer have beaches to go to, cruises will no longer be able to dock, and an increase of more powerful storms will dissuade people from visiting. Hurricanes like Ike and Harvey have devastated the Houston area, and the storms like this are only expected to go stronger and more frequent, such as the recent Hurricane Beryl that hit Houston and Galveston area just a few weeks ago. Barrier islands are supposed to naturally mitigate the damage caused by storm surges, but due to sea level rise, they are unable to. Currently, the city of Galveston has the NESEC plan, a 17-foot wall that would surround most of Galveston coast, but cost an estimated $57 billion and will prevent marine animals going to shore and also disrupt tourism. The changes we observe in Galveston can be observed all over the earth and affect coastal communities everywhere, but sea level rise is not the only thing affected by climate change.
Using astronaut photography, we can observe coral reefs and islands that are either too remote to observe in person or are changing too slowly for direct observation. The two photos shown on the left picture Santa Isabel Island of the Solomon Islands. When compared to the clear blue waters of the top image from 1991, the 2010 image shows plumes of tan sediment drifting outwards from the island and thus creating a murky effect. These areas are known as sediment plumes and are caused by rising sea levels that are a consequence of global warming. When the sea level rises beyond the height of normal tides, the ocean picks up extra sediment and drags it out into the open water, resulting in much of the sediment being deposited on reefs that border the islands. In the Solomon Islands, according to the National Oceanic and Atmospheric Administration, also known as NOAA, the sea level is rising approximately 3.65 millimeters per year, which will result in an increase of 1.2 feet within the next 100 years. In fact, satellite images have proved that at least 5 small reef islands have already been covered, and 6 more are on track to disappear. Excessive amounts of sediment will be picked up from this rise in sea level and these disappearing islands and lead to various consequences for marine life. The most significant consequence is the coral reef damage, specifically the coral bleaching that occurs. This happens in one of 2 ways. Firstly, excess sediment can land on top of and smother coral and block it from accessing light or food. And secondly, sediment that hasn't settled will cause murky water, as seen in the image on the right, that blocks sunlight and prevents photosynthesis. In addition to coral, fish and other reef organisms that rely on the safety of the reef will also suffer, as they struggle to find food and shelter from predators. But change over time can also be viewed in freshwater environments, such as floods and droughts.
As a result of climate change, floods and droughts are occurring at a faster rate, to the extent that communities residing close by cannot respond quickly enough. One flood and drought site that exemplifies this circumstance is the Horn of Africa, a region home to the easternmost part of the African continent. Due to the cycle of Niño Southern Oscillations, ENSO, the warming and cooling of the ocean surface as a result of climate change, weather patterns have become imbalanced, leading to an imbalance in the amount and severity of floods and droughts. This has caused areas such as the Horn of Africa to have a large death toll and many of its populations being displaced due to the damage to their villages and decreased livability. Now, one way to clearly see this occurrence is through astronaut photography. On this slide, there are astronaut photographs of an area within the region of the Horn of Africa, located in Somalia, which convey the aftermath of severe flooding. From 2005 to 2007, there was a visual increase in vegetation and water capacity. A dry swamp became a vegetated swamp, and an area of depression became flooded. While this may be portrayed as a benefit to the dry, hot continent of Africa, this is a rapid change that the landscape and communities residing cannot adapt fast enough to. Seen through resulting effects that have led to millions of dollars allocated in disaster response and over 3 million people to be affected to this day. Whether it be droughts or floods, which occur interchangeably in the Horn of Africa due to ENSO, both cause rapid landscape change, harming the region in its entirety.
Currently, salt lakes around the world are disappearing at an alarming rate for a variety of reasons, including climate change, poor agricultural practices, and the diversion of water away from the lake. A prime example of an affected lake is Lake Urmia in western Iran. As soon as is seen in the image to the left, taken in 2014, Lake Urmia has been experiencing severe volume loss. Its water variation is largely caused by the increased population of the local area. This population increase caused a greater demand for water in the region, which diverted previous sources of water that had been used to feed the lake. Beyond population growth, climate change has also contributed to the lake's disappearance, as it has caused an increase in temperature of the lake disproportionate to the global temperature rise, which is increasing rates of evaporation of the lake. The destruction of the lake is detrimental to its diverse ecosystems, which host a variety of wildlife such as flamingos, migratory birds, and brine shrimp. The health of the lake is also critical to the local economy and people, but hope is not lost for Urmia as efforts are being made to help it. As seen on the image to the top left, back in 2022, Urmia regained much of its water. However, it again lost it in 2023, as seen on the image to the bottom left. This change can be accredited to the works of the Iranian government, as well as the global community, as it has come together to begin to bring this lake back from the brink. However, it still is slowly drying up, and more needs to be done to prevent this lake's extinction. Urmia is just one tale in a story of hundreds of vanishing lakes, which are critical to protect and to study as we learn more about the effects of human activity on the hydrosphere.
The Yellow River, located in China, is one of the most sediment-filled rivers on Earth, which is demonstrated by these images. Its banks are very easily eroded as the current swallows up millions of tons of soil every year, and over 2,000 years has altered the coastline by hundreds of kilometers. Noted by Britannica, the Yellow River has flooded 1,500 times since the 2nd century BCE, causing unimaginable death and devastation. There were 3 historical floods on the Yellow River in 1887, 1931, and 1938. These 3 floods collectively killed millions and are considered the 3 deadliest floods in history and among the most destructive natural disasters ever recorded. The primary challenges of the Yellow River can be attributed to reduced rainfall, increased water demand, and overuse from agricultural and population demands. On occasion, the river has dried up before even reaching the delta. The increased usage of the Yellow River is a pressing issue as the river's water pollution problem worsens as the flood risk increases due to the high amount of sediment. At the same time, more sediment makes the water murky and increases the chances of fish gill blockage. Sediment fills the bed of the Yellow River when flows are low, and according to NASA Earth Observatory, the river is already perched above the surrounding floodplain by as much as 10 meters. Now, Brian will be discussing how algae blooms change over time.
Thank you, Quinn. Climate change has significantly altered the hydrosphere, impacting aquatic ecosystems and threatening various organisms due to unpredictable weather patterns like droughts and floods. One effect few know about are algae blooms. Algae is important to the Earth, being one of the greatest oxygen producers and carbon dioxide absorbers, as well as providing nutrients and habitats to aquatic ecosystems. Algae can also be harmful to the environment. When harmful algae blooms begin to decompose, a bacteria that aids in the process releases a toxin which extracts oxygen from the surrounding area, suffocating fish. Climate change has caused fluctuations in algae blooms worldwide. Higher water temperatures have increased and decreased algae growth unpredictably. Lake Natron, located in northern Tanzania, is a unique environment with high concentrations of alkaline and volcanic minerals, making it an ideal habitat for algae. The algae in the lake is lethal to most animals except for avian species such as lesser flamingos, pelicans, storks, etc. Because of the rising water temperatures, unpredictable weather patterns have distributed the equilibrium of the ecosystem in Lake Natron. This can be observed in the above image, which was taken in 1993, and the below image taken in 2002. Severe water reduction can be detected in the below image comparison to the above image. This reduction causes the salinity in the lake increase, promoting algae growth. But because of the reduction in water, algae is limited to the area it can populate. The microorganisms in Lake Natron are a crucial food source for the lesser flamingos and other species in the area. With less algae available, the food supply for these birds diminishes, leading to a decline in populations. Through astronaut photography, we can observe these changes over time and understand the full extent of the impact. This visual data helps researchers track the decrease in algae and its ripples effects in the environment, emphasizing the need for conservation efforts to protect the vulnerable ecosystems.
In conclusion, using astronaut photography is incredibly beneficial for studying the various aspects of our Earth's hydrosphere. It is also important to talk about the continuous work and effort being put into research and protection. Using information gathered from satellites, such as the GRACE and GRACE-FEL missions, shown on the left and right respectively, groundwork, and astronaut photography, NASA continues to research the hydrosphere as it becomes increasingly affected by climate change.
This knowledge is vital to understanding how our hydrosphere is changing to combat the negative trend better. Astronaut photography, by playing a significant factor in this research, is therefore also essential in protecting our hydrosphere.
Because of this, there are different ways that the public can interact with astronaut photography. The main access point is through the website Gateway to Astronaut Photography on Earth. Here, you can pursue both curated collections and find specific places on Earth using the Explore or Search tab.
Additionally, there are the Where in the World activities created by the Aries Science Engagement Office that allows you to explore the world through astronaut photography. In conclusion of the internship, here are some final reflections of our experiences here.
Because of the mass amount of astronaut photography provided to us, it was difficult to find specific images we were looking for. An additional challenge we experienced was combining our individual research together for the presentation because of their diverse nature. To overcome these issues, we narrowed our search field to the hydrosphere and practiced navigating the gateway to astronaut photography until we found the correct data.
Regarding NASA SEAS, we want to mention how impactful this internship has been. SEAS allows us to network with excellent professionals in the fields of our interest and collaborate with peers from diverse backgrounds to explore a joint passion for space and learning.
One of the most memorable parts of this trip was getting to know and get close to people from all across the nation. The friends and connections I made along the way made the trip one I remember forever. In the photo, it shows me and my team when we decided to paint and play games together after a long day of work.
This experience has provided us with such an amazing opportunity to work with and under the guidance of professionals who genuinely care for us and our success.
An amazing part of my experience here at UT Austin was visiting the Aerospace Engineering and Engineering Mechanics Department. Visualizing and listening to workshops and projects I would possibly participate in was exciting to hear and helpful towards the visions I have for my future.
My favorite aspect was meeting with a real-life astronaut. This is Dan Tanney, who was an astronaut aboard the ISS.
The most memorable experience for me was when we visited the Johnson Space Center in Houston, Texas, and were allowed to tour the different buildings, as touring a NASA facility is an experience I would have never had back in New York.
The research and experiences at the Center of Space Research were definitely an adventure. I enjoyed the many speakers, experiments, and teamwork activities hosted there. The image I selected was one of my favorite experiments dealing with microgravity.
My favorite part of this program was our time together as a team at Fly, an indoor skydiving experience where SEAS students learned about the aerodynamics of wind tunnels, were able to calculate their terminal velocity during our flights, and of course, indoor skydive.
The most memorable time I've had here at SEAS is when we went to Fiesta, Texas. While at the amusement park, interns were tasked to perform their chosen experiments with the Z-cube we had been learning about, basically collecting data on how microgravity affects our experiments while going on all the fun rides.
Firstly, we want to thank Ms. Rosina Miller from the Johnson Space Center for guiding us and giving us insight on how researchers work at NASA.
Next, we would like to thank Margaret Baggio, Selena Miller, and the rest of the NASA SEAS team and Center for Space Research for giving us this opportunity to work and research as interns.
Lastly, we would like to thank Florestela Gomez for guiding us every day and supporting us through our work.
Thank you all for coming and giving us your time today. We will now be opening up the floor to questions.
So for those of you who have not had an opportunity, please post your questions in the Slido app. We invite all members of the team to please turn on your cameras and unmute your microphones so you'll be available to answer the questions that have been posted. So our first question is, what are the benefits to using astronaut photography to study these regions as opposed to unmanned remote satellite imagery?
I can answer that question. So satellites can often provide more precise data, such as like accurate measurements of water and stuff like that. But astronaut photography, there's more historical evidence as photos date back from the earliest space missions before there were satellites orbiting the Earth. There's also various light angles or light levels from the sun, so you can take images at night or during the daytime, any time of day. Also various angles, like camera angles, which can offer unique perspectives. And finally, there's also a lot more of the Earth that can be covered because the ISS orbit around the Earth is different every time it goes around, so it can capture more of the Earth. In comparison to a satellite, which maybe only has a set orbit.
Great. The next question, is there any way to get quantitative measurements from astronaut photography?
Okay, I can answer this question. Like she said before, satellites are able to get more quantitative data, while astronaut photography is usually used to see and analyze it. So we're able to look at these images and it will make it more so for scientists to identify spots that they want to do further research into, rather than getting quantitative data. So it's more of an observation tool than a measuring tool.
Okay. How did you select the areas that you wanted to study?
I'll answer this one.
So, when crafting our articles, we each chose a topic under the hydrosphere, and we all concentrated on areas that have been severely impacted, whether it has visual changes through astronaut photography or basically on society. And so, with mine, flooding and droughts, I particularly chose the Horn of Africa because I noticed that it was having a lot of impacts on society, a lot of death toll, a lot of displacement. And I further researched into the astronaut photography that was given of that area. And there was also visual changes as well. And so we noticed more on areas that just you could see a lot of significant impacts on that were significant towards our topic.
What was the most difficult part of your project?
I'll take this one. The most difficult part was finding specific images due to the abundance of astronaut taken photography. Our mentor, Miss Miller, did an amazing job with providing us with so much astronaut photography. But as we practiced and got better at using the platforms, we were able to narrow down our search by searching for specific water bodies or even coordinates.
Did you see anything through the astronaut photography that surprised you?
I can answer this one. So I think when we started the project, we all knew that we wanted to observe change over time due to climate change, but it was really the drastic visual differences that we saw in the comparison photos that opened our eyes further as to how much climate change was impacting us and how much we could actually see that from space.
Would I have access to photos that were taken by astronauts?
That's a great question. I can take it. So yes, using almost all ISS astronaut photography is available to the public. All you have to do is go to the Gateway to Astronaut Photography on Earth website, and there they have a couple different areas. So you could do the Search or Explore tab, which, if you want to look up a specific place, like I'm from New York City, so I Googled New York City, and then all the photos ever taken of New York City from the ISS are then going to be listed there. Or if you just kind of want to peruse some more, or like you have specific areas you want to look at, such as like mountains or lakes, there's also collections tabs. And so then scientists have gathered photos that either they find really interesting and to put that in one collection, or again, like photographs of like, these are oceans that are being hurt right now, or these are landforms that are specific to an area of research. So yeah, that's the Gateway to Astronaut Photography on Earth website. It's really cool. Everyone should check it out.
Great. So well done, your whole entire team. Has this inspired any of you to pursue a career in studying the hydrosphere?
I can answer this one. So I have always been more interested in environmental science and conservation of the earth. And since we are able to observe like all the changes that are happening right now and how we impact it, I would want to do more to conserve the hydrosphere and see how we can preserve it.
So given how technology advances so quickly, such as AR, VR, AI, how do you see the progression of astronaut photography technology over and its use in the next 20 years?
So one thing that's unique about astronaut photography is the ability of a human being to take pictures. So I don't think that aspect's gonna go away. One aspect that's gonna make it from AI that's gonna make astronaut photography more accessible is the ability for AI to recognize different features. So for example, the Astronaut Photography Gateway website sorts things by landforms. So for my project, I looked up sediment plumes, and AI located sediment plumes in images and showed me those images. So with advancing technology, that aspect will get better. So it will make it more accessible to people to view changes in specific regions.
Well, you have done an excellent job. I know everyone joins me in thanking you for sharing your research and your experiences at SEAS. So thank you to the astronaut photography team.
Thank you.
So our next project, we will continue with team presentations from our Moon team. Their mentor is Dr. Ernest Lewis, who works in the Ares group at NASA Johnson Space Center, where he studies surface science techniques for new methods in planetary sciences and planetary exploration, along with sample return missions for NASA. The project assistant for the Moon team is Miss Becky Busby. So please join me in welcoming the Moon team presenting Discovery, Research, Exploration, and Analysis on the Moon, the Dream Lunar Base.
Hello, everyone. We are the Moon Exploration and Habitation team. Our project name is DREAM, which stands for Discovery, Research, Exploration, and Analysis on the Moon. Today, we will present our design concept for a lunar research-based system, which addresses long-term moon habitation and explores research working directly with native lunar materials. But first, I will introduce our team. My name is Yelisei Romanov, and I'm the Radiation and Travel Safety Specialist. Samantha Moorhead is our lunar base architect. Ann Johnston is our Cosmic Transit Specialist. Judith Martinez is our Physical and Mental Health Specialist. Sriman Bakam is our Data Transfer Specialist. And Angelina Tran is our Landing Site Specialist. Additionally, Judith, Sam, and I are in charge of the Alpha experiment. Sam and Angie are in charge of the RIM experiment. Judith and I are in charge of the Plant experiment. And Sriman and Ann are in charge of the LORE experiment. The goal of our project was to create a plan for a permanent moon habitat which supports 4 specific lunar experiments. Additionally, we designed our experiments to be beneficial for further development in space habitat design.
Space radiation is one of the more dangerous hazards of space travel. Typically, space radiation refers to high-energy galactic cosmic rays, solar particle events, and coronal mass ejections. The Earth's atmosphere and magnetic field block cosmic radiation, preventing high-energy gamma waves from reaching us. However, the atmosphere and magnetic field are absent on the Moon. If astronauts fly without proper shielding and countermeasures, they will be exposed to gamma radiation, leading to an increased risk of cancer, neurological disorders, and degenerative tissue defects. Light mass, hydrogen-rich materials should be used to minimize the radiation the crew is exposed to. Previously, NASA utilized polyethylene to protect the ISS from radiation. However, we will be using Kevlar since it is just as effective at shielding radiation as polyethylene, and it can be incorporated into our inflatable lunar habitat. At best, Kevlar might reduce the equivalent radiation dose by 34% at 5 grams per centimeter squared thickness. Therefore, radioprotective agents and medical supplements should also be used to ensure the safety of astronauts. Astronauts should consume antioxidant foods such as onions, tomatoes, and carrots to reduce radiation-related oxidative damage. Additionally, pharmaceutical treatments such as radioprotectors and radiomitigators can be given to astronauts exposed to high-energy ionizing radiation, respectively. Finally, scientists can monitor the radiation levels in the habitat using a hybrid electronic radiation assessor and assign treatments accordingly.
Commercial lunar payload services, also known as Eclipse, will be crucial in sending prior necessities, support frameworks, and technologies before the astronauts' arrival to lunar service near the permanently shadowed regions. Examples of these American commercial companies consist of SpaceX, Blue Origin, and various other companies. Together, these companies will help NASA expedite the mission process, mission requirements, and stimulate a new upcoming space economy. According to our plans, the first payload is to be transported 2 weeks prior to the astronauts' arrival to the lunar surface. This payload will consist of our deflated lunar base and our energy source of solar panels within the rocket. The second payload will arrive a week prior to the astronauts' arrival, consisting of the technologies, our lunar terrain vehicle, as well as our ice tracking and lunar regolith collecting rover. Our last launch, which will be a few days before the astronauts' arrival, will consist of the astronauts' food, medication, and resources, which will be used by the astronauts on a nearly regular basis. To achieve the goal of sending our payloads out and our astronauts, the DREAM mission will combine use of both SpaceX's Starship rocket and NASA's Space Launch System. Starship will be our primary method of transporting heavy payloads because of its size, payload capacity, and ability to alleviate costs with its reusable Raptor engines and super heavy booster.
NASA's SLS rocket is also a great option because similar to Starship, its advanced core stage and use of liquid oxygen and hydrogen make it another great resource for transporting payloads and the astronauts. Lastly, Gateway will be crucial in the DREAM mission for communications, transportation, monitoring, and more. It will also be essential in the arrival of the astronauts to the lunar base with its highly elliptical near rectilinear halo orbit and international partners, which will help make the arrival of the astronauts successful and create a path for future Mars missions.
An important aspect of building a lunar base is selecting the optimal landing site. After lots of consideration, the peak near Shackleton crater was selected based upon reviewing the following parameters: sunlight for power, area for landing, permanently shadowed regions, etc. The most important aspect is the existence of water ice, a necessity to human survival on the lunar South Pole. Satellites have confirmed that the albedo, or natural reflection, of the crater is high, thus highly suggesting water ice. Additionally, MIT believes that water ice may make up to 22% of the crater floor's micron-thick layer. Furthermore, 3 points on the rim are continuously lit for 90% of the year, which leads to stable temperatures. Not only that, but the terrain is smooth compared to other regions. With a slope of 5 to 10%, it is a suitable area to not only build a lunar base, but explore. Currently, NASA is reviewing 13 landing sites, and the peak near Shackleton crater is our recommendation. While the landing site is not in the line of sight for direct moon-to-Earth communication, we are excited about demonstrating a capability of routing communications through satellites and space stations such as the Lunar Gateway Space Station. Overall, Shackleton will best take care of our needs for human existence and science experiments by allowing a foundation for both sunlight and opportunities to explore permanently shadowed regions for Artemis missions in the short and long-term project plans for NASA.
The lunar lab must be able to withstand a wide variety of threats present on the moon, such as a lack of atmosphere, radiation, micrometeor showers, launch debris, regular dust, humidity, and extreme temperatures. Due to the necessity of protecting against micrometeor showers, the base structure needs to evenly distribute forces and pressures. The best structure for this is a geodesic dome, which is a hemispheric structure that utilizes triangles with their geometrical advantages to distribute stress, enabling it to endure heavy loads effectively. This lunar base also has a hybrid inflatable design with 2 layers. The inner layer is an inflatable membrane structure, which is very beneficial for transportation as it is cheaper to travel and takes up less room. The inside layer will be made up of multiple layers made primarily of Kevlar 29, which is resilient to radiation and good for installation. This layer will also serve as the temporary base while the outer base is being built. The outer layer will be made of lunar regolith bricks, which can be developed through a process of crushing, melting, and compressing the regolith to make concrete-like material. By working towards in-situ resource utilization, or ISRU, we limit the materials we must bring, break the resilience of the moon to the Earth, and help with protection from both micrometeor showers and cosmic radiation. The entrance is in the garage, where we will store all Rover's robots and be able to repair parts, as lunar surface is extremely abrasive to mechanical and electronic components. Through the airlock, the astronauts will be able to store spacesuits and access the main base, which will house communications and central lab equipment. This is connected to a storage area, which will house environmental control and life support system, a very powerful filter, and other supplies. The living area, also linked to the central lab, serves as the astronauts' dining, sleeping, and workout space, as well as our Alpha lab. The RIM lab and in spacesuit lab is outside the garage, and both Plant and Long-Range labs have their own lab, with Plant having access to a greenhouse. For all of this base to be powered, we plan on using solar panels. Since we are in the South Pole, solar power is a very feasible option as we receive sunlight 90% of the year. The solar panels will make up 125% of our estimated energy budget, allowing for a margin of error.
During an astronaut's stay on the moon, they must stay in excellent physical and mental shape. An astronaut's food, nutrition, water quality, base lighting, exercise schedule, spacesuit, and sleep schedule are essential to keeping an astronaut mentally and physically fit. One of the biggest issues with the reduced gravity on the moon is loss of bone and muscle mass by 1% for every month spent in space. To stop reduction of bone and muscle mass, the astronauts must exercise at least 2 hours every day. Besides losing muscle and bone mass, astronauts will experience a disruption in sleep and appetite. The lunar base must have lighting that simulates Earth conditions in order to allow the astronauts to develop healthy sleep rhythms. The change in appetite that might be experienced might be due to the lack of food variety. To solve this, many different types of dehydrated food must be brought up to the moon. Some examples of food and drinks to take are MREs, freeze-dried food, powdered drinks, dried goods, and canned goods. About 360,000 calories worth of food must be brought to the moon in order to support 4 astronauts for the 45-day mission. Taking water to the moon is expensive, so an environment control and life support system along with 530 gallons of emergency water will have to be installed in the lunar base. The environment control and life support system recycles all water in the base, whether it be sweat, urine, or wastewater, and turns it into drinkable water. Another big issue on the moon is lunar dust. Lunar dust, also known as the regolith, adheres to any and practically all fabrics because of its sharp edges. Lunar dust can cause respiratory damage, ocular damage, and much more. An astronaut's spacesuit material must be made from Kevlar, which has thermal stability and high strength, to minimize adherence to regolith. Regolith can't be completely avoided, but measures like the electrodynamic dust shield can be used to lessen exposure to regolith. Regolith can also wear down electronics and machines by jamming them with small particles. For this reason, regolith must be considered when designing spacesuits and machines.
In the experiment, Advanced Lunar Physiological and Health Assessments experiment, we're going to be testing radiation dosage, heart rate, bone density, body temperature, blood pressure, urine samples, and blood samples.
We are doing this so that we can help diagnose any potential problems in our base design, which we can address as soon as possible. Our hypothesis for this is if humans live on the moon for 45 days with protective suits and a secure base, then there will be effects on human health, however, it will be minimal.
Regolith's impact on materials, or RIM, will test the impacts of regolith on 3 different types of materials: Kevlar 29, Tyvek, and ultra-high molecular weight polyethylene, which are all possible materials for making spacesuits or lunar-based material. We will be testing which material is the most effective at long-term resilience to lunar regolith. Our hypothesis is, if all materials are exposed to lunar regolith, Kevlar 29 will be the most resilient. We believe this is so due to its thermal properties, high strength, and resistance to tear. In this experiment, we set up 2 rows of the same materials, one row using an electrodynamic dust shield and the other being a control group. These patches will be on the outside of our lunar base, exposing them to lunar regolith.
Another addition to this experiment is testing electrodynamic dust shield with the hypothesis of if we use EDS on materials once a day, the long-term impacts on the materials will decrease. EDS, as Judith explained, uses transparent electrodes and electric fields to lift and remove dust from surfaces by oscillating electric fields across the fabric. Our test will compare each material in the control group again by using EDS daily to remove the regolith. We will measure the efficiency by weight and visual observations. This aims to test the effectiveness of EDS in the long-term scope. This will also have implications for both spacesuit materials and lunar base materials with both short-term and long-term durations.
Progressing lunar agriculture with native thale-cress or plant aims to test the feasibility and differences of growth of Arabidopsis thaliana in the lunar environment. The goal of the experiment is to determine if there's a benefit in growing Earth-native seeds in lower gravity conditions and analyze if thale-cress can survive in lunar conditions as opposed to just lunar regolith. Our null hypothesis is that thale-cress's growth on the moon will be slightly worse with artificial lighting and much worse in a greenhouse with natural light compared to Earth conditions. However, if the null hypothesis is rejected due to significant evidence, it could mean that plants are just as, if not more, viable to be grown on the moon compared to the Earth.
We'll plant 30 samples of thale-cress in each of the 3 environments tested. The thale-cress used in the experiment is ecotype Columbia 0, which was previously successfully grown in the lunar regolith on Earth by Dr. Furrow and Dr. Paul. Data will be collected by measuring plant height and biomass. Additionally, the thale-cress's growth rate will be monitored and compared across tests. All seeds will be planted in lunar simulant JSC-1A. One group will be grown on the Earth, and 2 other groups will be grown on the Moon. The group planted in artificial light on the Moon and the Earth will receive UVA lighting. The group exposed to natural light will be planted in a greenhouse. Inserting perlite and sticks into the lunar regolith will make the soil more porous, allowing water to reach the roots of the thale-cress.
We are designing an experiment based on the extraction of oxygen from lunar regolith from different depths of permanently shattered regions, or PSRs, on the lunar surface.
While speaking with subject matter expert Ms. Anastasia Ford, we began thinking about applying the principles of our oxygen extraction lab to our mission to apply on the lunar surface.
Lunar regolith contains about 40% oxygen, along with various other metals and carbons. Inspired by this composition and Ms. Ford's research, we developed our own oxygen extraction experiments.
This is a landing site that we will be conducting our experiment from. To diversify our data, we will collect regolith from 2 different depths of the moon, allowing us to account for discrepancies in their conditions they have always been subject to. The regolith collected for our test will be conducted by using a rover or spacesuit EVA to access the 2 depths. Using the NASA proposed lunar terrain vehicle and a drill, we will be collecting samples of 100 grams of lunar regolith from different depths in the lunar highlands.
At a big picture, our experiment will test test the oxygen levels in lunar regolith by subjecting it both to carbothermal and catalytic reactions to produce oxygen gas. Here is a diagram of all our experimental features and variables.
We'll collect all samples from the same area to avoid bias. For each depth, we'll gather 8 separate samples to account for regolith variability.
Here are the steps to our experiment in 5 simple steps. The screen shows the carbothermal reaction of the card reactor. A laser melts the regolith and methane is added, releasing oxides trapped in metals, most primarily silicon oxide. This process releases hydrogen and carbon monoxide. In the catalytic reactor, hydrogen and carbon monoxide combine to produce water and methane. Methane is recycled for further reactions, or it could also be used as propellant, while water undergoes electrolysis to separate oxygen and hydrogen, completing the lunar regolith oxygen extraction process.
The extraction of oxygen from lunar regolith is crucial for a long-term moon base, reducing the need to bring oxygen from Earth. This saves storage and avoids technical issues. Additionally, the oxygen can help manufacture water and fuel for extended lunar missions.
An essential part of our lunar mission is quickly transmitting data back to Earth. This enables NASA scientists to analyze it in real time, maximizing efforts during and after spacesuit EVAs. Our experiments generate vast data, including oxygen levels, atmospheric pressure, temperature, and other variables, all of which must be relayed back to Earth. The most innovative data transfer method for our base is the LINE, which stands for the Lunar Infrastructure Optical Node made by FiberTech. This is a laser-based transmitter proposed in DARPA's 10-year lunar economy plan. LINE uses laser transmission to connect with Earth or other orbiters, seeking contact points to send data quickly. NASA's Lunar Laser Communication Demonstration has shown that this can achieve download speeds of up to 622 megabits per second. LINE will enable communication with Earth and across the lunar surface, supporting astronauts on EVAs or rovers. Data from our experiment and lunar base vitals will be stored on solid-state hard drives with space-hardened RAM. LINE will transmit this data back to Earth. With powerful laser transmitters, I estimate data transmission latency from the lunar surface to take about 5 to 8 seconds. To ensure stable data transfer, the node will connect to the gateway station, which will then relay it to the TDRS satellites orbiting Earth. These geosynchronous satellites handle most of NASA's data relay, and will send the information to JSC or any other NASA facilities for analysis.
Our experiments will try to be processed and recorded on the lunar surface or gateway in order to avoid any accidents during transport or unnecessary handling. If necessary for our experiments or samples to be brought back to Earth, careful monitoring of safety, temperature, pressure, radiation, and more will be practiced. After 45 days, the astronauts will begin their safe journey back home through the lunar lander in the help of Gateway. This approximately 3-day journey will demonstrate the capabilities of spaceflight and our hopes to explore human curiosity for the betterment of humanity.
In reflection, we have all grown so much through this internship and have learned so much more about STEM paths, as well as just so much about ourselves, having the opportunity to interact with like-minded peers, as well as just grow within our knowledge of what we want to pursue in the STEM field. And this has happened because of the speakers we've had an opportunity to meet with, as well as the Z-Cube experiment, as well as our individual project. All of these things have helped form our team and each of us individually to the next level. And I think we would all agree that this internship was very changing and very helpful in our STEM careers and our STEM knowledge. And we would like to thank our mentor, Dr. Lewis, as well as Miss Busby, for creating this opportunity and allow us to grow in these ways, as well as just all the C staff, as well as just highlight some of our favorite things we've done. We had a mentor dinner, we've met on Zooms, we went to JSC, we had a barbecue cookout, we did experiments with petri dishes, we did iFly, we went to Fiesta, Texas, and that's just another photo from iFly. And then lastly, these are all the sources we've used.
Hello, everyone.
So we invite the Moon Exploration and Habitation team to unmute their mics and turn on their cameras to prepare for questions that have been posed by the audience. So the first question for your team is, what will be the effects on the International Space Station community in space exploration if a lunar base is created?
I can take this one. So creating a permanent lunar base will be very important for the international space community. First of all, it'll allow us to push our boundaries regarding space exploration, as settling on the moon will allow us a completely different perspective to the one that the Earth gives us. Additionally, due to the low gravity of the moon, launching satellites and other important spacecrafts would be much more efficient and less fuel consuming, as it would take less to break the gravitational pull of the moon, and therefore allowing us to reach greater depths in space than we previously could. And Ann Johnson as well has some more thoughts to add on this point.
Thank you, Shremont. And to add on to Shremont's point, I'd like to also mention how we've had positive effects already with uses such as the commercial lunar payload services and international partners working together, as well as using the Gateway program, hopefully in the future Artemis missions, which are hoping to be successful with international partners, showing that together the Earth can come together to help in moon exploration.
Great. Your next question is, what software or program did you use to give you the information you needed to select an optimal landing site?
Yeah, I'll take this one. Thank you. So NASA provided us with their top 13 landing sites, and I used websites such as NASA's Moontrek and took data from the Lunar Reconnaissance Orbiter to analyze topography, nearby craters, slope of the surrounding area, and much more. My personal favorite is the Moontrek website, which I actually discovered through a speaker provided by SEAS.
So your next question is, I noticed that the greenhouse was not connected to the rest of the base. Was there a reasoning for that?
I can take this one. So the reason the greenhouse was not connected to the base was to have different. The greenhouse was not connected to the base because part of the plant experiment is to document the effects of lunar atmosphere compared with natural lighting and simulated lighting on the lunar atmosphere.
So what design tool did you use to create your base layout?
Yeah, I can answer this one. I used the base was designed in CAD, so I used Fusion 360 to design the base.
Great. What was the greatest challenge you had when it came to evenly dividing the workload, and how did you overcome that?
So I think the greatest challenge was we were each given an individual section to work on from Dr. Lewis, our mentor. And the hardest part was that some people got their work done a little bit faster than others. And then to overcome this, we made a status chart so that if you were far ahead, you could also help and collaborate with other people within their individual section. So this allowed for us to help each other out. Since Dr. Lewis prioritized tracking work time and status, which allowed us to better help each other and understand the timeline.
How can the radiation research that was completed with long-term moon habitation help with cancer research here on Earth?
So I guess since there's so much exposure on the moon to radiation, that can set new sort of adjustments to the dosage received during like cancer therapy. So I guess the larger exposure on the moon can help with research for developing like new cancer therapy methods based on like how much the astronauts can endure on the moon.
So you're on a team where the Artemis program has selected the first astronauts to head and lead a base. Based on what you've researched, what would you look for in an ideal candidate for this mission?
I can take this one. I think it's important that the astronauts or the ideal candidate picked for the mission has extensive background training in astronaut training, as well as the deep background in the specific sections of our experiments that we plan to run. For example, on our plant experiment, it is important that the astronaut has a background in botany and fields related to that. For our oxygen extraction experiment, it's important that their background in chemistry and fields of that sort. Overall, I think it's imperative that the astronauts have strong backgrounds in the specific sections and goals of our mission to maximize the efficiency of it.
How did working in a team at SEAS prepare you for the future in a STEM career?
Working at SEAS allows you to work with industry professionals and researchers and scientists, and allows you to have a feel of what it's like to work in a STEM field, to work with professionals. So it gives you a lot of experience for working with very experienced people and in a very professional environment. So, yeah.
And what advice would you give to other high school students wanting to apply for SEAS?
I can take that question. I think that the advice I would give is definitely to be yourself and to show your passion, since SEAS is such an amazing program and gives you amazing opportunities. And I think that it's important to show in not only the application, but just a sense of who you are and what you want to help contribute to not only the science community, but our whole society.
Excellent. Congratulations to the Moon Exploration and Habitation team. You've done an excellent job with your research.
Thank you.
Our next presentations are by interns on the Artemis Rhodes Viper team, mentored by Angelita Crenshaw, a science and robotics teacher. So please welcome the Artemis Rhodes Viper team with their project, Development of a 3D printable unibody compliant wheel for enhanced performance of the volatile investigating polar exploration rover, Viper, in extreme polar environments and sustainable exploration.
Hello everyone, we're the Artemis Rhodes team, and for the past 2 weeks we've been performing in-depth research on redesigning the Viper.
Hi everybody, my name is Andre Nguyen. I am from Saratoga, CA, and I am planning to major in electrical engineering.
My name is Simmerlene Carr. I'm from Dallas, Texas, and I plan on majoring in mechanical engineering.
My name is Shanae Baton. I'm from Gardena, California, and I intend on majoring in computer science.
My name is Kalman, and I'm from Houston. In the future, I want to be a computer engineer.
Hi, my name is Ian Shea, and I'm a rising senior from Lake Oswego, Oregon, and I'm interested in pursuing electrical engineering.
Hi, my name is Joe Luna. I am from Houston, Texas, and I plan to major in aerospace engineering.
Prior to creating the mission patch, we discussed many ideas that could symbolize the Viper missions. These included adding ice or water, using a snake to wrap around the patch, incorporating past prototype ideas, placing constellations in the background, and using the shape of the HERA crater, which is where we're going to land our rover. Later on, we decided to add our team name Vieram to the front of the rover, which is Latin for roads, and use colors that would give the mission power and significance. We fused these ideas into a patch, which we hope would stand out in its aesthetics and symbolism.
Our goal is to redesign the Artemis Rhodes Volatile Investigating Polar Exploration rover, known as the Viper, focusing on optimizing the wheel design for detecting ice and water concentrations at the HERA crater located in the moon's north pole. This aligns with NASA's goal to sustainably explore and inhabit the moon. Our team's collaborative approach involved extensive research and the exchange of ideas to tackle the challenges of designing a lunar rover. We began by setting our team goals and Viper mission objective, focusing on enhancing rover performance in the HERA crater. Next, we examined the current Viper design to understand its strengths and limitations. We then researched potential improvements and identified the challenges. Throughout this process, we consulted with mentors and NASA engineers to gather valuable insights. Using this information, we designed a prototype incorporating our proposed improvements. Finally, a failure mode analysis was made upon our design to identify possible failure points and build its resiliency.
Artemis Viper rover stands at 8 feet tall and measures 5 feet in both width and length. It moves at a speed of approximately a quarter to half a mile per hour and is equipped with several scientific instruments, those being the neutron spectrometer system, the regolith and ISRO for exploring nature, also known as the Trident system, the near-infrared volatile spectrometer system, and the mass spectrometer system for lunar operations. Powered by solar energy, Viper communicates through NASA's Deep Space Network, maintaining a direct-to-Earth radio link that requires a of Earth. Communication has a 60-second latency, and scientists use the rover's data and images to avoid racing the wheels and help it overcome rocks and steep inclines. This flexibility enhances the rover's ability to explore diverse lunar landscape, ensuring it can reach and study scientifically important sites that are otherwise difficult to access. This also allows Viper to traverse the unique lunar landscape and terrain without the worry of a malfunction or damage to the structural integrity of the rover, whether it be the rover itself or its wheels. In order to simulate the vertical movement of the wheel modules on the Viper rover, we determined that we had to use a 4-bar lifting mechanism. But what is a 4-bar exactly? Well, a 4-bar lift is a simple mechanical system that is used to raise or lower objects. It consists of 4 bars connected in a quadrilateral shape, with 1 bar anchored to a vase and the other forming a movable parallelogram. As one of the bars is pushed or pulled, the entire structure moves in a coordinated manner, allowing for controlled vertical motion. We also decided that in order to be able to rotate the wheel, we would have to use a pivot system that could allow the wheel to rotate up to 35 degrees when rotating to either side. In this video, we demonstrate the Lego model we've made. We made this in order to be able to visualize the mechanisms used on the Viper's wheel modules. This would also help us eventually when we decide to scale the model into a larger structure using VEX parts. What you see here is a scaled up version of the replica we made using Lego parts. However, now we're using VEX parts in order to mechanize the systems and be able to use motors to basically replicate the movements of the Viper's wheel modules. By building a scale replica of the Viper's wheel modules using VEX parts, we can have a hands-on understanding of the mechanical systems used and potential challenges of our wheel design. By motorizing these parts, we can observe how the wheel pivots and braces in real time, allowing us to analyze the stresses and strains on various components. This process also helps identify weaknesses and areas for improvement, ensuring that our designed enhancements are both practical and robust for lunar conditions. Additionally, constructing the module creates an iterative design approach, where improvements can be tested and refined through direct experimentation. By replicating the wheels' movements and functionalities, we can gain insights into the rover's mobility and stability on uneven lunar terrain.
To further the Artemis mission's end goal of creating a sustainable lunar base, a robust and easily replaceable wheel design is critical for effective moon exploration and habitation. In current and future expeditions to the moon, rovers need to be able to quickly and reliably traverse the lunar terrain for everything from transportation of humans and goods to scientific exploration to the depths of lunar craters. In order to effectively identify areas of improvement in current lunar wheel designs, we analyzed the existing wheels used on the moon from NASA.
We needed a method to compare the effectiveness and durability of various materials. We were fortunate enough to have a discussion with Becca Siegfried, a NASA flight director who introduced us to technology readiness levels, which indicate how thoroughly tested and ready technologies are for use in space. To aid our decision to use certain materials in improving the design for the Viper, we used NASA's technology readiness levels, known as TLR. This scale, ranging from 1 to 9, assesses the maturity of a technology throughout its development.
First of all, we will be starting with Perseverance rover's wheels. Unlike the lunar surface, Perseverance was built to combat Mars' relatively rocky surface. It is 0.5 meters in diameter with 6 curved titanium spokes to provide better control over rough terrain and small straight treads across the circumference of the surface. These specific components allow the wheel to retain its low weight while keeping with the minimum requirements of Mars' environment. The materials, weight, and durability were important considerations during the design process, as well as the TRO rating. Because of these criteria, aluminum and titanium were selected due to their relatively low weight and high strength.
While talking to Mr. Adam Noakes, a lecturer at the University of Texas at Austin, one of the questions we had regarding wheel design was why wheels with mesh weren't used in the current Viper. He explained that because the intended speed of the Viper was a maximum of 0.5 miles per hour, there was no need for the compliant design the mesh offered, as it would be an unnecessary use of material in space. Additionally, Mr. Noakes introduced us to the superelastic tire. The following suggestions made on the superelastic tire were made by Dr. Rajiv Dwivedi, a PhD in mechanical engineering. The superelastic tire uses a woven shape memory alloy, nitinol, to create a tire that doesn't require air. Dr. Dwivedi made some suggestions to increase traction and reduce weight and material. But after researching more into these suggestions, we realized that while this design provided increased traction, speed, and was a compliant wheel, it was difficult to manufacture, which strayed from our objective of creating a sustainable design that could be used in future settlements on the lunar surface.
The latest revision of Viper's wheels include many similarities and differences from Perseverance. Its size of 0.5 meters, aluminum build, and spokes mimic Perseverance's specifications. However, due to its use on the lunar surface, it has small shovel-like treads, which are better equipped for traveling through regolith and navigating rocky areas. It also features holes of varying sizes across its outer rim and treads, which may be useful to reduce weight and prevent buildup of various materials. The wheel itself is meant for low speeds of 0.8 kilometers per hour, using the rover's suspension for shock absorption. The goal for improving wheel design for the Viper rover is to combine the successes of past wheels, incorporating features from the Curiosity and Perseverance rovers. With a wheel diameter of 0.5 meters, design will utilize lightweight and durable materials like aluminum and titanium to withstand the harsh lunar environment. Adjustments will be made to enhance mobility over the regolith, ensuring better traction and stability. The compliant wheel will be optimized for 3D printing, allowing for easy production and maintenance. These improvements aim to boost the rover's capability to navigate and explore the diverse and challenging lunar terrain.
After extensive finite element analysis in 12 unique iterations, we came up with the design you see here today. Utilizing a unibody design while leveraging the ductility of titanium, the wheel is able to absorb shock while traveling along the uneven lunar surface without the need for complex suspension systems. This is accomplished through built-in titanium leaf springs connecting the outer wheel to the center hub, which provide compliance. We extensively studied how the specific geometry and material of the wheel impacts the compliance properties under load, which will be shown in a later slide. A compliant wheel design is critical for higher speed travel along the lunar surface. By increasing contact time through our design, it then follows from Newton's second law of motion that the impulse force will decrease, effectively absorbing the impact into the wheel. This allows wheels to travel at a higher speed where large momentum changes are more frequent. This wheel would enable faster travel than currently possible with the Viper's rigid wheel design. The wheel still preserves the lightweight and simple construction that made the existing design so reliable. Here you can see the wheel geometry up close. The overall wheel has a diameter of 0.5 meters and a width of 0.2 meters. We derived the specific geometry through finite element analysis to maximize the displacement under load while ensuring the wheel doesn't structurally fail. This primary innovation of the shape is the variable width of our leaf springs. The outer springs are thinner than the inner springs, which helps to create a favorable deformation to force profile. Furthermore, the shape is designed to create limits of deformation, ensuring that in the event of a high force on the wheels, they don't move past their limits of elastic deformation. You can see here that if the wheels deform too much, the springs will collide, preventing further deformation. These features all help to create a compliant yet robust design that is able to absorb shock without risk of breaking. The intention of the wheel design is to be produced using metal 3D printing. The ideal technology for this wheel is selective laser melting, or SLM, which uses a powder metal stock, in this case titanium, melting it precisely with a laser, layer by layer, to build the part. This process is ideal as it produces extremely strong parts at nearly full density when compared to traditional manufacturing, while allowing for much more complex geometry not otherwise possible. As previously mentioned, we used extensive finite element analysis, or FEA, in the development of our wheel. Manufacturing multiple iterations would have taken too long and increased our iteration cycle too much. So FEA became an invaluable tool that enabled us to test and rank our designs with quantitative data rather than just theory. We used FEA to both analyze the geometry as well as material for the wheel. We primarily utilized Fusion 360's built-in FEA analysis, looking at the displacement as well as safety factor under static loads. Within Fusion 360, we determined that a minimum safety factor of 3 was acceptable. The safety factor is essentially just a number that determines how likely the part is to fail at any given point in the object under a certain load. Anything under 3 is considered dangerous and at risk of failure, so we set that as our minimum acceptable value at high loads. The use of Fusion 360's built-in FEA meant that we were able to quickly run simulations while altering designs, allowing for extremely quick iteration cycles when compared to other softwares.
To re-emphasize, our design goals sought a 3D printable, compliant wheel design to absorb impact better, increase traction, and traverse the lunar surface at higher speeds. So, the main design criteria is going to be to maximize the wheel's displacement or compression. Of a lesser importance but still a consideration is that the wheel should have minimal deformation at rest while maintaining its capability for large displacements. This ensures more efficient travel when the rover is moving at a constant speed with little momentum change. Shown here is our first prototype. We started by taking inspiration from existing unibody compliant wheels, which integrated a suspension system into the wheel through curved spring-like spokes. Our simulation revealed that the wheel was only able to achieve a maximum displacement of about 13 millimeters. Compared to the wheel diameter of 500 millimeters, there was less than 3% of deformation. A major reason for the lack of compliance is the thickness of the spokes, but the thickness was necessary for the wheel to withstand the weight of the rover. This leads us to our second prototype design. We increased the number of spokes and adjusted the shape to be thicker at points that were more likely to fail, and thinner at safe locations to increase the compliance. We designed this wheel to be optimized for 3D printing tests. Although it compressed relatively well at a small scale using plastic material, it did not scale up to metal. This wheel was only able to compress a maximum of 6 millimeters, or just about 1% of deformation. Our third major prototype was an optimized version of our first prototype, achieving a much greater compliance through thinning the metal and greater strength by increasing the amount of spokes. This wheel was able to achieve almost 49 millimeters of displacement, pushing us to a deformation of 10% of the wheel's diameter. Our final prototype utilized the information gained from previous iterations combined with a unique design to optimize for strength and displacement through the idea of integrating a layered design of spokes. The inside wheel has a larger width to increase the strength of the inner spokes that support the load from the rover onto the axle. The outer wheel spokes are much thinner to allow for greater compliance. With this design, we achieved 70 millimeters of displacement. The greatest amount of displacement we were able to attain at a safety factor of 3. This wheel design allows for deformation of almost 15% while maintaining a unibody design and 3D printability. Additional benefits of this wheel design include possible scalability by adding more layers to optimize for certain properties such as compliance or strength. To better inform our final conclusions, we collected simulation data in a spreadsheet and processed it in MATLAB. In total, we compared 3 materials: aluminum, steel, and titanium, and 6 different wheel shapes, including our prototypes, our final design, and the original Viper and Perseverance wheels. Graphical analysis of the displacement of the different wheel shapes and the materials pointed to the best combination of design and material. To achieve our objective of finding the wheel that allows the greatest displacement, we set the safety factor to a constant of 3 and plotted the maximum load of the wheel against its maximum displacement. Although we would also like for the wheel to be strong and withstand more weight, compliance is the more important factor for us. Clustered in the bottom are the wheels with less compliant properties, such as the Viper wheel, the Perseverance, and our early prototypes. Filtering out all the wheels with less than 5% deformation or 25 millimeters of displacement, we are left with the graph on the right. The Viper and Perseverance wheel completely disappeared from the graph, which makes sense because they are rigid wheels that are not meant to be compliant. From the filtered graph, it is easy to tell that the final design has the most compliant properties. Next, we looked at our second objective of maintaining minimal deformation at a rest state of 174 newtons per wheel. Again, filtering out the non-compliant wheels, we are left with a clear graph on the right. The graph shows that the titanium versions of Prototype 3 and the final design best match this criteria, whereas the aluminum model remains too flexible. Though Prototype 3 has the least deformation at rest, the difference is minimal and the final design has a greater safety factor, so overall, the final design has the most optimal properties. Finally, we analyzed the observed properties of each material from the simulation to determine the optimal material. To determine the average compliance of the 3 materials, we first processed the data in MATLAB, calculating the average displacement of each material at a safety factor of 3. Then we plotted it on the bar graph. From the graphs, it is revealed that titanium is the best option to optimize for compliance. We repeated a similar analysis for the average strength of each material by plotting the average maximum load at a safety factor of 3 in the bar graph. Unsurprisingly, steel is the strongest out of the 3, then titanium, followed by aluminum, which is the weakest by far. We can conclude that of the 3 materials, aluminum is the least optimal, and although steel has the best properties for strength, it is not as compliant. More importantly, steel becomes brittle at low temperatures, becoming unsuitable for lunar exploration of the poles, where temperatures can reach as low as -249 Celsius. Thus, titanium is the optimal material. In addition, high concentrations of titanium are found on the lunar surface and can be harvested for 3D printing. When talking to Mr. Zebulon Scoville, the lead flight director for the Artemis missions, we learned that NASA is indeed planning to send a 3D printer to the moon and utilize the metals of iron and titanium on the moon to build habitats. This allows our wheel to be cheaply and sustainably produced for lunar rovers and transport on the moon.
Another crucial aspect of wheel design when traversing the lunar surface is the tread design. In order to effectively tackle the quicksand-like environment of permanently shattered craters, unique geometry is required. We decided on built-in treads much like the Viper and Perseverance wheels, borrowing the shovel-like shape that was extensively tested on the Viper rovers with the wavy pattern of the Perseverance treads. Due to the soft quicksand-like soil in the lunar surface, the shovel shape helps decrease sinkage, ensuring the rover does not get stuck. After talking to Rebecca Siegfried, who worked extensively on the Mars 2020 Perseverance rover, she explained how the triangular straight pattern on the Curiosity rover had issues with durability after years of use. The corners of the triangles created weak points that were susceptible to damage from the rocky surface. While the lunar surface is less rocky than the Martian surface, when traveling at high speeds, possible weak points in the wheels are necessary to limit. Furthermore, the wavy tread pattern is easily handled by the 3D printer, ensuring the unibody design while maintaining high traction across the regolith.
The main challenge faced by the lighting plus camera system is the environment it has to endure and the journey that rover has to travel to reach its destination. While the current design employs a lighting plus camera design in which the lights and cameras are attached separately, our modified design suggests a method of combining both systems to reduce the space occupied. The following combined design uses the original navcam design and adds a lighting system around the camera to ensure sufficient lighting in the camera view. The slight gap between the camera lens and the inside of the lighting ring ensures the camera can change focus while keeping the light in a stable position. Furthermore, we saw that the exposed ridges of the camera's length in the original design could be degraded by the lunar regolith, which is why our smooth and simple design, seen in Figure 3, prevents lunar regolith from obstructing the functionality of the instrument.
Operating in the extreme shadowed conditions of the Hermite crater presents a challenge for the Viper mission. To address this, a thermal regulation system has been worked upon in collaboration between NASA and advanced cooling technologies. The system includes loop heat pipes with integral control valves, which have a TLR of 7 for precise temperature management over long distances. External ammonia constant conductance heat pipes, which have a TLR of 8 for passive heat dissipation, and honeycomb radiator panels with embedded conductive heat pipes, which have a TLR of 6 for efficient heat radiation. These tools minimize power consumption and extend mission duration by reducing the required survival heat while ensuring the Viper's hardware can withstand temperatures as low as negative 249 degrees Celsius without relying on active cooling. The new design will implement the system, which is already highly advanced and tailored to the specific challenges of the lunar environment.
One of the challenges that we faced during the early stages of our research was that we were having difficulties in finding the details from the previous rover wheel designs. With the help of Adam Noakes, a lecturer at the University of Texas at Austin, we were able to find various sources that directly applied to what we were looking for. One of the highlights of our team was that we were able to use our varying skill sets to contribute to the project. While some of our team members were better with hands-on work, others were better at researching and technological applications. Together, we were able to build on each other's ideas and create our final product.
Over the course of my time here, I've gained invaluable experience working with a like-minded team on real research. This experience has further strengthened my love for engineering and affirmed my desire to pursue a career in space exploration.
During my time in the SEAS program, I've had the opportunity to work extensively in a research environment, all while being able to collaborate with other like-minded individuals in an attempt to achieve the same goals. This experience has strengthened my goals in pursuing a career in aerospace engineering, as it will allow me to continue working on big projects in specialized teams.
Like many before me, I thought the SEAS program was vital in expanding my understanding in engineering. The lectures, assignments, and even long-distance experiences were beneficial in developing my future career.
During SEAS, I had the opportunity to use CAD software for the first time, and I was able to learn how to use my research abilities in the engineering design process.
The SEAS program has deepened my understanding of space exploration and earth sciences while honing my skills in research, problem solving, and teamwork. This opportunity has allowed me to even apply what I've learned to a real space mission.
From the SEAS program, I was introduced to new career pathways while also teaching me the priceless joys of working with a motivated team. The experience also furthered my resolve to pursue a research career in STEM to experience similar excitements.
Finally, we would like to thank everyone who contributed to developing, assisting, and enriching our research. These people include our mentor, Angelita Crenshaw, Becca Siegfried, Brian Day, Parker Francis, Rajiv Dwivedi, Zebulon Scoville, and Selena Miller, and Margaret Baggio for directing the SEAS program.
So excellent job. I'd like the Artemis Rhodes team to please unmute and turn on their cameras. We have several questions for your team. Our first question is why a higher deformation is preferred for the wheel design?
Yeah, so I can take this one. Early on when we were researching the wheel design and how it could be improved, one thing we noticed about the Viper wheel is that the rigid nature of it limits the speed that the rover can travel. So the Viper is actually only designed to travel, I think, at 0.5 miles per hour as a top speed, which is extremely slow, which specifically for the Viper is okay because its primary goal is prospecting. But for future rovers where you want to actually go faster to transport materials and work with humans, having a wheel that can deform under load allows you to travel at higher speeds, since having a certain level of compliance in your wheel means that as you're traversing over the uneven lunar terrain, the shock and the impulse of any collisions you may have with the lunar surface, like rocks and uneven things on it, will be spread out over a longer time period, since when you hit it, the wheel will actually deform, reducing the amount of shock that goes into the rover. So we were talking to one of the Viper engineers, and he was talking about how with the current Viper design, you really can't travel fast at all. Otherwise, you will end up damaging the rover, as if you hit a rock or something, you'll see damage to the rover itself. So having the extra compliance means that for Viper and future rovers, you'll be able to travel faster on their lunar.
Great. How was the separation of roles within your team decided, and what knowledge have you gained with your personal research?
I could take this one. So we separated our roles and tasks based on each person's expertise, which maximized our results as we worked on the tasks that aligned with our strength. So we started with the main objective of redesigning the Viper, and then we branched out from there. So we had someone create a VEX model to give us a reference of the rover's structure, and then others CAD'd and performed analyses using FEA, and then others did extensive research on other aspects of the rover. So for example, we looked at the temperature and the navigation for it. We also gained a lot of knowledge from our research, especially after consulting with some NASA engineers. We were even fortunate enough to speak with Parker Francis, an engineer who's working on the actual Viper, and this has deepened our understanding of what we needed to consider in our design, such as the conditions that we'd be dealing with.
Great. What was the biggest challenge in creating the scaled models?
I can take this one. So the biggest challenge when creating these scaled models, especially the VEX models, was finding information about how the suspension of the Viper worked and information on the actual wheel itself. This is because most of the information on the Viper rover isn't publicly available. We did schedule some meetings with Viper engineers, but because of the recent hurricane in Houston and a lot of deadlines, we weren't able to meet with them until the last day. So that was definitely a major challenge that we had when designing the scaled model.
How did your wheel design different from the current Viper model, and why did you choose to design it differently?
I can take this question. So similar to like what Ian said earlier, our wheel mainly differed basically by being compliant and also 3D printable. And we made it compliant because, as Ian said, it allows faster travel speed, it decreases the impact and increases traction. And 3D printability allows the wheel design to be sustainable when there's a 3D printer on the moon. And so the major reason for these changes is because, as Ian said earlier as well, the NASA wheels were meant to be slow and they only travel at a maximum speed of 0.5 miles per hour. This was due to limitations of cost, as well as when we were talking to Parker Francis, they were only able to use static force simulations due to limitations of their computing power, which also only allowed them to basically travel at a slow speed in their simulations. And although we were also only able to use static force loads because dynamic simulations would require too much computing power, I think our wheel design being compliant will allow it to perform better in dynamic situations when rolling over rocks at fast speeds.
Well, y'all have all done an excellent job. Congratulations to the Artemis Roads Viper team. Our next team presentation is from the Gravity Recovery and Climate Experiment, GRACE FO. The team is led by Chirag Patel and Chaeyang Zhang. They're both research associates at the University of Texas Center for Space Research. The GRACE FO team, with their research on where the water flows, weighing where the water flows. Please join me in welcoming this team.
Hi, everyone. My name is Mira Singhal. And I'm Bala Foley.
And I'm Om Sanin.
I'm Shannon Callahan.
I'm Dylan Kablayan.
And my name is Lucy O'Brien.
We are the GRACE follow-on team with the NASA SEAS internship. In our project, we utilize GRACE and GRACE follow-on data to track ice sheet and glacial melts in Greenland, West Antarctica, and East Antarctica, estimate these regions' contribution to sea level change, and project sea level change into the future. Launched in March of 2002, GRACE, or Gravity Recovery and Climate Experiment, was a satellite in collaboration with NASA and the German Space Agency. The GRACE mission is composed of two twin satellites, GRACE A and GRACE B, one following the other in a near circular polar orbit. GRACE has the ability to detect minuscule changes in Earth's gravitational field by tracking the inner satellite range with a precision of about 0.1 micrometers, equivalent to the distance change of about 1/110th the width of a human hair. GRACE was replaced with GRACE Follow-On, or GRACE FO, in 2018 with a nearly identical design. Our project utilizes GRACE and GRACE Follow-On's monthly gravity measurements, which are influenced by mass changes in water systems and geological events. Our primary objective was to use the GRACE Follow-On data to model ice mass loss in polar regions and the corresponding effects on sea level changes. This involved processing GRACE Follow-On's range acceleration data using Python and converting the gravity anomalies to equivalent water height and eventually to ice mass change.
So, to begin modeling ice sheet loss, sea level change, and projecting these processes into the future, we obtained laser range acceleration, or LRA, and K-band range acceleration, or KRA, data from GRACE and GRACE follow-on. LRA and KRA data allow us to graph gravity anomalies from the follow-on mission, as seen in the figures featured on this slide. This specific data factors out static gravity anomalies, which is the picture on the left, leaving what is referred to as temporal gravity, the minute variations in Earth's gravity that change frequently, and with which GRACE and GRACE follow-on are able to detect. From the LRA and KRA data, one can derive the equivalent water heights of any geographical region of the Earth, as shown on the slide. Equivalent water height essentially describes the change in mass in terms of the water thickness of the melted ice covering the whole region we are looking at. To derive equivalent water height, the LRA and KRA data is converted to gravitational potential. After this conversion, geological phenomena are removed, such as post-glacial rebound and crustal uplifting. Events such as these frequently cause changes in local gravity levels, but are not pertinent to our objective of understanding Earth's changing water distribution. In other words, removing these disruptions allow us to focus more effectively on changes in Earth's hydrosphere alone, compiling the equivalent water heights to be used in the next steps of our project. This conversion from range acceleration residuals to equivalent water thickness is beyond the scope of our project, so we worked directly with the equivalent water thickness data.
We decided to visualize the equivalent water height data in a heat map animation in order to better understand its changes over time. As shown, there are clear trends of decreasing water height around Greenland and West Antarctica, while East Antarctica showed trends of increasing water height. This was our motivation for selecting these regions and conducting further analysis. To calculate each region's change in mass, we employed a global grid division approach, dividing the Earth into cells measuring 0.25 degrees latitude by 0.25 degrees longitude. We then focused on the desired regions of Greenland, West Antarctica, and East Antarctica by masking each region. The primary challenge in this approach was accounting for Earth's spherical geometry. Cross-sections of the Earth are not rectangles, but are rather sectors of a circle when visualized in 2D. Consequently, grid cell areas vary with latitude, since equatorial grid cells are larger than polar cells. To address this, we calculated each grid cell's area using equations 1, which can then be simplified to equation 2 to get the mass change for each cell by multiplying its equivalent water height with the grid's area and the density of water. The total mass change for each region was obtained by summing these individual cell contributions, which effectively accounts for the latitudinal variation in grid cell size. To convert mass change to sea level rise contribution, we divided the total mass change by the global ocean surface area. This gives us each region's specific contribution to sea level rise over the study period. When we did so, we uncovered a few interesting observations on each of our selected regions.
In two of the regions we looked at, Greenland and West Antarctica, there was a significant annual decrease in mass, primarily surrounding coastal regions, and a corresponding contribution to the increasing global sea level on a consistent basis. This is reflected in the figures displayed here, where we see that the annual rate of mass change for Greenland is a decrease of about 236 gigatons per year, and for West Antarctica, a decrease of about 106 gigatons per year. It is also represented here, where we see that the annual contribution by Greenland to global sea level is about 0.64 millimeters per year and roughly 0.28 millimeters per year for West Antarctica. Notably, Greenland appears to contribute the most to a global change in sea level, and regardless of size, has lost the most mass over the period studied. There are a number of potential reasons for which we see this trend emerge. Among them, and most likely, are rising temperatures and ice calving. With regards to rising temperatures, a factor notoriously associated with climate change, this causes ice sheets and glaciers to melt, forming melt ponds that further increase melting speed, or in other words, create a feedback loop. From here, water seeps into the surrounding ice sheets, lubricating their bases and accelerating their movement into the ocean. The second mentioned region for which Greenland and West Antarctica may be experiencing the changes that they are is ice calving, or ice mass loss. This occurs when icebergs break off from glaciers and float into the ocean. This process is influenced by ice flow velocity, thickness, and ice shelf area. Of course, without a deeper analysis of these regions, we can only postulate as to which specific processes have caused the changes we have observed. This is true as well for East Antarctica, the third and final region we would like to discuss.
East Antarctica served somewhat as a surprise for our team. Contrary to what one might expect, we observed in East Antarctica that there was a net positive rate of mass change and a net negative contribution to global sea level. With regards to this pattern, it is important to recognize scale. For instance, the magnitude of the mass change and sea level rise in Greenland are nearly 700% greater, respectively, than those of East Antarctica. What's more, the size of the area covered by East Antarctica is considerably larger than that of either other region studied. Regardless, however, this pattern is notable, and as is the case for Greenland and West Antarctica, there is a reason for which such an anomaly may be presenting itself. Specifically, a consistent increase in the magnitude of precipitation received by the region due to global warming and changing atmospheric conditions may be coming into play. It is this complexity that led us to the final step in the research process, analyzing the extent to which these regional changes impact the Earth as a whole. For context, however, the image featured here depicts the size of a single gigaton of water relative to New York City.
The Earth is a delicate chemical, physical, and biological system. It possesses mountains, glaciers, a fluid core, and more. All of these complex features ultimately lead us to one important consideration. No change in Earth's function or resource distribution will be felt equally in all parts of the world. As we look over GRACE data and analyze the effects of climate change in global sea level change, it's important to note that said effects are not felt with uniformity across the world. This is due to several processes and anomalies such as crust deformation and shifts, as well as Earth's rotational axis. Because sea level rise is not distributed equally across the globe, we have to scale each region's contribution to sea rise. Here we can see a gradient fingerprint map for each region we studied, illustrating the consequent changes in water height as these regions discharge the mass in the form of ice and water. These maps depict the distribution of 1 millimeter of ice sheet melt from each respective region, distributed around the globe. As you can see by the hotter colors, equatorial and Pacific regions are disproportionately affected by sea level rise as compared to more polar regions. The animation on this slide shows sea level change projections based on current data collected from GRACE and GRACE follow-on. At the current projection, the sea level is estimated to rise by 75 to 100 millimeters, nearly around the globe, by 2100. It is important to note that these are only estimated contributions from Antarctica and Greenland and is not the whole picture. Other factors such as temperature, thermal expansion, and more also play significant roles in sea level change.
To conclude, West Antarctica and Greenland are experiencing large-scale mass loss of -236 and -106 gigatons per year. Even though a majority of our climate is losing ice mass, East Antarctica is experiencing a period of mass gain at approximately 35 gigatons per year. West Antarctica and Greenland are contributing to global sea level rise at rates of 0.64 and 0.28 millimeters per year, with Greenland contributing the most. Overall, global sea level decrease in polar regions and rises around equatorial regions are likely due to variations in gravity, crust deformations, and shifts in the Earth's rotational axes, contributing to the unequal distribution of sea level changes.
With these results presented, our team would like to take a moment to speak about our experiences with the SEAS program this year. Here, we include a few highlights and challenges of the internship on the whole for anyone interested in reading, but at this time, we would like to each share our own perspectives. To begin, I would just like to say that these past 14 days have offered me some of the most enriching research opportunities of my high school career and have exposed me to so many different and exciting perspectives and people that I would otherwise never have had the opportunity to explore. Thank you, and I will now pass the mic off to my fellow team member, Om.
Overall, these 2 weeks in SEAS have been great. Not only have they been an opportunity to work on our project, but they've also been an amazing learning experience. I've had the chance to collaborate with gifted students from around the US, meet renowned NASA employees, and also partake in other projects such as microgravity Z-cube research, which are all helpful to my future STEM career. I'll now open the mic for anyone else who wants to pitch in.
The past 2 weeks as a NASA STEM intern have been filled with so many opportunities that have given me amazing new insights into sides of STEM that I am less familiar with. I've always been interested in astronomy and astrophysics, and this passion remains. But through the GRACE project, I have been provided with a new perspective on global issues, which I strive to keep in account in my future studies. There were some challenges, mostly technical, such as getting rained on with the Z-cubes and navigating confusing data collection methods. I also learned so much about coding and data analysis with the help of my amazing teammates and mentors, which I will definitely be using in my future education and careers. The time flew by so quickly, and I'm going to miss everyone here, but it was an amazing experience. I'm so grateful to have had it.
Overall, I would say the SEAS program has reaffirmed my career ambitions. I still want to go into the STEM field, but with a differing path, specifically in combination with public policy. Focusing on addressing disparities associated with STEM education and ensuring the perpetuation of funding for vital agencies such as NASA and the Department of Education. This internship has given me so much insight into the absolute necessity of keeping funding for programs like this available. As I continue my path in public service, I plan to pursue both a political science and a degree in electrical engineering to gain both a technical and civic understanding in policies regarding STEM education/tech policy.
So like my teammates mentioned, SEAS was just such an incredible experience to meet students from around the country who are interested in learning about Earth and space science, math and physics, coding, and other really nerdy topics. SEAS has prompted me to really consider collaborative STEM research as a career choice because of the exposure that I've had working with so many dedicated and passionate students and mentors.
These past 2 weeks have felt like a fever dream to me. When I first heard that I was accepted into this program, I fully thought it was a prank, and 3 months later, I still do. Before coming into this program, I wanted to complete my associates, get a degree in economics, and maybe minor in environmental sciences. But now I want to pursue a degree in environmental engineering. Our mentors, Chirag and Shayong, were instrumental in every step of this process, from patiently explaining matrices and simple geometry to helping us troubleshoot our code. I could not thank my teammates and mentors enough for making this experience the way it was. Thank you all for a life-changing 2 weeks. Before we end, though, there are so many people that we'd like to acknowledge in helping make our project successful. Firstly, our mentors, Chirag and Shayong, then the NASA SEAS staff, especially Margaret and Selena Miller, then the UT Austin Center for Space Research for letting us use their facilities every single day, University of Texas at Austin for letting us sleep and eat there, and all the guest speakers and staff for their amazing presentations. Thank you all so much for listening. And if you have any questions, please raise your hands now.
So we do have several questions that have been posted on the Slido app. We invite all GRACE team members to please unmute and turn on your cameras. Why different instruments and data are used for LRA and KRA in your study?
So I'll take this one. So GRACE Follow-On is the second version of the GRACE satellite. Initially, the first iteration of the GRACE satellite only had the K-band ranging instrument, or the KRA. However, for the next GRACE mission, which is called GRACE Sea launching in 2028, they wanted to test out the effectiveness of the laser ranging instrument, which is why in GRACE Follow-On, they put that as a testing device to see if it works. And so far, we found that it's more accurate than the K-band ranging instrument, which is why the LRA will be the only instrument implemented in the next GRACE mission.
So why do GRACE and GRACE-FO use 2 satellites and not just one?
I can take this question. So the GRACE satellites are intended to measure very minute changes in the Earth's gravitational field. And so with 2 satellites, we're able to make a lot more precise measurements. And so that's why there are 2 instead of just 1.
do you have a potential explanation for the increased ice over East Antarctica?
I can also take this one. So our primary, when we studied East Antarctica, the primary reason we believed that we were seeing an increase in mass over that region was due to an increase in precipitation due to the just changing distribution of water around the globe.
And how would you use this experience in studying GRACE to convey climate change concerns to the public?
So I'll take this one. So the results of our presentation, again, was that we found that there was ice mass loss in many regions, and that there was also a rise in sea level in specific regions. So if we can use a combination of those two data and analyze them around specific areas in the world, and also correlate them to maybe high emissions in certain areas and lower emissions in other areas, we can show that higher emissions can lead to increased ice mass loss and sea level rise in specific areas around the world.
And why sea level drops near Greenland?
So I studied Greenland, so I'll also take this one. So I mean, when I initially studied Greenland, I thought there would be sea level rise during Greenland because of the ice mass loss. However, since mass is directly proportional to gravitational pull, when ice sheets melt, it actually reduces the gravitational pull on the surrounding ocean, and this causes water to redistribute away from the region. In addition, when you have heavier ice sheets melting, it results in a process we learned about called isostatic rebound, where the landmass beneath the ice sheets slowly rise back to its initial position, and this can lead to a drop in sea level.
Excellent job to the GRACE team. So thank you all for your research and your participation. So our next team presentation is from the High Altitude Ballooning Airship Project, led by Dr. Darcy Snowden, an associate professor of physics at Central Washington University. And the project assistant for this team was Sherelle Webb. So please welcome the High Altitude Ballooning Airship Project with their research on advanced lightweight prototype high altitude airship, designing and testing a model airship for long-term scientific observations on Titan.
Hello, everyone, and thank you all for taking the time to listen to our presentation. We are the 2024 High Altitude Airship Project.
My name is Bárbara Lebrija, and I'm from Monterrey, Mexico.
My name is Brandon Lowe, and I'm from Bellevue, Washington.
My name is Mairead Meany, and I'm from Wilmington, North Carolina.
My name is Kathy Martinez, and I'm from Mission, Texas.
My name is Anna Nguyen, and I'm from Sugar Land, Texas.
My name is Sanvi Pradhan, and I'm from Austin, Texas.
Hi, my name is Kat Tate, and I'm from San Antonio, Texas.
I'm Jacob Toomey, and I'm from Allendale, New Jersey.
We would also like to thank Dr. Snowden and Mrs. Webb for their contributions to our project.
Our objective was to design, build, and test an airship in order to demonstrate its suitability for an extended study of Titan's surface and atmosphere.
We selected Titan because it is one of few celestial bodies in the solar system that has a dense enough atmosphere for an airship to fly. Titan is also a very interesting moon to explore, as even despite its toxic nitrogenous atmosphere, methane clouds, rivers, and lakes, and its extreme cold, there is still potential for life forms that use methane as a liquid solvent instead of water. Life as we know it couldn't exist, but if we were to discover life, it would revolutionize the fields of biology and astronomy, showing the potential for different life forms from all across the solar system and galaxy.
As lighter-than-air vehicles, airships are the ideal platform for a long-term mission to Titan. They rely on aerostatic rather than aerodynamic forces, which minimizes fuel consumption. Additionally, airships offer a unique combination of low-speed, low-altitude flight, endurance, and maneuverability. Finally, airships are able to capture high-quality data while covering a large land area, enabling analysis of Titan's hydrologic cycle, methane sources, and possible origins.
Before constructing the airship, we calculated some of the forces that would be acting on it. We found that considering the weight of the balloon, the airship would have a carrying capacity of around 0.38 kilograms, assuming a perfectly spherical balloon. We also calculated the estimated drag, finding that there would be about half a Newton of force opposing the thrust from our motors.
Using the calculations from the previous slide, we determined that the total weight of our design had to be 0.516 kilograms, with the payload mass being less than 0.38 kilograms, and the minimum speed had to be 1.5 meters per second. The guidelines from our mentor and the program gave us 2 weeks to construct the design using a 0.368 meter radius balloon. With the criteria and constraints in mind, we moved into the sketching phase, where each team member sketched their own design for the airship. Some of the aspects we focused on were the shape of the gondola, the number of propellers, the propeller positions, and the method used to attach the gondola to the balloon. We then came together to compare designs and narrowed it down to 4 options.
Our first design idea relies on force components. 2 motors enable horizontal movement. When both are run, sideways forces cancel, enabling forwards motion. To turn, only 1 motor needs to be run. An additional motor on the bottom of the airship enables vertical motion.
Our second idea consisted of 8 motors, pointing left, right, forward, backward, and down. Increasing or decreasing the thrust of certain propellers would allow the airship to move in all directions without turning. This was a simpler and more traditional approach to airship design, by having 8 propellers and motors raised concerns about weight.
Our next idea was modeled after a quadcopter drone. This would utilize 4 DC motors in an attempt to replicate the flight dynamics of a drone to move the airship. The big advantage of this design is that it allows for strafing and horizontal movement without rotating the whole body. However, applying drone dynamics to a relatively large balloon platform would be a challenge given its greater inertia. Our final idea utilizes thrust vectoring. This is the most traditional approach to a gondola design out of the 4. 2 DC motors, each rotated by a positional servo, angle up and down and sideways to provide thrust. This approach would be the most simplistic because it is following traditional designs of a normal gondola. To decide which designs we should pursue, we created a decision matrix. Each design was graded based on a set of criteria, with the lower numbers as worst and the higher numbers as best. As you can see here, for attachment mechanisms, we decided on using a net instead of a rigid exoskeleton to attach our gondola to the balloon. This was largely because of the ease of doing so. For our gondola, we settled on the drone design as it was the most well-rounded and performed the best overall. And ultimately, we settled on our final design of a drone maneuvered by 4 DC motors, with the electronics placed in the center. The drone is 19 centimeters across and weighs about 29 grams once 3D printed.
For the electronic components, we chose to program an Adafruit featherboard and integrated a motor driver to control 4 DC motors. The motors were powered by 4 AA batteries, while a 3.7-volt lithium battery provided power to the featherboard itself. Attached to the featherboard was an SD card reader responsible for recording data from its onboard sensors, which included temperature, humidity, acceleration, and pressure to monitor environmental conditions. The featherboard operated wirelessly, enabling autonomous flight capabilities.
Using the previously shown diagram, we modeled the optimal placement of our electronics using fritzing. To conserve space and minimize weight in our final model, we positioned our motor driver above the featherboard, thus eliminating the need for a breadboard. Here on the left, you can see Barbara and myself soldering the heather pins to the featherboard to secure it into the driver during the testing process.
In terms of programming, we utilized an Adafruit featherboard that is equipped with the USB connector, charging port, and several different sensors. With the charging port, we were able to fly our airship wirelessly while using a battery, and with the USB connector, we were able to plug the board into a laptop and run code files from the CircuitPy drive we created. We ran and coded our programs in the CircuitPython environment called Mu, and from there, we were able to test the functions of our code, such as spinning the motors through the Bluefruit Connect app that contained a control pad, all of which was compatible with both our featherboard and CircuitPy. At first, we had some technical challenges connecting the board to our laptop and getting some of our programs to execute. But after we were able to troubleshoot those issues, we were able to implement several features on our airship, including movement and sensors. These sensors include an accelerometer, a gyro, which measures angular velocity, temperature, humidity, air pressure, altitude, proximity, sound, and more. As we tested our build in the air, all the different sensors collected data and stored it within a file within the SD card, which will be discussed in depth later.
After setting up the microcontroller, our main focus was coding the motors, done by utilizing CircuitPython and its MotorKit library. We were able to maneuver the airship vertically by switching the directions of the motors, which changed the airflow, causing the ship to push either up or down. However, our biggest challenge was changing the direction of the ship without causing it to drift upward as well, and integrating these quadcopter flight dynamics into a neutrally buoyant airship, a concept we couldn't find much past research on. After some experimentation, we accomplished this by referencing drone dynamics, running 2 adjacent motors at a high speed and running the other 2 at a low speed, causing the ship to move in the direction of the slower motors. Using the Bluefruit Connect app, we added a user interface to allow the ship to be maneuvered through a control pad. As you can see, the control pad included 4 directions, front, back, left, and right, and some additional controls such as stop, up and down, and 4 incremental settings for speed. One of the most important parts of the user interface is the 4th button, which allowed us to program when we wish to collect and store data. By clicking the button, a stream of data is stored to an SD card, including readings for temperature, pressure, sound, humidity, and acceleration, which can be later downloaded and analyzed. This was another one of the biggest challenges we faced throughout the project, determining an efficient way to collect data. After attempting to use an MQTT protocol, we eventually settled on the SD card due to its simplicity and efficiency.
We conducted several tests throughout our project as we made an increasing amount of process in terms of the code and design. Initially, we were able to test the motors at varying speeds ranging from 0 to 1, and we noticed that the motors created a significant amount of thrust able to easily lift their own weight. After we had received our 3D print, we were able to build our first prototype, which is pictured in the second image, where the 36-inch balloon filled with helium is oriented horizontally with the drone on the bottom center. We tried the net at first, but then decided against it as it added too much mass to the airship, making it too heavy to be neutrally buoyant, deciding to use masking tape and Velcro to secure the build to the balloon. In our most recent prototype, which is in the third image, we oriented the balloon the way it normally is and found success in securing the drone at the bottom with a string that was tied around the balloon. After deciding that that particular design was the best, we added little increments of mass to the airship to make it neutrally buoyant, which allowed us to continue testing and controlling the movement of the airship with the motors.
Although we had performed some rough calculations prior to the build, we recalculated a lot of these numbers after initial testing. Due to the diameter of the balloon being smaller than expected and its ellipsoid shape, the true calculations came out to be much smaller than expected. Our final carrying capacity ended up being roughly 0.269 kg, significantly less than our estimated 0.38 kg.
Measurements made by the accelerometer show the airship's directional acceleration in 3D space. This data is useful to show both where the airship is going, as well as being used to calculate wind speeds on Titan.
Adding to that data, we were also able to collect data on the surrounding pressure and humidity over time and convert that to line graphs. Understanding these atmospheric conditions helps us understand the airship's flight for stable operation. And for landing on Titan, this data is crucial to navigate its dense atmosphere and ensure that we have a safe descent.
Throughout the course of this project, our team had to handle many challenges. Firstly, the initial calculations we made for lift force and terminal velocity weren't accurate because of the assumptions and estimations we made. This made it more difficult to make the airship neutrally buoyant. Secondly, the balloons were difficult to work with because they were delicate and would deflate by the end of each day. Finally, we had limited time since we only had 2 weeks in person and resources such as helium and 3D printed items were limited. If given unlimited materials, there are some improvements we would make to our design. We would include additional sensors and capabilities such as a camera, mapping capabilities, or a UV sensor. We would make sure to use precise measurements and calculations so we could know exactly what constraints we were working with. And if this were an actual mission to Titan, we would also include a shield to protect the electronics from Titan's harsh conditions, and we would deploy multiple airships for fault tolerance and increased data collection.
On behalf of the team, NASA STEM has been incredibly impactful in not only providing the opportunity to engage in high-level research, but also the importance of perseverance. This experience has not only deepened my curiosity for science, but the trips along the way significantly improved the team's collaboration and created a positive environment, which reflects on the quality and outcome of our work today. We give the deepest thanks to not only our mentors, but everyone behind the scenes that made this program possible.
Previously, I wanted to major in mechanical engineering, but this program has allowed me to explore a new career path, and I now plan to major in aerospace engineering.
I'm an aspiring aerospace engineering major, and this program has allowed me to learn about the NASA Pathways internship, which is a possibility for me in the future.
Working on the electronics portion of this project solidified my passion for engineering and made me capable of becoming an electrical engineer in the future.
I'm an aspiring aerospace or mechanical engineer major, and this program allowed me to gain experience with CAD and engineering design, both of which will be useful for me in the future.
I'm an aspiring electrical engineer or computer scientist, and this internship has allowed me to gain experience with programming and hardware, which will be useful to me in the future.
Participating in NASA SEAS gave me hands-on engineering experience, which I hope to later apply in the future as an electrical engineering major.
Through SEAS, I became more certain of my plans to become an aerospace engineer for NASA.
I'm an aspiring computer science and economics major, and through SEAS I learned that even though I don't want to be an engineer, there's still a place at NASA for people of all different skill sets.
Lastly, we again wanted to conclude by saying thank you to NASA SEAS for giving all of us this opportunity. Additionally, thank you to our team mentors, Dr. Darcy Snowden and Ms. Sherelle Webb, for their support and guidance, which made our project a great learning experience. This internship was an amazing experience, and our favorite part of this amazing experience was getting to visit the Space Center in Houston and getting inspired by the great features achieved there.
Excellent job. So I invite all team members on the high altitude ballooning airship project to unmute their mics and turn on their cameras. The first question to the group is, how did you ensure the propellers wouldn't damage the balloon? Is the airship team unmuted?
Yeah, so we messed around a lot with the different sizes of propellers when we were kind of CADing and 3D modeling our design in Fusion 360. And another thing that kind of affected it was the size of the motors and which propellers could fit with the different motors. But we went through a lot of revisions and sketches and models prior to actually designing the airship. And so kind of going through that with our whole team and discussing it really helped us have a vision and an idea set in place before we actually started building.
And for other team members, have you considered what material changes would be necessary for an airship on Titan?
Yeah, so for the actual airship itself, for the mock-up, we 3D printed it out of POA, and that was just like the fastest way we could get a prototype. But for the actual airship on Titan, we feel like a stronger material such as aluminum or titanium would be more appropriate for the harsher atmosphere. And then similar for the balloon would need to be much stronger, and that would probably be out of some synthetic material or something of that sort.
How did previous missions to Titan influence your project?
So I would actually like to answer this one. Previous missions on Titan focused on utilizing probes, landers, and drones and other sources of satellites to capture data, which assisted us on how we wanted to conduct not only what data we wanted to collect, but also the device that we decided, which was an airship. A good example of a mission that we reviewed very well was the Cassini Hudgens, which performed numerous Titan flybys. But because it was a flyby, it lacked the capacity for extended observation. So a permanently stationed airship would actually help with the long-term analysis of Titan. So that and a few more were very helpful in how we wanted to conduct our research. Thank you.
And do you think the color of the balloon would affect the equipment movement?
So I would actually also like to answer this one. Previous research on previous airships had used black balloons, which would ended up getting overheated and pop after only descending about 20 feet or so. So we knew that this was not that color specifically was something that we wanted to avoid. So most of our testing prototypes use white and red balloons, which would gave the ability to handle hotter temperatures. Thank you.
And how would autonomous systems be implemented for the real airship on Titan?
Yeah, so when we did past research on previous airships, we looked a lot at the different features that they implemented. And one thing they really kind of emphasized was that they could learn and diagnose mission failures. So they can kind of
diagnose a failure and then replan their flight or the data they need to collect using autonomous systems. And this was something we didn't really have time to implement because we were using obviously like cheaper electronics, and we kind of controlled our airship through a control pad just operated through our phone. However, if we were doing a mission to another planet, we would look into programming the airship so that it could control itself and use its sensors and the environment around it to diagnose where it needs to go and the data it needs to collect, and in case there are any mission failures, what it needs to do to recover from certain failures.
And what are the benefits of a balloon platform versus a regular drone design?
Balloons can stay in the air a lot longer and observe things because they're neutrally buoyant. So even after, if a battery were to die, the balloon can still make observations through, because we had batteries separately controlling the motors and the sensors. So the sensors could still collect data even if something were to happen to the main drone body, because that balloon can stay in the air for a long time.
Great. Well, you did an excellent job with your research. We will be taking about a 20-minute break. We encourage you to watch highlights on the student accomplishments during the Earth and Space Science course. Our thanks to Asha Carmacher for scoring and preparing these highlights. We will reconvene at 12:50 with session 2 of the SEAS Science Symposium. So we'd like to welcome everyone back for session 2 of the SEAS Science Symposium. Our next presentation is from the Human Exploration Research Analog Team, led by Patrick Petty, a mission support specialist at NASA's Johnson Space Center, where he oversees the design, implementation, and execution of HERA activities, and also thanks to his project assistant, Becky Fritchie. Please join me in welcoming the HERA team with their presentation, Humble, Humans Undergoing Medical and Behavioral Life Experiments.
Good afternoon, and thank you for tuning into our symposium today. The NASA SEAS 2024 HERA team is proud to present to you our new suite of experiments, Humble, or Humans Undergoing Medical and Behavioral Life Experiments. Now to meet the team.
Hi, my name is Evelyn Bahina, and I'm from Fayetteville, Arkansas.
My name is Grace Bittlingmeyer, and I'm from Wheaton, Illinois.
My name is Caleb Bocanegra, and I'm from Hanover, Maryland.
My name is Tyler Clark, and I'm from Beverly Hills, Michigan.
My name is Brian Jarman Dunlop, and I'm from Queens, New York.
My name is Gigi Gordon, and I'm from Bethesda, Maryland.
My name is Kennedy Hall, and I'm from Fort Wayne, Indiana.
My name is Joseph Mujica, and I'm from Far, Texas.
Golden leaves in our patch are assembled to appear like a Grecian crown to represent the Greek goddess Hera. The leaves are also aligned into 24 rows for the year of 2024. We put the constellation of Aquarius because Hera is the guardian of Aquarius, and it has 8 total stars that represents each team member. The moon symbolizes the Artemis 5 mission to return to the moon, and the DNA symbolizes the human research we're conducting. Each different color in the DNA strand is associated with the team member.
Space travel is a puzzle harder than humankind has ever had to figure out, and the Artemis program is the most ambitious endeavor NASA has ever imagined. To accomplish Artemis's goal of reaching Mars, many problems must be overcome. Our suite of experiments follow the 5 elements of NASA's Human Research Program, otherwise known as HRP. These elements combat the various hazards of spaceflight to humans, otherwise known as RIDGE. RIDGE includes radiation, isolation, distance from Earth, gravity fields, and hostile environments. We've designed Humble to primarily mitigate the hazards we deem the highest magnitude for long-term missions to Mars. We split Humble into 2 experiments, Humble 1 and Humble 2. Humble is to be carried out during Artemis 5 before we take the leap to Mars. Humble 1 focuses on stress responses, while Humble 2 is centered on mitigating space radiation and testing particle accelerator function in space. The 2 experiments are very different, but align in protecting humans in space while promoting humans' goal of reaching Mars.
Humble 1 will be focusing on astronauts that will be exposed to high-stress scenarios, where the only choice is a fight-or-flight response. This experiment will be tested on the subject 3 times, which will be before astronaut training, after astronaut training, and after the first spaceflight of that astronaut. This experiment will be focusing on whether the repeated exposure results in the desensitization and/or adaptation to adrenaline. With this result, we will try to understand whether their training worked and to what extent it worked. Finally, the last question is, what simulants elicit different responses?
This experiment will be carried out by testing epinephrine and cortisol levels through blood and urine samples, blood pressure, heart rate, and blood oxygen levels before and after exposing astronauts to adrenaline-inducing scenarios, such as roller coasters and VR simulations based on lunar missions with different anomalies and conflicts presented, to determine what stimulants elicit different responses in each person. These tests will be completed before candidates are trained, after they're trained, and after spaceflight to compare and analyze any adaptational differences in the results.
Astronauts will be completing a series of surveys once every week for researchers to analyze their behavioral changes and adaptations to stress-inducing scenarios throughout the duration of their mission. These surveys will be completed after a major event or conflict that they were exposed to while in spaceflight. These questions will vary from, do you think your team was prepared for such an event? How did you feel some team members handled such an event? And how prepared did you feel for such an event? Surveys will be completed anonymously in order to receive honest feedback from each crew member. This allows for crew members to analyze their own reactions as well as those of their crewmates to address issues and increase the succession of the mission.
Humble 1 would help us to better understand how astronauts will adapt under the prolonged spaceflight conditions of future missions, both mentally and physically. This also allows for better preparation and less risks involved to ensure mission success and completion.
Humble 2 is the second study within our suite. This study will focus on space radiation mitigation by testing the effectiveness of 3 different materials in blocking radiation waves. The experiment will test 6 separate skin cell samples from the same astronaut, each exposed to radiation in a different manner. One sample will be exposed to no radiation and will act as a control. One will be in space surrounded by water, one will be in space surrounded by liquid hydrogen, and one will be in space with no radiation protection. All of those samples will be on the Gateway space station, which will be orbiting the moon. There will also be 2 samples enclosed in particle accelerators, one in space and one on the ground at Brookhaven National Laboratory. The radiation levels of each sample will be measured daily, and the experiment will be repeated for each astronaut on the mission.
The samples will be shaved biopsies, 6 from each astronaut, likely from the arm or leg. They will be stored with cryopreservation so they may last longer and be tested longitudinally. Once collected, they must be put in similar environments for testing in order to maintain minimal variability. The chosen container that each skin cell sample is to be inserted in is a carbon fiber shell with a diameter of 30 centimeters. All 6 samples will be stored in this manner, and 2 of them will contain no outer shield, such that there is a control unexposed to radiation, or in other words, left on Earth, and a control with no extra blockage from radiation on Gateway. For 2 of the tested samples, a 30 centimeter diameter cyclotron will be affixed to the diameter of that inner sphere. One of these will be set up at Gateway and one at Brookhaven National Laboratory. This way, it can be measured if there's a difference in functionality of particle accelerator in space and still test the extent to which it blocks radiation in both places. For the 2 liquid samples, the small shell will be placed into an outer shell, which is 45 centimeters in diameter and also of carbon fiber. The gap between these 2 shells will be fully filled with the desired liquid, either hydrogen or water. It's been determined by prior experiments that the ideal thickness for a shield should be 7 centimeters, so this is achieved by having a difference in diameter of 15 centimeters.
When conducting our experiment, the accelerator on the ground will be used to conduct the same experiment to be more reliable, as the one in space has not been tried as the physics are altered. The skin cells will be collected from each of the 4 astronauts. Some will be preserved to be positioned on the ground, and the others will be launched into space. The different states will be compared and analyzed to show the difference in radiation it was exposed to and the effects that each sample went through. The Gateway and the future Artemis missions will generate about 45 kilowatts of energy from the sun daily. 1.5 kilowatts will be allocated to the cyclotron accelerator daily to keep it constantly generating and to keep it stabilized. We will have a Geiger count, an instrument meant to measure radiation on the Gateway to check the radiation exposure to the cells daily, giving us the necessary data for this study.
Humble 2 investigates radiation mitigation, which will be ever more important as we venture beyond the moon towards Mars on our long-term missions. Humble 2 tests multiple possible mitigation methods, meaning there are multiple possible routes to success, increasing our chances of finding an efficient mitigator. By working to protect from radiation, Humble 2 ensures the health of astronauts as well as the efficiency of mission objectives, as a healthy crew is the most effective one. Further, by testing particle accelerators in space, Humble 2 investigates possible differences in operation compared to on Earth. By comparing these differences, it is possible we could better utilize particle accelerators in space for their many uses on Earth, such as cancer treatment, plant and crop biology, and in strengthening materials. Overall, Humble 2 is crucial as it addresses the factor of radiation, one which will be exponentially worse the further we go from Earth.
Both studies adhere to the following principles. 1. Social and clinical value. Each research question must justify and convince participants. For Humble 1, There's significance to testing how the Artemis 5 astronauts' mission reacts to stressful flight or fight scenarios. Our study could lead to a helpful addition to the space training depending on our results. For Humble 2, the longevity of spaceflight and the mitigation of space radiation are aspects worth investing in. 2. Scientific validity. We must check all boxes on the study's procedures. Both Humble 1 and 2 ensure that participants are equipped with clear methods and are aware of reliable practices. 3. Fair subject selection. For any research, our pool of participants is an important aspect. Each study considered certain factors such as age, sex, health status, and occupation. 4. Favorable risk-benefit ratio. The biggest concern is having our participants in pain or discomfort. Risk can be physical, psychological, economic, or social. For Humble 1, we aim to minimize the physical and psychological risk. For Humble 2, there's minimal radiation exposure. Overall, we want to get the most out of the study while maintaining our participants' safety. 5. Independent review. A superior and neutral board will review and monitor the study. 6. Informed consent. Participants are informed, completely understand, and are willing to participate in the study. 7. Respect for potential and enrolled subject. The participants will be treated with respect throughout the study.
Both Humble 1 and 2 will open opportunities for future research and experiments to be conducted. Humble 1 will serve as a guide for astronaut training by adjusting the conditioning astronauts must go through for better preparations for unexpected and stressful scenarios. NASA and other space companies will also be able to gauge a better understanding of the requirements for astronauts in the future, such as performance under stress. This will be done using the provided understanding of adrenaline in space from Humble 1. Humble 2 opens opportunities for future research in multiple areas. If water is effective, it will open a path to start harvesting ice from the Artemis 4 landing site. If liquid hydrogen is effective, it can also be recycled and used as rocket fuel, effectively turning the gateway into a refueling station. The particle accelerator will lead to the most innovation as it creates possibilities for many future experiments to explore its uses and impacts.
We have had a great time together throughout our SEAS experience. SEAS has been a valuable experience, including going to Fiesta, Texas, High Flight, visiting the HERA site at Johnson Space Center, and, of course, the most funnest of all, playing games together during our free time. We have even met an astronaut called Dan Tani, who was the first ever astronaut that I have personally met. SEAS has been a very valuable experience for us as a team where we have mastered several skills, including communication, time management, and problem solving. These skills will help us succeed in our future careers.
People that our team would like to recognize have helped us in many different ways to make the experience as a NASA STEM intern amazing. They each have been amazing resources that aided us in creating our project. Firstly, our mentor for this project, Patrick Petty, a mission support specialist, guided us in our research and understanding of HERA and its importance. He truly supported our eagerness to learn and gave us amazing opportunities during this program. Andre Stewart is an Orion spacecraft navigator and analog astronaut that took his time to talk with us about his experience participating in human analogs such as HERA. We would also like to thank our assistant mentor, space educator Becky Fritchie, supporting our ideas and eagerness to reach great heights, ultimately bringing our team together to complete this project. We also had help from Phyllis Friello, an Exploration Medical Integrated Product team member at the Johnson Space Center, who gave us insight on logistics for our project and guided our experimental perspective. Special thanks to Margaret Baggio and Selena Miller, who helped make this amazing program possible and created an environment for students to learn about NASA's opportunities.
We as the HERA team would like to take this time to thank you once again for your attention today. And if you have any questions or comments about our presentation, please leave them below in the chat and we will answer as many as we can in the next 5 minutes. Have a wonderful rest of your day.
Good job, HERA team. We do have several questions, so please turn on your cameras and unmute your mics. The first question is, if given the opportunity, would you be willing to sign up for a human analog mission?
I think the group consensus has been yes. For me personally, originally that might not have been my answer, but as we said, we did get to meet with an analog astronaut, Mr. Stewart, and also getting to tour the HERA habitat, I think changed my own personal opinion in just seeing Mr. Stewart's enthusiasm about what he did and also just learning about the importance of those kinds of experiments and missions.
The next question for your team is, what were some of the biggest challenges you faced?
So at least for the group of us working on the Humble 2 experiment, one of our biggest challenges was fitting in like ways for radiation mitigation because we knew we wanted to help solve that problem, but it's like a really difficult problem to solve. And it's only like exponentially worse the farther you go. Like when we talked to the Artemis flight director, Zebulon Scoville, he said it's just like a risk people have to accept that they have like a higher cancer risk. So that was like something that was hard for us to figure out. And then also, when we originally thought of using a particle accelerator, um, the main problem was like fitting it in and like figuring out the logistics of that. And then eventually we decided to expand it and have like multiple mitigation methods. So really just thinking about expanding our experiment. And the logistics of everything would be the main challenges for at least Humble 2.
And I could jump in for Humble 1. So for our research, we used a portal that searched all of NASA's HRP studies, and there were over 36,000 studies. And one of the priorities we needed to maintain was we need something new. So within 36,000 studies, how could we find something new? And if we can't find something new, how could we add on to a previous study? So for our group, that was our biggest struggle, in which, okay, some groups might have analyzed stress. Well, how can we add on to that? And that's why we added the VR component and the roller coaster component.
Excellent. You toured the HERA habitat. Was there anything that surprised you during your tour?
I guess I'll take this one. I feel like something that I don't know if anyone wants to add anything after, but for me, what surprised me was kind of like the size. Like it was bigger than I imagined. Like it had multiple floors. And for something that was like inside of a building and was like analog to a space environment, it was larger and like more spacious than I imagined. I mean, it's not large, but it was spacious enough to like maybe have some semblance of privacy if you're away from everyone else.
I could also add on, when you entered the building, firstly, it's kind of separated from everything else. We needed a card to enter. And when you enter the building, you see like there's insulation around all of the walls. And that was pretty interesting to see. I'm like, okay, we are in a research building for sure. They're definitely like conducting proper research with the insulation around the walls. And we got to go onto like the HERA, I guess you could say, station of where they have the astronauts be in a simulation for around the year to simulate Mars. And in itself, you could see how they like how they do like research activities, and also yeah, just research activities in general.
The last thing I'll add on to Brian and Tyler's, if I may, is it was really crazy to see, in contrast to the other analog missions that NASA does, like in Hawaii and the submarine missions in Antarctica, how those are all so separated. It's incredible the feeling of separation that they could still get. Meanwhile, there's the rest of the crew within the building monitoring them, and they're like 50 feet away. Yet when you went inside both the main HERA hab and the rover, they still created a great like faux isolation almost. And it was really incredible to see how real that could feel while you're still, 5 minutes away from everybody or a 2-second walk from the people monitoring you.
So in just a brief statement, what do you think is the most science that you could learn from the HERA mission?
I could take this one. Oh.
Go ahead,
You
Grace.
can go, Grace. I can go
Okay.
after.
Yeah, so like we said, there were the 5 elements of the HRP, and I don't think there's any one science that's more important than the other. Of course, in Humble 1 and 2, we split it up into a mostly like mental health perspective of things and then the radiation perspective. So I don't think there's any one most scientific thing to learn, but just those main categories. But of course, like we said, the keeping astronauts in a great mental capacity for the entirety of the mission is always important, and we should always be researching that further. And then, of course, the radiation to prevent that increased rate of cancer in astronauts.
Well, congratulations on a job well done. Our next presentation is from the Texas Atmospheric and Space Research TASR team, led by Melissa Poore, an educational leader among the TWIGs, working with the TWIGs Space Lab, NASA's Space Communications and Navigation Group, CASE's ISS National Lab, and Space Center Houston crew. Bob Twiggs, an astronomical engineering professor who developed curriculum for students interested in small space experiments and helped develop the original concepts for CricketSat, CanSat, CubeSat, and the Pocket Cube. And Nick Pugh, who developed the first microwave loop in the Gulf of Mexico and led telecommunications technology in and around the Gulf of Mexico, leading to a regional economic development. Please welcome the TASR team.
Hello, and welcome to the 2024 STEM Symposium. On behalf of the Texas Atmospheric and Space Research Team, I want to extend our most heartfelt appreciation for your attendance while we present our research and experimentation. Let's begin.
Hi, I'm Misha Patia, and I'm from New Jersey.
My name is Imelda, and I am from Seattle.
Hi, I'm Annika Lindhorst from Seattle, Washington.
Hi, I'm Micah, and I'm from Montana.
Hello, my name is Ken Felder, and I am from Idaho.
Hi, I'm Rania Marrero Alatar, and I'm from Puerto Rico.
Hi, I'm Sadie Lemmer, and I'm from Miami, Florida.
Hi, my name is Raya Wadwa, and I am from Houston, Texas.
Hi, my name is Emma Tian, and I'm from Houston, Texas.
Hi, my name is Ella Walty, and I am from San Francisco, California.
We also had wonderful mentors, including Melissa Poore, Bob Twiggs, and Nick Pugh, who helped us along every step of the way. Melissa is a passionate educator with over 25 years of teaching experience and has led 3 student satellite missions to space. Professor Twiggs co-developed the CubeSat and contributed to educational designs like the CricketSat and Pocket Cube. Nick collaborates with Professor Twiggs on SlimSat development, and he partners with the University of Louisiana.
Our research topic focused on establishing meteorological relationships by using data collected from remote sensing and discovering new ways to utilize remote sensing.
Our group was interested in analyzing environmental and changing atmospheric conditions. Our team collected meteorological data remotely via a SlimSat payload. The payload is equipped to gather comprehensive data including altitude, humidity, temperature, pressure, voltage, and GPS data. The data we collected enables us to predict patterns and understand the effects of environmental factors. SlimSats are data collectors that enable vast research and exploration opportunities. Remote sensing paves the way for new space applications, grants accessibility of space research to the public, and is an affordable and efficient method of collecting data across the globe.
Altitude ballooning is important because it allows for the collection of atmospheric data at various altitudes using balloons equipped with scientific instruments. These balloons can reach heights of up to 40 kilometers, providing a unique vantage point for studying the atmosphere. This method is more cost-effective and flexible compared to other approaches, making it ideal for targeted high-resolution atmospheric studies. The data collected can significantly improve the weather prediction models and enhance our understanding of climate change, leading to better informed decisions and policies.
And now for our logistics.
Before we launched our main mission and balloon, we did a variety of skill preparation. Before arriving in person to Austin, we had several virtual team meetings where we discussed logistics about the project and were given presentations about space concepts like orbits, satellites, and telescopes. Once arriving, we practiced soldering techniques with a jiggy board, which is a mini practice circuit board made by Bob Twiggs, our mentor, which allowed us to gain familiarity with manipulating components in circuit boards like resistors, batteries, motors, etc., and understanding how they work in conjunction.
We practiced data collection with TinkerSats. This allowed us to gain a better understanding of how sensors are implemented into circuit boards along with the other components to collect the data and easily analyze it on a computer. Electronic components on this payload include the Chow microprocessor, the BME 280 which measures humidity, and the 3-axis accelerometer which allows us to measure the direction of movement. This was an important stepping stone towards our understanding and use of the SlimSat.
The main component of our payload was a SlimSat, which is currently in development by our mentors as a cheaper and more accessible version of Bob's previous design, the CubeSat. On the slide is the hardware block diagram for the SlimSat showing how each component is connected on a circuit board. The main components consist of the UHF radio, which is the communication hub that allows us to connect with the satellite, a JAO, which acts like the brain of the satellite, and SGP-30, BMP-180, BME-680, which allows us to collect data on tons of atmospheric variables.
On the software side of things, our team utilized Adafruit. Adafruit is a platform that projects sensor data, presents maps of both the balloon and the chase team, and displays the graphs of the data given by the weather balloon. These three aspects were critical to our team in terms of communication and data analysis. The graphs transmitted from Adafruit allowed us to draw relationships that support our research topic in conjunction with maps presented on the platform, which allowed me to communicate with the chase team regarding the location of the balloon and its proximity to the SlimSat payload.
After learning about various concepts and the capabilities of our software and hardware technology, we developed a set procedure for the different stages of our high-altitude balloon launches. Here is a brief overview of our procedure. During the pre-launch, we focused on setting up communication networks and technology, prepared the balloon, and attached the payload. During the launch, we were constantly tracking our balloon and monitoring the live feed data. And after our launch, we reflected on our procedure and compiled the data we collected.
For the setup, we used a weather balloon, SlimSat, payload housing, helium, fishing wire, a scientific scale, scissors, and a Sharpie. For the launch, we used communication devices, laptops, and Zoom. For operation, we used Adafruit, a Yagi antenna, path prediction, and Zoom. And for the chase, we used a net, notebooks, Zoom, antenna, and hats or sunglasses.
Now we will detail the varying team roles essential for the successful execution of this project.
My role as team lead consisted of many responsibilities, but the most emphasized portion of my role was communication. During the launch, I had to communicate with all of the sub-teams of my group to ensure that everything went as planned and that we were all in the loop. To simulate radio talk, our team used Zoom and said over when we were finished speaking. Although the rule of saying over was a bit redundant and silly, it ensured that all of our comments were acknowledged, which contributed to a successful launch and payload retrieval.
So for weather surveillance during each of our launch days, whether tethered or untethered, I was in charge of continuously checking and updating the team on changes in wind, gusts, and wind direction based on information from the Weather Channel. This information enabled the team manager and the team to determine if we were able to continue to follow our procedures and launch the balloon.
The balloon management team played a crucial role in preparing the balloon for launch. Imelda and I filled the balloon with the necessary amount of helium to achieve the desired lift for the mission. Additionally, Annika and Caden securely attached the payload, which included a camera module, TinkerSat, and Arduino, ensuring everything was properly secured for a successful launch. During our tethered launch, we managed the balloon, making sure that it didn't get stuck or fall to the ground. During the untethered launch, our team was also responsible for launching the balloon.
We received signal from the balloon using a 70-centimeter Yagi antenna that we set up in different locations, including the parking lot and the Center for Space Research roof to collect data. To track the payload with the antenna, we used information on altitude and direction of the balloon given by the tracking team to make directional adjustments. We did this until we lost the signal, which was announced to the team.
Tracking team, we create predicted flight paths based on known information like coordinates, launch time, burst altitude, and information we're assuming, like ascent rate and descent rate, using a platform called StratoFlight, which considers the wind patterns for that specific day and time.
However, this pre-launch predicted path isn't completely accurate since we are assuming ascent and descent rate. Thus, when the balloon launched, we manually calculated the ascent rate along with updating the location and altitude to generate more accurate predictions. Simultaneously, we tracked the balloon using both AirTags and an Adafruit GPS. Our tracking was then communicated with both the chase team, who tried to arrive to the predicted landing site, and the receiving team, who needed the location to adjust the antenna and point it to the balloon.
Tracking team, we create predicted flight paths based on known information like coordinates, launch time, burst altitude, and information we're assuming, like ascent rate and descent rate, using a platform called Stratoflight, which considers the wind patterns for that specific day and time.
As the chase team, our main mission was to track and retrieve our payload by receiving information from ground tracking and redirecting where to drive as our flight path changed. Throughout our different steps, we utilized the Yagi antenna with the help of Chris in order to receive information and data from our payload and determine general location.
We documented cloud cover and weather conditions, serving as indicators of altitude and potential variations throughout the flight. This information was vital for accurate data interpretation post-trial. Using my phone, I recorded the entire retrieval process, capturing valuable footage and observations for later analysis. We safely retrieved the payload and were able to gather data crucial to our research topic. We were able to share our project with Miss Karen Quinlan, a local resident whose backyard we found our payload in.
Now, let's delve into the critical insights and outcomes from each of our high-altitude balloon trials.
For our first flight, which was tethered, our main goal was to get hands-on experience in the roles we had chosen prior to our untethered launch day. As you can see from the slide, the weather was quite optimal, with high levels of visibility and no extreme wind conditions. For this trial, we attached 2 TinkerSats and a camera module as the balloon's payload. The mass of our payload ended up equaling 190 grams, and so we had to fill up our balloon with a ton of helium until it reached a lift of 225 grams. So in reflection, our first trial showed us how easily it is to feel overwhelmed when you are not sufficiently prepared, and the importance of really feeling solid in your position in the team. Overall, our main takeaways consisted of remeasuring the 30-foot increments for accuracy so we know exactly how far away the balloon is, taking accountability for decisions and helping others when you feel it is needed, while also ensuring you are doing your assigned role for the team first and foremost, and making sure to record and document everything, since it is beyond important for looking back on what could have gone better in the process and to be used for this very presentation.
Our second trial was a tethered flight and payload cutdown that we conducted on July 12th. The main goals of this trial were to practice cutdown procedures and collect data mid-air using a SlimSat. The trial took place from 2 to 3:15 p.m. in challenging conditions. It was 91 degrees, cloudy, stormy, and humid, with winds from the south to southeast at 9 miles per hour and gusts up to 15 miles per hour. For this trial, we attached a 165-gram SlimSat payload to balloons, which provided a total lift of 280 grams. After our second trial, we were able to collect and analyze our data. We compared the relationship between altitude and temperature, noticing that as altitude increases, temperature decreases. We also examined the relationship between humidity and altitude, noticing that humidity increased as altitude increased. This was a very successful test, since we were able to use remote sensing to confirm these known relationships.
Reflecting on the process, it was crucial to have a room with Wi-Fi for the manager and to use Zoom for communication between groups. Each team member was also advised to use earbuds or wireless headphones to stay connected via Zoom. Following Rhea's instructions were essential, especially for launch timing and the cut-down procedure.
Our third and final trial was an untethered flight that we conducted on July 16th. The main goals of this trial were to track the balloon using Stratoflight, Adafruit, an Apple AirTag, and the Yagi antenna. We also wanted to collect relevant data to support our research topic, carry out a cut-down procedure, and efficiently locate the payload. The payload remained in the air from 3:06 p.m. to 3:20 p.m. We were fortunate to have ideal conditions as the temperature was 93 degrees, the humidity was roughly 51%. There were 10-mile-an-hour winds from the south with 17-mile-an-hour gusts, and the skies were fairly clear with some minor cumulus clouds around the launch site.
For this trial, we attached a 220-gram SlimSat payload on 2 balloons, which provided a total lift of 260 grams.
Through the data that we collected on the high-altitude weather balloon, we were able to measure temperature, humidity, and air pressure and see their relationships with volatile data. Furthermore, from this research, we were able to see the necessity and benefit of having different modes of data collection through our high-altitude balloon. Although it is possible to simply look up these relationships, our high-altitude balloon allowed us to understand the dynamics of the sky from a different perspective, one beyond what we could see with the naked eye. From the data, we saw that both humidity and temperature and air pressure and altitude had inverse relationships, meaning that as one went up, the other one went down. We predicted that our balloon reached heights upwards of 5,000 feet, but our payload was cut down before the sensor was able to capture this. The max altitude, as read on the sensor, was approximately 490 meters, equivalent to 1,600 feet. At the highest altitude, we also noticed the lowest air pressure at 101,133 pascals. Similarly, when we reached our highest temperature of 109 degrees Fahrenheit, we also recorded our lowest humidity level at 17.1%. These results are reflected in the graphs.
Launch, the team generated a predicted flight path as shown in the image on the left, with a predicted landing site to be 2.4 kilometers away. This path was generated with the assumption of the balloon having a 5 meter per second ascent rate and a 10 meter per second descent rate, but we did the calculation with a 500 meter launch altitude, which was inaccurate and significantly affected the accuracy of our prediction. Then, as the balloon launched, we began to calculate the actual ascent rate. However, as previously mentioned, the altitude sensor readings became constant. Thus, we approximated the ascent rate to be 1 meter per second, creating the path shown on the right. However, this path was also not applicable, since the reason we were receiving constant altitude readings was that the payload string attaching it to the balloon got cut early, meaning our package fell to the ground. Our first takeaway from this is that during the flight, the GPS on the Adafruit was not working, so we had to rely mostly on the AirTag GPS, but both of these GPS took a while to update. The actual flight path, the Adafruit and AirTag GPS started working towards the end, and the location became constant, where the balloon appeared to have landed in Miss Karen Kinland's backyard, 0.6 miles away, as shown in these 3 figures. The chase team utilized data of the strength of the signal between the payload tracker and the Yagi antenna to find the payload on the ground. Our second takeaway is that the flight path was compromised since our weighing of the balloon and payload mass was inaccurate and it affected the lift and thus flight path. Our third takeaway is that our predicted flight path was also compromised due to the friction within the payload that caused the string to cut early and the payload to fall to the ground.
In addition to the official 3 trials, we conducted a 4th tethered trial with only a camera as our payload, with the sole purpose of exploring the physical limits of our data collection range. Instead of focusing on collecting sensor data, we focused more on the mechanics of balloon launching, considering wind speed, direction, and launch area to determine a new strategy of balloon launching that was more efficient. We were able to release the balloon 559.5 feet into the air and collected these screenshotted photos.
Our project emphasized continuous improvement through analysis of each trial. The following are our key learnings and insights.
There were times throughout the project where we were not on the same page and where it felt difficult to communicate truthfully with one another about our concerns with the project. We also faced disagreements and misunderstandings that likely contributed to us postponing further progress on our project. Whether it was learning how to desolder on the jiggy board or figuring out how to fill the balloons, we encountered many situations where we learned from trial and error and employed the engineering processes of problem solving to finally make breakthroughs.
That being said, we learned so much throughout this internship regarding the value of teamwork, precise procedure, and learning from failure that allowed us to consistently bounce back from our missteps. For us, it helped a lot to break down everything into smaller roles and steps and allow people to do what interested them the most. We also managed to successfully find and retrieve our payload despite our GPS malfunctioning because we were extra prepared and used 2 tracking devices instead of 1.
We want to give a special thanks to our wonderful mentors, who not only provided us with their skills and knowledge throughout this internship, but also allowed us to explore and have fun. From talking about black holes, the formation of atoms, and questions like, how do the sensors know what to collect?
Bob, Melissa, Nick, and Chris answered our questions with full spirit and motivated our interest throughout this internship.
Throughout this project, we learned valuable key skills and lessons that we will be able to implement into our future careers. By working in a large team, we greatly improved on evenly delegating tasks and finding strength in our differences during work time. This internship also enabled us with hands-on experiences to create specific procedures for accurate and efficient data collection. For this project specifically, our incremental trials of practicing varying aspects of our procedure, such as team roles, balloon cut down, and data collection, taught us the vital lesson of performing each step methodically to ensure nothing is overlooked.
Subsequent to C's, I will continue making connections and nurture the connections I have made from this program.
I want to apply the skills I learned here at C's to become a mechanical engineer and develop assistive devices.
And to utilize the invaluable exposure I've gained to engineering experiences such as team problem solving and understanding complex hardware to bring back projects to my community.
Like we did throughout this internship, I hope to continuously foster collaboration across larger groups while also maximizing productivity, and to keep being creative through hands-on learning.
I plan on using the skills I learned from the C's program to develop projects that make an impact in my community.
I will take what I learned from the C's program to get involved in the maker community to build unique and impactful electronics and help inspire more youth and girls like me to pursue STEM.
In the future, when working with large teams, I'm going to prioritize being a good teammate and managing my time effectively. Some things I have learned from this amazing C's internship is to ask all my questions, connect with professionals, stay curious, speak up for my ideas, and continue advocating for women in STEM.
What I took away from the C's internship is that I will continue to take advantage of as many opportunities as possible and practice my leadership, assertion, and networking skills.
After this internship opportunity, I hope to use the leadership, teamwork skills, and knowledge I've gained to better myself, my community, and empower girls in STEM.
These were the online resources we used.
Thank you for listening. Over and out.
Great job, TASR team. I invite you to unmute and turn on your cameras, please. We have several questions. The first question for your team is, how did you settle on the mass needed for optimal flight?
Yeah, so we started by just before our procedure, we were targeting a circumference of 36 pi, which we did through certain calculations. And when our procedure came around, we began by measuring our payload with everything on top, including tape, just the way that it would fly, and we got to 165 grams. From this, we consulted with our mentor, Nick Pugh, to determine how much net lift we would need to successfully launch our balloon. And he had told us we should target a net lift of 100 grams. So that would mean we wanted to get up to around 265 grams. But while we were filling the balloon, since it did form more of a teardrop shape rather than a sphere, it was harder to accurately measure exactly where it was at. So we decided on using two separate balloons to keep them smaller and make sure our measurements could be as accurate as possible. And after that, I think for our untethered launch, we ended right around 260 to 270 grams, which was exactly where we wanted to be. And that's kind of how we made sure that we had a large enough net lift and that the mass was appropriate for a successful flight.
Did you find communication difficult during tracking?
I can take
Yeah,
that.
so sorry, this is a yes and no question. In our practice tethers, we were having some difficulty with communication just because we weren't used to communicating across floors in the building. But once we got to practice and once we established our Zoom call, it was relatively easy to talk amongst ourselves on the ground. During the actual tracking, though, Rania can expand on the difficulties.
Yeah, so since the tracking team, we were at the ground base and we were close to most of the other team members, we didn't really find it difficult to communicate with them. But in communicating with this team and a team, quickly.
Your microphone is disconnecting. So does someone else want to step in?
Yeah, I can take over for her for that part. So what she was saying was that since the tracking team was at the ground base, while the actual people tracking the balloon was somewhere else.
As in the orientation of the balloon, the location, altitude, and it's flying.
Okay, so the next question. Using high altitude balloons as your tool, what future question about the Earth system would you like to explore?
Throughout our internship, we learned the necessary steps to replicate our own balloon missions. In the future, I would like to investigate differences in CO2 and wind speed at different altitudes and locations to see how wind speed affects the dispersion of pollutants, allowing us to further understand and mitigate the effects of air pollution.
Well, good job, TASR team. Thank you all for sharing your research. The next research is from the Measuring Environmental Changes with Altimetry ISAT-2 team, led by Christine Smirda, a subject matter expert in remote sensing and data analysis techniques for planetary science. Please join me in welcoming the ISAT-2 teams. We will view 3 research projects and then open questions for all 3 teams. Team 1, Race Against Climate Change, a case study of vegetation in New York and Atlanta is first.
Good afternoon, NASA interns, scientists, and the rest of the audience. My name is Sharik Batania, and my team members are
Brooklyn Magoo,
Christine Choi.
Today, we will be discussing the research we have taken part in over the past few weeks, named Race Against Climate Change, a case study of vegetation in New York and Atlanta. Here is what we will be discussing throughout our presentation, highlighting the many parts of the scientific process we have gone through. So let's start with the introduction. Urbanization is a common phenomenon in America now, with it happening across the nation. It started in the 1950s and has grown exponentially since then. However, when urbanizing cities, the environment has been put on the back burner, normalizing unsustainable practices in nature. This unsustainability has led to the exacerbation of one big issue, climate change. We will be focusing on 2 symptoms, CO2 production and the urban heat island effect, which is the increasing or warming of temperatures due to large amounts of heat reflection and emission from man-made buildings. And this is where we land on space data. Satellites and space instruments are unique in their data that they can give us because they provide us unique insights that cannot be found anywhere else in the world. Like the satellites and instruments on the page listed here, like the ISAT-2, JEDI mission, MODIS Terra, and the OCO2, we were able to analyze and look at the data to find ways to combat climate change and have a greener future.
Methods. First, for locations. We chose New York City's Central Park as a control for the study due to their stable tree population and compared that to Greater Manhattan, along with downtown, suburban, and rural areas of Atlanta due to their varying levels of tree height, biomass extent, and urbanization. As for our time frame, all data was collected from 2018 to 2020, coinciding with ISAT-2's initial launch in 2018 and the onset of the COVID-19 pandemic in 2020. OCO2 extraction. Using QGIS, a spatial software tool, we outlined a shape around each location. With each point on the shape came a coordinate. We programmed a Python function that calculated the spherical average coordinate pair of all the coordinate points in each shape. We used a spherical average because that took into account the Earth's curvature, whereas a centroid average assumed that the Earth was flat. We then used the spherical average coordinate pairs to find carbon dioxide data from the OCO2 satellite through Earth data. Since the data was presented in a NetCDF4 files, which aren't readable in QGIS, we programmed a Python function that converted NetCDF4 files into CSV files that were readable in QGIS.
Above ground biomass density extraction. We extracted the above ground biomass density from the JEDI mission located in NASA's Earth data software. We then processed and visualized it using the QGIS software. In QGIS, we used polygons that were digitized manually to extract the density values using the zonal statistics plugin applied to the raster dataset.
Good afternoon, NASA interns, scientists.
All the coordinate points in each shape. We used a spherical average because that took into account the Earth's curvature, whereas a centroid average assumed that the Earth was flat.
We then used the spherical average coordinate pairs to find carbon dioxide data from the OCO2 satellite through Earth data. Since the data was presented in a NetCDF4 files, which aren't readable in QGIS, we programmed a Python function that converted NetCDF4 files into CSV files that were readable in QGIS.
Above ground biomass density extraction. We extracted the above ground biomass density from the JEDI mission located in NASA's Earth data software. We then processed and visualized it using the QGIS software. In QGIS, we used polygons that were digitized manually to extract the density values using the zonal statistics plugin applied to the raster dataset. This same method and application was used to do land surface temperature extraction.
Next, we went onto the canopy height data using the ISAT-2 satellite. We first went onto Open Altimetry, a software created by NASA specifically for the visualization of ISAT-2 datasets. Using the software, we specifically selected the ATL-08 laser on the ISAT-2 satellite, which is the only instrument on the satellite that collects vegetation height data. Using the calculated locations and time spans from earlier, we found the data we needed. Additionally, we developed equations to calculate deforestation rates and percent change in biomass density using the canopy heights from the satellite.
As previously mentioned by Sharia, ISAT-2's canopy height data was used to calculate the biomass density percent change, as the JEDI instrument only provided biomass density for 2020. Next, using such derived equations for carbon sequestration, we programmed a Python function to calculate Atlanta's carbon sequestration. Satellite results.
Atlanta's biomass. Seen in Figure 1, Atlanta's boundary is overlaid on an above-ground biomass density map. Figure 1.2 shows the pixel visualization of downtown Atlanta with a mean density of 15.71, while Figure 3, much lighter, shows Atlanta's rural area, which is a mean density of 130.71. And to the right of me, Figure 1.4 shows suburban Atlanta with a mean density of 52.66, just in the middle of both. When we compare this to Central Park, you can see on the left there's a pixel visualization of Central Park's mean density of 43.29. This biomass statistic suggests a managed urban park with a moderate number of trees, shown in the standard deviation that was extracted, with fewer trees and less variation than compared to the much larger and grander rural Atlanta. The land surface temperature means. Downtown Atlanta, although high, has 315.12 Kelvin, while rural Atlanta is much cooler with a recorded 313.82 Kelvin. Suburban Atlanta is much higher with 317.95 Kelvin. And when we're looking at the New York regions, we have Central Park with this 316.22 Kelvin, and the Greater Manhattan, just located souther with the boundary, is 316.44 Kelvin.
Carbon dioxide content in Atlanta. The highest average carbon dioxide content in parts per million for Atlanta is in downtown Atlanta, the middle average content is in suburban Atlanta, and the lowest average content is in rural Atlanta. Downtown Atlanta also has the greatest carbon dioxide content growth rate, with suburban Atlanta following and rural Atlanta the least. On the graph, you can see a slight dip in all three lines in carbon dioxide content around October 2019. We assume this discrepancy was due to Atlanta students partaking in the 2019 global climate strike in September. Carbon sequestration in Atlanta. Downtown Atlanta has the most drastic carbon sequestration change rate out of all three locations, at a decrease of 49% sequestration annually. Next, suburban Atlanta has a negative 27% sequestration rate annually. And finally, rural Atlanta in fact increases slightly by 2% annually. Overall, rural Atlanta was the only location out of all three locations in Atlanta that had increasing carbon sequestration.
Canopy heights provided us with a lot of insights as well. First, we were able to find the deforestation rates in all three locations of Atlanta, being 50% for downtown Atlanta, 28% for suburban Atlanta, and then negative 9% for rural Atlanta. This means that rural Atlanta did not experience deforestation, but the other two locations did, and that overall less trees exist the more urbanized Atlanta gets. Additionally, with the data and the equations we developed previously, we found that the percent change of biomass density is 2% for trees in Atlanta.
Correlations.
How biomass affects surface temperature. The calculated correlation coefficient is approximately negative 0.411, which suggests that the above-ground biomass density and temperature given has a negative correlation in relation, but as above-ground biomass increases, temperature slightly decreases. And you can see this in rural Atlanta with the AGB and temperature.
How biomass affects carbon dioxide and carbon sequestration.
Overall, in Atlanta, increases in biomass produces increased carbon sequestration. Additionally, overall in Atlanta, as carbon sequestration increases, the amount of atmospheric carbon dioxide content, parts per million, decreases. All three values, carbon dioxide, sequestration, and biomass density for rural Atlanta, are relatively unchanged with only a slight increase over time.
Green spaces could be our future. The effects of implementing green spaces in New York City is seen on the graph above. The Central Park Zone, which is Central Park and 3 blocks out, has a recorded land surface temperature of 316.22 Kelvin, while the Greater Manhattan region, located a little south, is 316.43 Kelvin.
Finally, the conclusion. First, our broad hypothesis is supported that vegetation cover in urban areas are effective at mitigating the effects of climate change. Based on our examinations of CO2 production and the urban island effect, we were able to find support that vegetation is able to reduce the amount of CO2 in our atmosphere as well as lower temperatures. This means locations like New York City can be used as a blueprint for green infrastructure for locations like Atlanta, which need it. Also, space data is very useful for combating climate change and should be studied and used more in future research to help create better functions to prevent climate change in the future.
The NASA STEM program has definitely helped me as an aspiring architect, offering multiple benefits that both enhance the design process and the final outcomes of my future projects. Mapping what I learned provides vital spatial data that informs site analysis, allowing me to understand the topography and existing architecture that can be used in the future.
For me, the NASA STEM program has provided me with invaluable skills and insights essential for my aspirations as a computer scientist focused on the environmental field. Through hands-on experience with various software tools, data analysis, and coding, I learned how to manipulate and interpret complex environmental data and how to leverage data-driven approaches to promote sustainability.
For me, the NASA STEM program was an incredible experience and provided me with a lot of data and learning about how to analyze data over a wide range of topics. Additionally, with the experience I gained using many online software tools as well as data analysis tools, I was able to learn a lot and gain a lot of experience for what I can use in the future as an aspiring data scientist.
Just some highlights. Some of our highlights was the iFly experience, the Z-Cube, the main event, and Dave & Buster's, while some of our challenges included the accessibility of some data types, project planning, and deriving equations for carbon sequestration.
So finally, we would like to thank our mentor, Dr. Sumerta, for all the help she has given us over the past few weeks to complete our project, as well as the NASA STEM program as a whole. With our presentation coming to an end, does anyone have any questions?
So we will hold questions till the end. And I just wanted to let you know we are having some technical difficulties. That's why the last presentation was a little blurry. We will make sure on the recorded version that it is uploaded with the one the students provided. We're under severe weather storms at the current time. So let's keep our fingers crossed the next presentations will go smoothly. We want to welcome Team 2, Understanding How Ocean Patterns Impact Coral Reefs in Hawaii.
Hello, we're the ISAT 2 team. My name is Jai Pasilio.
And I'm Michaela Gerbishak.
Our project is understanding how ocean patterns impact the coral reefs in Hawaii. This research aims to highlight the correlation between waves, ocean properties, and coral reef damage to better understand how coral systems can be preserved. Researching different ocean characteristics from the past can help to predict what will happen to coral reefs in the future.
For context, climate change has created multiple extreme changes in ocean patterns, causing excessive damage to coral reefs such as those around the Hawaiian Islands. The datasets used were sea surface temperature, chlorophyll concentrations, wave heights, sea surface salinity, bleaching alert areas, coral hotspots, and bathymetry. All metrics in this research were used to correlate with one another to understand the relationships between these patterns.
The process we used. This process uses satellite data from 2021 to map bathymetry, sea surface salinity, chlorophyll blooms, sea surface temperature, coral bleaching, alert areas, and coral hotspots. The data is focused on Oahu, and we used buoy data to calculate the average monthly wave heights. We used 4 buoys around the island. To get all different views of Oahu, we used data from the northeast, southeast, southwest, and northwest shores. This data is recorded and mapped to show the monthly differences for all of the satellites and buoys. My name is Jai Pasilio, and northwest shores. This data is recorded and mapped to show the monthly differences for all of the satellites and buoys.
This video highlights chlorophyll concentrations and the graph as well. Both were to analyze the algal blooms by months in 2021. The greatest blooms were in the southeast and the northwest. Chlorophyll blooms, for context, are most frequent when the sea surface temperature is around 25 degrees Celsius. That means if it is too warm or if it is too cold, the chlorophyll will not bloom. The number of blooms drop during the summer months where the water is too warm, whereas it will peak in the winter when the water is just right.
Sea surface temperature is the measure of the ocean's temperature. We measured the mean sea surface temperature. We also measured it in Celsius. In the winter and spring, sea surface temperatures are lower because of the cooler atmosphere, whereas in the summer and fall, sea surface temperatures tend to be higher as the weather is warmer. This correlates with chlorophyll concentration because the colder temperatures see the biggest spikes in chlorophyll blooms.
This graph shows wave heights around 1 p.m. in 2021 on monthly averages. There is daily data and is now averaged out. The highest wave heights were in the south of Oahu, which for reference are both in orange and green to represent southeast and southwest Oahu. This correlates with sea surface salinity because the highest sea surface salinity was in the east. The northeast saw the highest sea surface salinity because it has the least amount of water movement. That means that the salt stays in the ocean far longer than it would have in areas with more movement.
Sea surface salinity is the measure of salt throughout the sea. This affects the density and ecosystem of the ocean. The northeast tends to have the highest sea surface salinity. This is caused by less waves and a higher ocean temperature, which affects evaporation. Throughout the year, sea surface salinity continues to grow.
We are going to start the video again to see if we can resolve our technology issues.
Higher ocean temperature, which affects evaporation. Throughout the year, sea surface salinity continues to grow.
This video shows bleaching alert areas. In the year of 2021, Oahu saw no bleaching threat. However, in some months, other islands saw threats. For instance, in March to May, the island of Hawaii saw bleaching threats, same with other islands. Coral hotspots correlates with this because the bleaching alerts and hotspot alerts had the same months being the highest points on their graphs.
Coral hotspots are the measure of where coral has faced thermal stress. Thermal stress is heat damage. In March, hotspots hit their lowest point as the sea surface temperature also hits its lowest point. However, in August, they hit their highest as the sea surface temperature also hits its highest.
This graph highlights the bathymetry from ISAT-2. Bathymetry is the study of ocean depths, but for this research specifically, it was used to show where the coral is below the sea surface. On this graph, we can see that the data shows that the coral is about 10 meters below the sea surface on the southeast side of Oahu.
In conclusion, this research found trends between different ocean characteristics around Oahu and Hawaii.
By taking data from all four sides of Oahu, the study was able to see how different places are affected by different ocean characteristics.
This research found connections specifically between coral bleaching, sea surface temperature, wave heights, and chlorophyll.
Through this research especially, it is now possible to predict future ocean events and anomalies. This is about the pros and cons of this project. For our pros, we will bring up analyzing data, charting data, and finding motivation. Analyzing and charting data were easily the best parts because of how quick and smooth they went. If we had not had our software, we would have had to do this all by hand, which could have easily led this to go to the con side. And the final pro, finding motivation, is easily the best pro, because it was so easy for us to find motivation on a topic we both were interested in.
For the cons, finding data, time limit, and scheduling. Finding data was challenging because many data sets either weren't the correct dates or were difficult to download. We were also given a time limit of 2 weeks, which created an urgency and a stress to finish this project as fast as possible and as well as possible. Scheduling was also very difficult because while working on this project, we also had other activities going on. This caused us to have a lot less time, and it made it difficult to find time to work on the project out of what's already was scheduled. This program has helped strengthen my will to become an engineer. Through this program, I was able to connect my love for STEM with my love for my home. Dr. Sumrita, thank you for guiding us through this project and nurturing our love for science. Thank you, C's, for this incredible opportunity.
This program has also helped me realize what I want to be when I grow up. I would like to continue my passion of becoming a marine biologist. Through this program, I was able to study the coral on the Hawaiian Islands, which is very interesting to me. Thank you, Dr. Sumrita, for all the help that you have given us during these past few weeks, and especially thank you to C's for the summer program that is nothing like I have ever experienced.
So our next ISAT-2 research is on analyzing air quality dynamics in U.S. cities affected by COVID-19 lockdowns.
Hello, my name is Kira Boone, and this is my presentation on analyzing air quality dynamics in U.S. cities affected by COVID-19 lockdowns. This study examines air quality changes in New York City, Los Angeles, and Chicago using Sentinel-5 satellite data for the years 2019, 2020, and 2023, focusing on 5 key pollutants: carbon monoxide, formaldehyde, nitrogen dioxide, tropospheric ozone, and sulfur dioxide. The aim of this project is to evaluate the impact of decreased human activity during the pandemic lockdowns on air pollution levels, and to understand the subsequent rebound as cities return to pre-pandemic activity levels. The COVID-19 pandemic caused global lockdowns, resulting in almost immediate decreases in many forms of air pollution, most notably nitrogen dioxide and 2.5 micrometer particulate matter. As lockdown restrictions eased and people began to engage in more transportation and industrial activities, these levels began to rise, but stayed lower than pre-pandemic. As society began to return to normal, emissions and air pollution levels also began to return to pre-pandemic levels, in some cases exceeding them. This was not without consequences, however. Temporary improvements in air quality during the lockdowns likely had positive health impacts, reducing respiratory illnesses and cardiovascular problems associated with air pollution. As seen here, the 5 air quality indicators analyzed in this study can have harmful impacts on human and environmental health when present in high concentrations. Using the pandemic period to study the effects of reduced human activities on systems and climate patterns offers insights into potential mitigation strategies to improve human health for the long term. The study focused on 3 major U.S. cities, New York, Los Angeles, and Chicago, chosen for high population densities as well as transportation and industrial activities. The analysis utilized Sentinel-5 satellite data to monitor the 5 air quality indicators mentioned previously. Data was collected for the months of July in the years 2019, 2020, and 2023 to capture pre-pandemic, during pandemic, and post-pandemic conditions respectively, as well as data from July 2019 to July 2023 to observe larger scale changes over time. Difference mapping was utilized to visualize the changes in each of the 5 analyzed pollutants as average July concentrations between 2019 to 2020 and 2020 to 2023. Selecting a single month helped to isolate seasonal fluctuations that may affect aerosol concentrations and distributions, and July was the selected month as is typically the busiest month of the year for urban activity. Time series for July of 2019 to July of 2023 were also conducted for each air pollutant for each of the 3 cities so as to provide a larger scale of air pollutant distributions and concentrations. This allowed for seasonal fluctuations to be examined and for potential anomalies to be highlighted and investigated further. As seen in the examples here, the general trends of aerosol concentrations were stable, though there is a gradual upward trend closer to July of 2023. After exporting average July air pollutant concentrations by city, graphs were generated for each pollutant by year, 2019, 2020, and 2023, in each city, New York, Los Angeles, and Chicago. These bar graphs display mean annual changes in tropospheric ozone, sulfur dioxide, and nitrogen dioxide. Trends were typically that the pollutant concentration would drop from 2019 to 2020, but would rise again by 2023, in several cases surpassing pre-pandemic levels. Analyzing percentage changes, sulfur dioxide levels showed different trends across the cities, indicating regional differences and specific pollution sources such as power plant and industrial facilities. Tropospheric ozone levels had slight variations, influenced by changes in precursor emissions such as nitrogen dioxide. Nitrogen dioxide decreased significantly in 2020, likely attributed to by the reduced vehicle traffic, and then rebounded again in 2023 as the activities resumed. Similarly to the previous bar graphs, the average pollutant concentrations for carbon monoxide and formaldehyde were also analyzed. Carbon monoxide saw reductions during the 2020 lockdown and made notable rebounds by 2023, whereas formaldehyde experienced continuous concentration drops from 2019 to 2023 in both New York City and Chicago. This difference layer of carbon monoxide concentrations visually depicts how the Northeast US experienced disproportionately larger carbon monoxide concentration increases than the rest of the country when averages from July of 2020 are compared with those of 2023. Potentially contributed to by the boreal forest common in the northern hemisphere, known to emit formaldehyde, as well as the different atmospheric conditions that could have accelerated its formation. The lockdowns led to substantial decreases in pollutants, with New York City, Los Angeles, and Chicago showing marked improvements. Post-pandemic, there was a sharp rebound in pollutant levels, particularly carbon monoxide and nitrogen dioxide, as normal activities resumed. Sulfur dioxide levels varied across the cities, highlighting the influence of specific regional pollution sources. This suggests that local factors such as industry and energy production significantly impact sulfur dioxide emissions. New York City and Chicago saw significant increases in carbon monoxide levels post-lockdown, far surpassing the rise in Los Angeles. This indicates that local activities and sources may have driven these sharp increases. Sulfur dioxide trends were inconsistent, suggesting other factors influenced its levels beyond reduced human activity. Los Angeles' significant reduction in formaldehyde during the lockdown points to a pronounced impact from reduced industrial activity or distinct local sources. The study observed significant reductions in sulfur dioxide and nitrogen dioxide levels in 2020 compared to 2019, indicating the immediate impact of reduced human activities during lockdowns. However, carbon monoxide and formaldehyde levels showed variable changes, with some increases noted by 2023, reflecting the complexities of air pollution sources and atmospheric conditions. Tropospheric ozone levels remained relatively unchanged, underscoring the intricate chemistry involved in ozone formation and its dependence on various precursor emissions and environmental factors. These findings highlight the considerable influence of human activities on air quality, particularly for pollutants like sulfur dioxide and nitrogen dioxide. Insights gained from these changes can be crucial for shaping urban planning and public health policies to mitigate air pollution and improve environmental health. Here are my references. Thank you. I'd like to thank all of the amazing staff at both CSR and NASA STEM for all of their help and mentorship with this project, particularly Ms. Miller and Ms. Baggio, as well as my amazing mentor, Dr. Christine Samarda. Some of the highlights of this project were the many projects, and while it was a challenge to balance these, it was such a collaborative environment and I developed so many important skills. Overall, I love this program and it has solidified my passion for climate science and my hope to continue this in the future.
So we invite all 3 of the ISAT-2 teams to turn on their cameras and unmute their mics. We have several questions. The first questions are for Team 1. How did you select the area that you wanted to study?
I can answer this one. So first for our control location, we chose New York City Central Park due to their very stable tree population, and then compared that to Greater Manhattan as well as downtown, suburban, and rural Atlanta due to their varying levels of tree height, biomass extent, and urbanization.
And then let's skip over to Team 2. What are your thoughts on mitigating the issues around the Hawaiian Islands that you have identified?
We could talk about, like, I guess increasing wave patterns, somehow getting movement in the areas could help diminish what is happening to damaged coral because the particles won't just be staying in one spot.
And Team 3, what was found in the data that you provided that surprised you, and what data would you like to explore further?
I think something that particularly caught my attention was the trend with formaldehyde in particular. In more northern regions of the US, such as Chicago, there was a much larger trend. And looking into this further, it turns out that there are many precursor emissions to this, to formaldehyde, that can be caused by things like boreal forests. So that would be something that I would definitely want to look into more, as it is definitely an extraneous variable that I originally did not account for.
Great. Well, you all did an excellent job. We thank you to the ISAT-2 teams. So please welcome the Mars Rover Utilization Team, led by S.J. Ralston, a Mars research scientist with Jacobs Technology, located at NASA Johnson Space Center, and led by Project Assistant Todd Heflinger on site. The presentation from the Mars Utilization Team is Innovation Rover, a stepping stone to human exploration at Holden Crater.
The Innovation Rover, a stepping stone to human exploration at Holden Crater.
My name is Rohith, and I'm a rising senior at Thomas Jefferson High School for Science and Technology in Alexandria, Virginia.
My name is Lisa, and I'm a rising senior at Mililani High School in Mililani, Hawaii.
My name's Shohan. I'm a rising senior at DuPont Manual High School in Louisville, Kentucky.
My name is Ava, and I am a rising senior at Grand Rapids Christian High School in Grand Rapids, Michigan.
My name is Noah, and I'm a rising senior at Vanden High School in Fairfield, California.
My name is Matthew, and I'm a rising senior at Cheraho Regional High School in Richmond, Rhode Island.
My name is Emma, and I'm a rising senior at Grand Rapids Christian High School in Grand Rapids, Michigan. I'm Reagan, and I'm a rising senior at Yulee High School in Yulee, Florida.
As far as we know, Earth is the only place in the universe to ever bear life. But that's only as far as we know. If we truly want to understand whether or not we're alone in the universe, the search for life is vital. But where should we look? Mars. Mars orbiters and rovers have hinted at a past full of flowing water activity, which are signs that are conducive to life. This begs the question, could Mars hold human life in the future? Importantly, this aligned with NASA's goals of human exploration and habitation beyond Earth, with Mars being the next frontier. Human missions are essential as rovers simply cannot keep up with human research potential. Developing technologies to live off the land and local minerals on Mars will reduce Earth dependency, as well as furthering our knowledge in expanding human habitation throughout the inner solar system.
In situ resource utilization, or ISRU, is the idea of harnessing local natural resources to enhance the capabilities of human exploration, rather than relying on Earth for materials. In essence, it's making needed resources on location instead of bringing them from Earth. There is no way to consistently travel to Mars without ISRU. It will cost too much and take too many trips. The hope then is to be able to produce fuel, water, oxygen, and habitation materials on Mars from Mars. Possible Mars resources that can be used to do this include silicates, which hold the possibility for extraction of a variety of materials, including oxygen, which can then be used as a fuel propellant, and metals like iron and magnesium. Clay minerals can be used to extract water for fuel propellant, and also have the possibility of being used for building materials and strong pottery. Ferric minerals hold iron that has a variety of applications within building, carbonates, and silicates hold the ability to be used as a binder for a possible 3D printing compound, and Mars regolith holds the ability to possibly be used as a printing compound.
NASA has already sent rovers to Mars, so why do we need another one? Previous rovers such as Curiosity and Perseverance traveled to Mars searching for signs of past and current life. And with the Artemis mission in full swing, it has become evident that we need to start looking into a future mission to Mars with new objectives, which is what our rover Innovation would do. It would be the first to prioritize the search for resources and locations on Mars that would prove to create possible sustainable environments for future astronauts.
Now, going from our background work to our project. It entailed designing a hypothetical rover mission to explore in situ resource utilization on Mars. In addition to acquiring knowledge about Mars, such as studying its habitability and preparing for future human exploration, our mission involved identifying various regions of interest around our landing site, in addition to creating a suite of instruments for a rover.
One of the primary aspects of our mission involves choosing the landing site that will serve as the location for our rover's research and exploration. To determine the landing site, we looked at target minerals, environments of interest, ISRU potential, and mission constraints. Arizona State University's JMARS and Washington University's Mars Orbital Data Explorer enabled our team to examine elevation, slopes, and other confining factors as they related to landing site decisions. Taking into account these factors, we quickly narrowed down the list to 4 top candidates. Holding Crater due to its stratigraphy and diverse mineral deposits, Everswald Crater for its well-preserved delta, Lomonosov Crater because of its rich weather history, including a mega tsunami, and Mars Vallis due to its rich clay deposits and stratigraphy. In the end, Holding Crater was chosen as the final landing site for Innovation. This was because it held many environments of interest, including channels, evidence of ancient water activity, and potential large stratigraphy sections. It also held many target minerals of ISRU potential within our landing ellipse, including carbonates, ferric minerals, and phyllosilicates. Lastly, Holding Crater is an area of low rock abundance, slope, and elevation, ensuring the rover can easily drive around the crater.
The selected targets in the Holden Crater each feature highly sought-after minerals for creating in-situ resources and providing information about the history of Mars. Using JMARS's database, our team examined the abundance of minerals within the Holden Crater by means of CRISM data. For example, locations 6, 7, 8, and 10 all were selected due to the presence of hydrated minerals and the potential for an in-situ binder in 3D printing, while other locations such as 2, 3, and 4 were selected for the presence of ferric minerals that can be used for construction, oxygen production, and fuel propellant.
With the selected targets in mind, it was important that Innovation be able to detect and collect the necessary data, which is what played into the selection of the instrument chosen in addition to safely landing the rover. Due to the weight of the rover, implementing a sky crane for landing was the best option, ensuring that Innovation could safely land in the ellipse. After a successful landing, the rover needs to stay powered and operate until nightfall, leading to the choice of an RTG as a power source. Innovation has a versatile instrument suite as shown to handle all aspects of our mission objectives. Selections of cameras such as SuperCam and Sherlock were chosen for imaging minerals and their composition using lasers and spectroscopy, while systems such as RAD and REM were meant for informing about atmospheric data. To reach areas inaccessible to Innovation, a small helicopter equipped with spectrometers was placed inside the rover. Finally, a 3D printer using Martian regolith was implemented as a pioneering method for in situ fabrication on Mars. Now, let's dive into one of these instruments. One of the primary objectives for Innovation is to find a way to use in situ resources to build possible habitable structures. For this to be tested, Innovation will be equipped with the Mars Regolith Fabrication System, or MARS. This is a 3D printer that will utilize the Mars regolith and other available minerals as possible binders to fabricate structures as a technological demonstration. The MARS printer is equipped with 2 secondary instruments, an electrostatic regolith collector and a corkscrew mineral excavator, to collect the necessary resources. Both are located beneath the rover near the printer's nozzle. The electrostatic regolith collector will be able to pick up the regolith from the Martian surface and deposit it into the printer, while the corkscrew excavator will scoop in situ binders and necessary minerals, which will then be combined into a 3D printing compound and printed using the nozzle onto Mars's ground.
Now, when navigating a rover through Martian terrain, the utmost care is required. This often results in extremely slow terrain traversal, as well as limitations on what type of terrain can be investigated. In order to access a wider variety of observations, we proposed the inclusion of a versatile, lightweight atmospheric drone known as VLAD. This dual-rotor, solar-powered drone would be able to conduct science in locations not accessible by innovation, such as crater edges or sand dunes, through the use of a lightweight Raman spectrometer known as LARF. This instrument could conduct mineralogy studies in locations 3 meters away from the drone in a small footprint of under 500 grams. By using the rover and SuperCam to scout out locations for VLAD to investigate, along with orbiter data, we could not only greatly increase the scientific potential of the mission, but also support the search for 3D printing binders needed by the proposed Mars mission.
NASA's SHERLOC instrument, which stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals, is currently being utilized on the rover Perseverance. The instrument is located on an arm using a Raman spectrometer with an ultraviolet laser for detailed mineral and organic compound analysis in the Holden crater. SHERLOC identifies minerals like clay, carbonates, and sulfates, helping locate regions of past water abundance. This data is important for finding potential binders for the Mars 3D printing compound that could be used for sustainable building materials for future Mars missions.
The RAD instrument, or Radiation Assessment Detector, was previously used on the Curiosity rover. The instrument would be used to detect the levels of radiation on Holden crater's surface. RAD's investigation of the radioactive conditions on Mars is crucial for the understanding of the environment and ensuring future astronauts' safety. Besides providing vital information on the threat of space radiation, RAD is also a key instrument in testing MARF's capability. By evaluating how well the MARF's regolith compound is at blocking these harmful rays, RAD will help test the possibility of Mars regolith as a protective measure for future human habitation.
In addition, Innovation would also be equipped with the Rover Environmental Monitoring Station, which would be used to measure and record the environmental conditions at Holden Crater. It would use a variety of sensors to measure various weather indicators, such as wind speeds, humidity, and atmospheric pressure. While previous rovers such as Curiosity have already used REMS to record and analyze the environmental conditions in locations such as Gale Crater, Innovation offers new opportunities for this device. With the capabilities of MARFs, REMS has the opportunity to observe and record the effects of Mars's weather on 3D printed structures that, in the future, could possibly be used to shelter humans on the planet.
To close out the instrument suite, SuperCam, used on Perseverance rover, is equipped with a microphone, camera, laser, and spectrometer to analyze Mars mineral and chemical composition. With this, it can target areas as small as a pencil point from up to 20 meters away, and by examining minerals and soils with its many instruments, it can aid in the understanding of specific minerals and the locations that are important to the future habitation on Mars. Furthermore, onboard SuperCam, it has a visible near-infrared spectrometer capable of precisely detecting mineral compositions.
All in all, In-Situ Resource Utilization, or ISRU, is the next step in space exploration. By identifying and harnessing Mars's resources, we make human habitation not only feasible, but necessary. ISRU is the first step in exploring the possibilities of living on Mars, enabling us to live off the land and reducing the need for costly shipments from Earth. Our rover, Innovation, tries to accomplish NASA's goals and expand ISRU capabilities, ensuring a sustainable environment for future astronauts. The future rests in the hands of the present, and our work today paves the way for humanity's tomorrow on Mars.
This internship has been full of amazing opportunities and experiences. It has allowed us to build relationships with other students and professionals in the field, providing us with incredible mentors who have been able to give us relevant scientific sources and experience novel opportunities. However, it has not all been sunshine and rainbows. There have been many challenges we faced in our research, from inconsistent data to learning multiple new programs and apps. When contradictory evidence was presented, such as inconsistent elevation data in JMARS, we had to find accurate data, looking through multiple sources to determine the correct elevation of a specific landmark in Holden Crater. Through challenges like these, we adapted and learned new methods of research used in developing a concept for the next Mars rover mission, Innovation.
SEAS exposed me to the vast realm of scientific research pertaining to Mars exploration, a topic I have remained widely infatuated with since childhood. Even more so, my SEAS experience was enhanced in large part due to the brilliant and inspiring minds I was surrounded with the entire time.
The SEAS internship has been a wonderful experience, allowing me to work in a professional environment with like-minded peers and mentors. Through this experience, I've been able to dive into spaces of research I now hope to go into in the future.
The SEAS internship has shown me what it's like to work in a professional environment. During the internship, I was able to immerse myself in cutting-edge research on Mars exploration. Working alongside brilliant mentors and peers has both expanded my knowledge and increased my passion for space exploration.
SEAS has been a great experience for me, providing a once-in-a-lifetime opportunity to learn about the scientific world and research involved. In this internship, I have been challenged in many ways that I know will allow me to advance further into my future career.
This internship has been an extraordinary experience and has given me the opportunity to dive deeper into the sciences by providing relevant scientific resources and novel hands-on experiences. It has also allowed me to build connections with and to learn from other like-minded students and professionals in the field.
SEAS has been an amazing opportunity for me, not only allowing me to connect with people of diverse backgrounds who share similar interests to me, but also to be able to have access to mentors who are knowledgeable in the topics I care the most about. I've learned so much in these 2 weeks and truly advanced my abilities as a researcher.
SEAS has been a truly enriching experience, allowing me to work in a collaborative environment with peers and mentors that share my drive and passion for science. Through SEAS, I've been able to challenge myself and really understand the why behind the research I've been so drawn to these past few years.
SEAS has provided me with the experience and opportunity to grow my skills and has allowed me to meet peers and professionals in the top of my prospective field. In addition to making great memories with fellow interns, it has served as a catalyst to my abilities as a scientist and researcher. Finally, we want to thank everyone over these past 2 weeks who has helped us develop and create the project. First, we want to thank the NASA SEAS program and the Center for Space Research at UT Austin for providing us with the resources and facility in order to conduct our research. In addition, we also want to thank the organizers, Ms. Margaret Baggio and Ms. Selena Miller. We also want to give a shout out to all the advisors that have helped us along the way, including Ms. Molly Goldstein, Dr. Aditi Pandey, Ms. Stephanie Hanover, and Ms. Rebecca Siegfried. Next, we want to thank the University of Arizona and Washington University for JMARS and the Mars Orbital Data Explorer. Lastly, but definitely not least, we also want to give a big thanks to our project mentor, S.J. Ralston, and assistant project mentor, Todd Hefflinger, for guiding us through the entire project and helping us whenever needed.
So we invite all the Mars team members to please turn on their cameras and unmute their mics. We have several questions. The first question is, do you think your research on creating sustainable Martian building materials can be utilized on Earth to transition away from resource extractive practices?
I think one of our teammates' camera isn't working, so I can answer this for them. The answer is yes. We believe that after a period of time of being able to practice it on Mars and creating sustainable Martian building, this can definitely be transferred and utilized to Earth, and being able to more efficiently and effectively extract resources from sources on the planet.
And the next question, how do you plan to troubleshoot the 3D printer if there were to be issues when picking up regolith? Someone from the Mars team?
Yeah, so I can take this question. So, one big thing would be just finding locations in the first place where there is a abundance of regolith, and this can be done by looking at the thermal inertia of certain areas on the ground, and areas with lower thermal inertia are often covered in finer regolith, which could be used for the Mars 3D printer, as well as just having redundant systems that would be able to pick up like so that if one of the systems fails, another one would be able to still pick up regolith from the surface.
And how would you determine where it is safe for your rover to land?
When we considered where we wanted to land our rover, we considered a bunch of things, such as the amount of rock abundance that was in the area and the elevation. Typically, when you want to land a rover, you want to look for lower levels of elevation. So that's what played into choosing about where we wanted to land.
What challenges did your team encounter while working on this project?
While working on this project, we had to use softwares such as JMARS, and those softwares are made mainly for researchers and don't have a user-friendly system. So it was a learning curve to understand the softwares and utilize them properly.
How has SEAS impacted your future goals in the STEM field? And which skills do you feel were able to acquire and take back with you for your academics moving forward?
I can answer this question. I just want to make sure real quick that you guys can see me okay.
We can.
Awesome. So SEAS for me has really solidified my passion for STEM and has even further encouraged me to actually search for astronaut opportunities in the future. More specifically, my project introduced me to the prospect of one day traveling to Mars, because I have always wanted to become part of something incredible in space discovery, and I think going to Mars sounds pretty incredible in that aspect. And more specifically, before this internship, I often strive to complete projects quickly with just enough accuracy to get the job done. But I am now going home with the valuable lesson to slow down and truly understand the intricacies involved in working with the STEM field, both in high school and one day soon, hopefully, the real world.
Awesome. You've all done an excellent job. Congratulations to the Mars team for your research. The following research is from the FUNPEDS team led by Adam Noakes, a lecturer at the University of Texas at Austin and in the Cockrell School of Engineering, and teacher in the Department of Aerospace Engineering. So we want to welcome the FUNPEDS team and their research on drone positioning with Kalman filtered estimations.
Hi, I'm Noah Van Burden. I'm from Percy, Pennsylvania, and I attend Penrith High School.
Hi, my name is O. McAhall. I'm from Richboro, Pennsylvania, and attend Council Rock High School South.
Hello, my name is Seth Akins, and I am from Faircrest, Washington, and I go to Curtis Senior High School.
I'm Geraldo Jefferson from Miami, Florida, and I attend Ransom Everglades.
Hi, my name is Alicia Chen, and I am from San Jose, California, and I go to Basis Independent Silicon Valley.
Hello, my name is Omolo Falana, and I am from Plainfield, New Jersey. I attend Union County Magnet High School.
My name is Marian Fusco. I'm from Brooklyn, New York, and I attend Millennium High School.
Hi, my name is Hope Dixon, and I'm from Falls Church, Virginia, and I go to Georgetown Visitation Preparatory School.
Now, let's move on to the inspiration behind our project, which comes from the UT Austin Drone Estimation Lab, or DEL. The DEL project is working to create an accurate location estimation for drones by running real-time sensor inputs through an extended Kalman filter, or EKF. This process involves fusing outputs from different sensors on drones. By doing so, they are able to create 3D error ellipsoid visualizations. One significant achievement of the DEL project is their error ellipsoid accuracy of 97.1%. However, it's worth noting that while DEL has performed location estimation, they have not yet implemented an extended Kalman filter. This gives us the opportunity to build on their work and integrate a Kalman filter into our project to achieve even greater accuracy in drone position estimation.
To build on the DEL project, we felt the best way to improve accuracy was to incorporate more data through the added sensors such as LiDAR or a camera. Then using an extended Kalman filter, we would be able to fuse onboard drone IMU and GPS data with LiDAR data or camera data for more accurate pose estimations.
The main problem that our group is trying to face is that the growth of the drone industry increases air traffic, raising the risk of drone collisions with other UAVs and non-cooperative targets such as birds and kites.
Imperfect data is considered noisy. Take this sonar data collection of altitude, for example. The human eye could reason that based on the graph as a whole, the altitude would never drop by multiple meters in a fraction of a second. However, hardware inaccuracies and sensor fluctuations produce noisy data that needs to be filtered and cleaned. Our study sought to estimate position accurately by filtering noisy data from IMU, GPS, and LiDAR data with a special filter designed for aerospace applications called the Kalman filter.
Now let's walk through the data analysis process for our project. The process can be broken down into 6 main steps. During drone flight, data is recorded by the Pixhawk 6X flight controller as the drone flies. This includes all of the sensor inputs, flight data, and IMU recordings needed for our analysis. After the flight, the recorded data is extracted. We use QGround control to download the .ulog files from the drone. These files contain the raw flight data in binary format. The next step is to convert these .ulog files into a much more usable format. Using the pyulog Python package, we convert the .ulog files into .csv files, which contain the data in text format, making data analysis much easier. Once we have the .csv files, we are then able to import our data into MATLAB and choose the specific data types that we wish to Kalman filter and analyze. Then, we apply the Kalman filter to the data in MATLAB. Here, we minimize the noise and errors present in the raw data. This allows us to create an estimate of the true position of the drone. Finally, we compare the filtered results to the GPS data and videos that we took of the flight, as well as graph our filtered data to visualize the path of the drone. This allows us to evaluate the accuracy of our position estimation and make any necessary adjustments to improve it.
Let's look at the key components of the Holybro X500 V2 development kit for our drone project. The Pixhawk 6X flight controller manages the flight dynamics with advanced IMU and multiple I/O ports. The PM02D provides power and monitors battery voltage. The M10 GPS module provides precise positioning data. We use the SIK Telemetry Radio V3 for long-range communication. The X500 V2 frame kit is durable and lightweight, and additionally it's modular for easy assembly. 4 Holybro 216 KV920 brushless motors provided thrust, controlled by BL Heli S28 ESCs for smooth operation. 6 1045 propellers ensure efficiency in thrust and stability, ensuring our drone's reliability and efficiency in performance. Now the communication system. The transmitter or remote control sends input signals when you move the various switches to the bound receiver on the drone. The receiver then replays these inputs to the flight controller. The flight controller acts as a mini computer, processing the inputs from the receiver and sending output values to the motor, ensuring they reflect the controls performed on the transmitter. Additionally, the flight controller continuously monitors the various sensors' values as the drone is flown.
During our building process, we organized the team into 3 groups based on their skills and interests. Each group was assigned different remote controllers and utilized distinct GPS receivers and transmitters. 2 of these groups used telemetry communication hardware included in the Holybro kit, paired with Radio Link and Radio Master controllers respectively. The 3rd group opted for a different telemetry network, HERA, which required the addition of an air unit and cooling fan to their drone. All these groups successfully assembled the frames, installed the motors, and set up the Pixhawks. Additionally, each group managed to establish a stable connection between the remote controller and drone. During the assembly of our drone, we encountered several obstacles primarily related to product issues and financial constraints. Initially, assembling the Holybro kit posed a challenge as the baseboard screw holes were too small for the screws provided. To address this, we used a Dremel to make holes big enough for the screws to fit properly. After we finished assembling the drone, both teams 2 and 3 faced difficulties advancing in the project because they were waiting for specific 2S and 3S batteries required for operation. Team 1 managed to successfully fly their drone initially, but encountered a setback on the 2nd day of testing when the motors caught fire, causing irreparable damage within our project's time constraints. On day 6, Team 3 faced issues with their drone's center of mass, which was unbalanced and affected flight stability. They resolved this by removing the drone's legs to regain balance and enable proper flight. Despite these challenges, we successfully got 1 drone flying by the end of the project.
We chose to test the HERA system due to the draw of a fully pre-integrated system. The HERA kit includes antennas, a controller, a GPS, and its own telemetry unit, the air unit. It had the potential to be the best of the 3 due to the fact that it had the complete integration and wouldn't require us to do any sort of connecting on our end. The air unit was the main center of the HERA system and functioned to communicate between the actual drone itself and the ground control. It ultimately failed due to an unfixable battery issue. We ran into 2 main issues while trying to get the HERA to work. The first main issue was the idea of having to get a power supply to it. The HERA required a voltage input of around 11 volts, and with our current 4S batteries, we exceeded that voltage maximum. What we ended up doing was switching the whole system over to a 3S battery, and just connecting both the air unit and its cooling fan directly into the power supply board. The second main issue was actually communicating between the air unit hardware and the Pixhawk hardware. What we ended up doing was creating specific wires that would allow us to switch between the 2 ports and actually get data flow.
The TX16S Radio Master is a versatile 16-channel transmitter widely used for controlling drones. As a transmitter, it serves as a remote control device, sending signals to the drone to execute various commands. Equipped with a large color touchscreen, OpenTX firmware for customization, and comprehensive telemetry capabilities, it offers reliability and flexibility for both hobbyists and professionals. In Mode 2 configuration, the 4 main channels control the drone's movement. Throttle on channel 3 for altitude, yaw for rotation on channel 4, pitch on channel 2 for forward and backwards tilt, and roll on channel 1 for side-to-side tilt. These controls enable precise maneuver and stable flight. In setting up the Radio Master transmitter, we encountered an issue with the transmitter configuration. We found that the throttle channel midpoint was set at 0, but a neutral position of 50 would be better suited. Adjusting the channel settings to shift the midpoint to 50 caused a high throttle warning in the Q ground control, preventing the drone from arming. Despite multiple calibration attempts, the issue persisted. Keeping the original throttle position reduced the range of motion, causing more drastic propeller speed increases with slight stick maneuvers and making the drone harder to control.
This radio link controller is an 8-channel T8S radio transmitter that features dual joysticks, switch dials, and different control modes. The radio link also comes with a RAEF receiver, which we attached to the drone so that the controller can communicate commands to it. We used this controller as a cheaper alternative to the Radio Master controller. The radio link was also quick to set up and didn't require extra batteries. The controller is more of an entry-level controller to a Radio Master.
For our software, we leveraged an open source software application called Q Ground Control. Without directly having to code our own environment for data logging or motor configuration, Q Ground Control provided easy configuration for motors and radios and MAVLink communications with the drone for live data visualization.
GPS has some inaccuracies caused by timing issues. Firstly, because the speed of light is so fast, at about 300,000 meters per second, if the sensor reads the signal even a microsecond too late, it will record a distance with an error of about 300 meters. To minimize this error, sensors and satellites must have atomic clocks, such as this one, that are capable of recording nanoseconds. Secondly, because of how fast the satellites are moving, and the relativity of time, it is very easy for the clocks in the sensors and the satellites to become unsynced. And lastly, the problem that pertains to our project the most, GPS only works with sensors that are on the surface of the Earth. This renders them totally useless in cases of location estimation inside buildings or even on other planets. Continuing from where we left off, let's dive into the Inertial Measurement Unit, or IMU, on the drone's Pixhawk flight controller. The IMU records the drone's acceleration and rotation rate relative to itself. It consists of 2 primary sensors, an accelerometer and a gyroscope. The accelerometer measures the drone's linear acceleration, detecting changes in speed in all directions. The gyroscope measures the drone's rotation around multiple axes, including pitch, roll, and yaw. Using these sensors, the IMU detects changes in the drone's position, orientation, and velocity, crucial for maintaining stable flight and executing precise maneuvers. In summary, the IMU provides essential data that allows the flight controller to keep the drone balanced and on its intended flight path.
Light detection ranging, or LiDAR, is the process of sending out pulses of light and recording the time it takes for it to reflect off a surface and come back to a sensor. With that, you're able to calculate the distance from the sensor to certain objects. For our process, we use the SlamTech A1M8, which allows us to record in a complete 360-degree 2D slice, as the actual sensor itself is able to spin. This has applications in many parts of the drone process, including both altitude measurement or object avoidance.
To demonstrate the mild inaccuracies that can occur when observing LiDAR data, and how the Kalman filter can fix them, we needed the LiDAR to observe an object from a known distance. We set a trash can 5.5 meters away from the sensor, and meticulously marked every meter between the two. Without a drone that could support our LiDAR sensor, we had to get creative. We used a cardboard box to mount the sensor to a rolling chair, and secured another piece of cardboard that reached from the side of the chair to the floor, so that we could show the sensor's exact location with markings on the ground. On the chair, we set the computer that had RoboStudio running, and using LiDAR data to record position and distance, and we set a stopwatch running to observe time of each position.
There are many ways to filter noisy data, and the primary idea behind filtering is averaging out inaccuracies within the data to predict and estimate a drone's position. Different methods include simple averaging, which is where you add all of the terms and divide by the number of terms, and this is known as a batch expression. Another way to filter is to take a moving average. When a simple average is too much to compute in a real-time onboard processor, recursive moving averages allows you to calculate real-time without storing all previous data points, because you simply update the average with each new data point instead of re-evaluating the data every time you get a new point. This way is efficient and faster. Another way of filtering is called a low-pass filter. This allows low frequency and filters out high-frequency data points, where high-frequency data point represents the noise, but each term is weighted the same. The ideal method to filter data is known as a Kalman filter. A Kalman filter is a weighted low-pass filter, where past data gets weighted exponentially smaller as new, more relevant data comes in. An important aspect of the Kalman filter is the ability to tune it to specific data sets to meet analysis needs. Here you can see the original raw LiDAR data that looks spiky even though it was tracking a linear one-dimensional data set. Applying and tuning the Kalman filter allows us to create a range of estimates by changing the noise covariance variable Q. A smaller Q value, as shown on the left graph, makes a smoother line, which makes analysis easier if you were to integrate or take a derivative of your data. However, a larger Q value, as shown on the right graph, aligns more closely with the original, noisier data, thus creating a spikier graph that more closely resembles the original data points. Here you can see a comparison of position estimation between local positioning and global positioning systems from the same flight of a drone. Notice how the Kalman filter fills in gaps and holes in the dataset. Also notice how the Kalman values appear shifted to the right of the original dataset values. This is because using the Kalman filter uses previous data in addition to current data to make its predictions and estimates.
Even though we had difficulties in the drone build process, we did have significant results. We found that the radio master controller and standard telemetry radio provided the most stable communications. By running the collected data through the Kalman filter, we achieved a noise reduction of 41% in the IMU measurements. For the LiDAR measurements, the Kalman filter was particularly effective in removing extreme outliers from the dataset, helping to create a more realistic representation of the operating environment for obstacle avoidance, especially crucial in autonomous flight systems. The Kalman filter halved the average error in the LiDAR measurements. This study demonstrates that IMU and LiDAR data refined with the Kalman filter can accurately estimate drone position. These methods show potential for position estimations in areas where the GPS reliability is a big concern.
We realized throughout the building process we had spread ourselves too thin and ran into many hardware roadblocks, leaving barely enough time to add another sensor or a coprocessor or even get to any of the data processing. So instead of fusing data together, we targeted to filter noise out of the GPS and IMU data we already had. Rather than just focusing on tuning out noise, our next steps would be to incorporate more sources of data, meaning adding another sensor, whether that be a LiDAR or a camera, and to fuse that data with our current GPS and IMU data to better find a more accurate position.
Working on the FUNPEDS and ZQ projects has given me practical aerospace experience and solidified my passion for space exploration. Interacting with NASA professionals during the SEAS internship provided critical career insights and confirmed my goal to become a NASA engineer.
The NASA SEAS intern, I was able to meet so many professionals in the field, such as NASA astronauts and researchers. Their passion for their work is so strong, whether that be Earth exploration, moon exploration, or some other planet, or just leading a team. I was truly inspired and really opened up my eyes to the different avenues in the job market. I also had the opportunity to work with an incredible team focused on drone positioning. Throughout the 2-week journey, which felt so long yet so short, I learned to look for the solutions when everything felt like it was going wrong. Thank you, SEAS, for this amazing opportunity.
For me, SEAS has been a truly life-changing experience. Not only has it reaffirmed what I want to do with my life, but having such an amazing opportunity has left me incredibly thankful. I'm so happy to have had the opportunity to work in such a caring, inspiring environment that, although challenging at times, pushed me to be the best version of myself.
My time spent in the NASA SEAS internship was a phenomenal experience that I would like to do again. The internship has piqued my interest in aerospace engineering and space exploration. It has also connected me with extraordinary people who share my passions for space exploration and engineering. This was a great experience, and I really enjoyed the work we conducted during this research project. Thank you so much for this opportunity.
Being a NASA STEM intern has been a once-in-a-lifetime experience. I've had the amazing opportunity to meet and hear from people directly involved in aerospace through the speaker series, which has been truly eye-opening. I'm so grateful as well for the opportunity to meet and connect with so many like-minded peers during my time in Austin. Working on this project with my team has confirmed my interest in aerospace engineering.
My time with the NASA SEEDS program really boosted my interest in aerospace engineering. Working on our team project taught me so many strategies and softwares that can be applied in the field. It was hands-on and eye-opening, making me even more excited to keep exploring aerospace engineering.
As a NASA intern, I have really enjoyed contributing to a real ongoing research project where our study will aid the future of commercial drone use. I've especially enjoyed learning about the graduate level math behind the Kalman filter because I was able to visualize and produce real-world applications of this math. My NASA SEAS internship has been an amazing opportunity, not only to learn from and contribute to the scientific community, but also to network and work with other like-minded peers and mentors fascinated by space and aerospace engineering.
Before this experience, I had no idea what career path I wanted to pursue. But my experience as a NASA SEAS intern has taught me so much about the specifics of and science behind much of the work that NASA does. But even more so, it's taught me how to work with other people, to troubleshoot and work around issues, and to never give up, even if it feels like all the cards are stacked against you. I am extremely grateful that this experience has opened my eyes to so many interesting job options, and specifically has inspired me to consider a career as an astronaut.
At this point, we'd like to thank our mentor, Mr. Noakes, for the guidance you offered us on this project throughout the time we were in Austin. We'd also like to thank Mrs. Baggio and Mrs. Miller for helping to manage SEAS. We truly appreciate all that you have done to make our time here such a great experience. We'd also like to thank Mr. Barker and all of the other helpers and mentors who helped SEAS run smoothly. And finally, we'd like to thank all of our fellow interns who we loved getting to meet.
Excellent job. So we want to invite the FUNPEDS team to please turn on their cameras and unmute their mics. The first question that we have for your team is, great job, fantastic presentation. How would you have designed or changed the kits that were available to you?
Yeah, I can answer that question. Overall, the kits actually worked out pretty well for what we were trying to accomplish. The main thing that was an issue for us was establishing communications. So the simplest solution to that would have been to have the kits come with their own controller and transmitter that were guaranteed to work from the start. And otherwise, the only issue that we had with the kits themselves was the quality control wasn't so great, so we had to modify the base plates a little. So the only other change that I would recommend would be a more quality control in the kits.
Great. Next question. How did you apply the Kalman filter to the raw data?
Thank you. I can take this one. So we started by learning about the Kalman filter online, and a great thing about modern technology is there are a lot of open source code resources out there. So we took a code for the Kalman filter and tweaked it based on what we needed it to do for our data. And this included changing one of the variables in the filter to match our drone's data that we collected. And then we put it all into MATLAB, which is a free coding math platform. And that's how we produced our graphs and our 3D models.
Great. What will you remember the most about completing this project?
So one thing that we'll remember the most about completing this project is the hard work and perseverance that we put into this project on the last week, trying to get the data and figure out the Kalman filtering. I will also want to note that another thing that we will remember is that when we did get that first drone flying, not only did we crash it, but it also caught on fire. So I think we're going to remember that.
Yeah, and then also if I could just piggyback off of that, I'm so grateful to seize opportunity. And what I really liked from this project is I was able to actually merge my passion of engineering and data science into one project. So it gave me that practical research experience with
merging my two passions.
Great. If you could redo the project, would you have done it with only one drone from the start?
I can take this question. I think we actually discussed this at one point, and I think we're all pretty much in agreement that the knowledge that we got from breaking up into 3 groups and testing 3 different controllers was extremely crucial. And even though we ended up only successfully getting one flying, the things we learned from the 2 failed controllers were really helpful in eventually getting that one drone flying. So I don't think that we would go back and only use one.
And why did you have to manually record the LiDAR experiment results as you did?
So I can answer that question. So we spent a long time working with the actual LiDAR sensor itself, as the computer program that it came with didn't allow for actual individual data recording of a certain time. So we spent a while trying to look at some back-end processes of actually getting real-time data measurements, but we weren't able to contact the manufacturer for the certain activation codes we needed. So we ended up having to just do the best with what we could and just manually record the data.
Great. Well, you did an excellent job with your project. I knew you had some big challenges to overcome, and obviously as a team, you were able to do that. So congratulations. We're going to take a 20-minute break. We will invite you to watch the video that's highlighting Python coding projects, and we will reconvene at 3:10 for session 3. So I want to say welcome back to session 3. We will continue with the SEAS Science Symposium with the Age and Distance to an Open Cluster team led by Olivia Cooper, a teacher in Greenville, Tennessee. She serves as a NASA Solar System Ambassador, an active member of the Bays Mountain Astronomy Club, and a member of the University of Texas at Austin's Astronomy Group. Here is the analysis of open cluster NGC 4815 stars to determine their age and distance.
Good afternoon, everyone, and welcome to our presentation on age and distance to an open cluster. I am Aminatu, and I'm thrilled to have you here today. This project has been a collaborative effort, and I'm proud to introduce my dedicated team members who have contributed significantly to our research.
Hi, my name is Saksham Agarwal, and I attend Walnut Grove High School.
Hi, my name is Abhay Bhaskar, and I attend the Edison Academy Magnet School.
Hi, my name is Derek Chang, and I go to Round Rock High School.
Hi, my name is Kedar Kashyap, and I attend Leland High School.
Hi, my name is Amina Tusay, and I attend Mara High School.
Hi, my name is Ayush Tripathi, and I attend Hillsborough High School.
Hi, my name is Shreya Valluri, and I attend South Brunswick High School.
Before we begin, I would also like to have a huge thanks to our mentor, Dr. Cooper, who has been an invaluable guide providing us with expert insight and support. Now, let's delve into the background information about open clusters. So, what are open clusters? These are a group of stars that are loosely held together by gravity and were born from the same cloud of gas and dust in space, which is known as a molecular cloud. The size ranges from a few dozen to a few thousand stars. Over time, the stars in the open cluster slowly move towards each other and may disperse after a few million years. These clusters are important in astronomy because they give us a chance to see stars in different sizes and stages of life, all at the same age and made from the same material. Also, because the stars in the open cluster are similar in age and chemical composition, astronomers can use them to check models of cellular evolution and ages of stars. Characteristics of open clusters. Stars in open clusters are primarily held together by mutual gravity within the system. As noted before, this leads to relatively weak gravity, and as a result, most stars in the system will disperse after a few 100 million years. Open clusters have both young and old stars, but because of the weak gravity, the stars typically are less than 1 billion years old. Since open clusters are relatively young compared to globular clusters, they consist largely of blue stars, which are associated with higher temperatures. Stars in the open clusters are also typically in the main sequence of a Hertzsprung-Russell diagram, which is shown here to the right.
So now diving into the open cluster that we examined in this project, it was NGC 4815, which is an open cluster in the Musca constellation. And this open cluster can be viewed from the southern hemisphere if you're using powerful binoculars or a telescope. And one of the most important things about this cluster is the fact that there's not been a lot of recent research into it. In fact, the most recent study into this open cluster was almost 3 decades ago. And since then, obviously, there have been major leaps and advances in the data available and also the technology that we could use as a team. And this allowed us to get a more accurate information about the age and distance of this open cluster. So the telescope that this data came from was from the Southeastern Association for Research in Astronomy's telescope in Cerro Tololo, Chile. So you can actually see in 2 of the images, one of which is actually on this mountain in Chile, and the other shows a little bit more of the inner workings of the telescope. And then furthest to the left, you can see an image of the actual open cluster. But actually just diving into a little bit about the problems that the telescope faces, one of the main ones is the fact that there's a lot of gas and dust that can obscure the open cluster from the view of the telescope, and we'll actually discuss a little bit later about how we accounted for this and attempted to mitigate it. Also, high humidity and precipitation can lead to water vapor forming on the lens, which can cloud the view that it gives of the open cluster, and also a balance between getting a bright enough image and a sharper image, because as there's a narrower aperture of the telescope, the resolution of the image will increase because less light is able to enter, so there's also less blurring because of light diffraction. But the problem that arises because of this is that since less light is entering, sometimes the image might have an artificially low amount of light. So it's really this balance between two factors that have to be managed with telescopes.
Now that we've set the goals and the context for our situation, let's understand what's the key important concept to finding more about the open cluster, and that's through photometry. Photometry is the measurement of the brightness of stars in the pictures, essentially looking at pixels and trying to calculate how bright they are so we can learn more about the stars. We have to apply a concept called filters. For instance, if I put a blue filter over a large amount of stars and they tend to be in the red star range, it's going to come out very dim. But if I change the filter towards a red filter against the red stars, it's going to be a lot brighter. And shown in the ResearchGate image, we can see that based on the filters, you're going to see different kinds of brightness for different types of stars. Because we're mainly targeting hot and young stars, as explained before, you're going to use the blue and greener visual filters to see NGC 4815. And finally, the last niche part is our calibration. As we're using not only flat and dark files, we're also going to be using many different flat calibration files that can make it very easy to understand and also get the best measurement for the flux and brightness. But to go from here, when we're analyzing the region of sky, it wouldn't be efficient for just one of us to look and do the photometry for the whole section. So instead, we split NGC 4815 into 7 key regions and did analysis for over 257 stars out of the 8,500. We used the software of AstroImage-J with the calibrated B and V filters, and we targeted the stars for their magnitude and calculated the B-V value, which can help us understand its color index. This is our B-V collected data.
So after we had collected the photometry data, we classified all 257 stars in the open cluster according to their spectral type. Stars are classified mainly in 5 ways, which are surface temperature, luminosity, chemical composition, mass, size, and age. Based on these factors, the spectral type of the star is identified. The spectral types are O, B, A, F, G, K, and M, where O has the highest luminosity and M has the lowest. Classification of stars can be summed up into the Hertzsprung-Russell diagram, which measures a star's luminosity in relation to temperature, spectral class, or color. The HR diagram is important when astronomers are charting the lifestyle of a star, and it helps classify stars by spectral class in open clusters. In our study, we measured the stars B-V values indicating their color magnitude. And using this magnitude, we checked which color indices it was in between, given a reference sheet, and we could easily classify the stars. Additionally, the main sequence stars are the stars that show up on the diagonal line of the HR diagram, and they represent the majority of the stars in the universe. And this is called the main sequence, where the stars spend most of their lives. Also, what's important to know is the zero-age main sequence, also known as the ZAMS line, which is the time when a star first joins the main sequence on the HR diagram. And this helps us to identify the age of an open star cluster.
From our analysis of the photometry, we found that there are predominantly B stars in NGC 4815, but due to the lack of finding no O stars in the cluster, we estimate that it is at least over 10 million years. And despite being in a very hot cluster, we were also able to find 2 M stars, which are incredibly dim when compared to the B or A stars. We also got a good sample of the sample G type stars, which is just like our sun.
So over here on this graph, you can take a look at our initial color magnitude diagram. And as you can see, our ZAMS line is very far away from our initial recordings of our stars. And this is largely due to a phenomena called reddening. And what reddening is it's a phenomena that occurs when starlight appears more red due to the scattering of light. To further explain this, we can take a look at this diagram on the right, where a distant object will produce blue and red light. And since blue light has shorter wavelengths, it is more prone to scattering from dust and other space material, whereas red light can get through it much easier. As a result, starlight will appear more red to an observer, where in reality it is actually consisting of more blue. So to do this, we have a reddening value, and our image of NGC 4815 had a reddening value of 0.808. And it is important to note that this is actually a relatively high reddening value. And so in order to correct for reddening, we use two formulas that are shown on the below. On the left, we have our true color index, which is our B minus V. And then on the right, we have our magnitude, which is our V filter.
So as previously mentioned, we had to correct each star's V and B minus V value for reddening due to the fact that there was an abundance of space dust which can scatter the light emitted from each star. By correcting the V and B minus V values, this gives us our true color index and our magnitude for each star. And as a result of the correcting, we ended up finding that the stars present in NGC 4815 had a very similar color index. Through our photometry, we noticed that this open cluster consisted of primarily young and bright B-class stars. And initially, this wasn't exactly what we expected because there wasn't that many stars that deviated from the data trend. So what we decided to do was to perform additional photometry on other faint and bright stars that were present in the cluster. And we still noticed that that NGC 4815 primarily consisted of B-class stars, and this led us to believe that NGC 4815 is a relatively young cluster with a lot of space dust in between, which would make sense. Which would make sense because there aren't that many old and faint stars present.
And so what does all this data and analysis tell us? Well, by using the B minus V corrected value and the corrected V magnitude of a reference star, we are able to use the distance modulus equation as shown above to get an estimate of the distance of NGC 4815 from Earth. However, since we did not know the absolute magnitude of any star, we use the absolute magnitude of the Sun for the capital M value and use stars similar to the Sun, or class G stars, for the lowercase m value. But when we use the two stars with the closest corrected B minus V value to the Sun, we got two very different estimated distances, as you can see in the second bullet point. To combat this, we decided to estimate the distance by taking the mean of the estimation across all class G stars. And by doing this method, we were able to get an estimate that NGC 4015 is approximately 426 parsecs away from Earth. And what about the age of NGC 4015? And so first we have to talk about a turnoff point. And a turnoff point of a cluster is when the majority of the stars in the cluster begin to deviate from the main sequence relative to the ZAMS line as shown in the graph below. This point is used to determine the cluster's age, as the cluster cannot be older than its oldest member star. Since the turnoff point is about B minus V is approximately 0.1, this implies that the oldest member stars have a B minus V of 0.1, which classifies them as an A-class star. This in turn indicates that NGC 4015 is about the age of an A-class star, or about 400 million years old. And please note that all V corrected values were shifted down by 8 units to correlate with the ZAMS line.
From this project, our most important takeaways were how to use photometry on a telescope image to find the age and distance of open star clusters, and to contribute to furthering research about stars, and especially provide newer data about open cluster NGC 4815. As 2024 sees interns, our highlights of the program were collaborating as a group and forming new connections, having subject matter expert Olivia Cooper as our mentor, learning how to use software applications like AstroImageJ, Google Sheets, and Excel, and taking away key research skills and workplace experience. Some of our challenges were trying to overlay our ZAMS line onto our main sequence stars data, because we were originally working with our data on Google Sheets, but we found more success after pivoting to Excel. And additionally, our data did not turn out as we expected, as we mentioned some of our errors and ways we tried to fix those earlier. But at the end of the day, science may not always turn out as we expect it to, because it's all about trial and error and the process of investigating for new discoveries.
And so reflecting on the city's experience as a whole, SEAS has been an amazing, unique experience. I have learned what it's like to conduct authentic scientific research and how to work with others from around the nation to further our knowledge of space. SEAS has broadened my view of what is possible for me to achieve in post-secondary education.
Participating in NASA SEAS program was a transformative experience that significantly heightened my appreciation for space exploration.
SEAS has been an incredible opportunity for me to do unique scientific research and add to the body of knowledge regarding astronomy and open clusters. SEAS has shown me what it's like to do research in a group, and it has also expanded my interest for my secondary education.
SEAS has provided me with an amazing opportunity to experience what space science is all about. Being able to conduct hands-on research with a team of peers has provided me with a memorable and valuable experience of how fun and challenging research can be.
NASA SEAS has given me an invaluable opportunity to explore the evolving field of space science. I've enjoyed working with driven peers, gaining important research skills, and broadening my perspective on space research into my future education.
Participating in SEAS has enabled me to engage in scientific research within astronomy for the first time. Through the program, I've collaborated with talented peers from across the country, exposing me to new ways of thinking, techniques, and this fascinating field.
Working at SEAS has taught me many new concepts in such a short time, drawing my interest into various fields of astronomy. It was incredible to participate with a great group of high schoolers, solving problems and finding unique solutions.
These are the references.
So we invite all members of the Open Cluster team to turn on their cameras and unmute their mics. We have several questions for your team. What types of challenges did you encounter as a virtual team for this project, and how did you overcome them? So anyone on the team that wants to answer?
Yeah, I can answer that question. And so probably the biggest problem we had as a virtual team was getting everyone to be on the same page, especially when dealing with problems in our data. Like whenever we had to redo certain data or have to choose like what time our next meeting was, it was difficult finding a time that worked for everyone because we were spread across all different time zones and not everyone was available at the same time. And so we overcame this primarily by getting used to working on our own and knowing what our job was at a specific time, even when we weren't directly communicating with one another. And so just like having a higher degree of independence was critical for this. And we would also do things such as like leaving notes on our shared data to know where someone left off or what they had previously worked on when contributing to the work.
So did you use Google Docs, or how did you communicate?
Yeah, we used Google Sheets primarily for our data collection and our data analysis. And then sometimes we would just like type things whenever we worked on something like, hey, I did this. Could someone else maybe tackle this part of the data and things like that?
Perfect. Next question. What made you choose this specific open cluster to study?
I can answer that. That's a great question. The main reason we chose this cluster is because it's very understudied, as the last study was 3 decades ago. We also wanted to study it with new technologies, as advancements have been made since the last time the cluster was studied. And lastly, this cluster stands out due to its potential role as a tracer for the abundance gradient, which is a feature that could shed light on the distribution of elements across the galaxy.
And what about their shorter wavelengths makes blue light from stars more susceptible to scattering than red light?
Yeah, I can take this one. So blue lights have shorter wavelengths, and so when shorter wavelengths encounter smaller dust particles, they're more likely to bounce off of them because they're more similar in size to them. And it's also why like our sky is blue, and it's because the shorter wavelengths can encounter dust more easily, and that's why they can bounce off or diffract quicker or easier.
Great. You did an excellent job with your research, and thank you for sharing it. So the next presentation comes from the solar eclipse impacts on weather, a citizen science approach, NESEC and Globe Mission Earth project led by Dr. Kevin Jakowski and Olawale Femi. So the first presentation, we'll have 3 presentations in this group and questions at the end of those 3. The first presentation is Solar Eclipse Impacts on Air Temperature and Sky Visibility.
Hello, I'm Isabella Quimino, and today I'm joined with my team member, Kaylin Cervantes. Today we'll be discussing solar eclipse's impact on air temperature and sky visibility.
A solar eclipse occurs when the moon passes between the Earth and the Sun, temporarily blocking the sun's light. There are 3 main types of solar eclipses: total, partial, and annular. On April 8, 2024, the United States had a solar eclipse in which all 50 states either experienced a partial or total eclipse. This eclipse was unique because the path of totality, where the moon completely covered the sun, stretched across several states from Texas to Maine.
Our goal is to study the impact of the April 8, 2024 eclipse in 2 counties, one experiencing a total eclipse and the other experiencing a partial eclipse. By comparing these locations, we aim to understand how the eclipse influenced the air temperature and sky visibility in each of these counties.
The 2 areas of study will be Baltimore, Maryland, which had a partial eclipse, and Dallas, Texas, which had a total solar eclipse. After we figured out the locations of research, we then had to figure out what tools were we going to use to research. We then realized that ArcGIS Online, Globe Observer, and Excel were perfect for what we were going to try and do. We utilized ArcGIS Online to create a map of the data obtained from Globe Observer, and then we downloaded the data from Globe Observer for our research, and we used Excel to process the data from Globe Observer and made graphs out of the data.
During a solar eclipse, the extent of the eclipse will impact air temperature and sky visibility. In the case of a total eclipse, it is expected that the air temperature will decrease more dramatically compared to a partial eclipse, as the complete blockage of sunlight leads to a more pronounced drop in temperature. Sky visibility, on the other hand, will decrease to the point where mist stars may become visible. In contrast, during a partial solar eclipse, although the sky will dim noticeably, it will not become dark enough.
The graph above shows the data collected from the day of the eclipse. The black box highlights the general time of the eclipse, and that's why there's such a dramatic drop in the data. This graph is a zoomed-in version of the black area highlighted previously. The black line on the graph shows the average of the data. We noticed that there was a 4 degrees Celsius drop in the temperature.
The total solar eclipse in Dallas, Texas happened at 12:23 p.m. and its maximum was at 1:42 p.m. The lowest temperature was 24 degrees Celsius, the highest temperature was 28 degrees Celsius, and its average temperature was 18 degrees Celsius. All the data used in our research is from the Globe Observer.
This map is also a representation of the different air temperatures in Dallas during the eclipse. This scatter plot is a representation of the exact time the solar eclipse happened in Baltimore County. I also included the air temperature 30 minutes before the eclipse to see if there was a drop in temperature once the eclipse started. As stated before, the time of the eclipse was from 2:05 p.m. to 4:33 p.m., with the eclipse reaching its maximum at 3:21 p.m. The lowest air temperature during the eclipse was 15 degrees Celsius at 2:46 p.m. That highest recorded air temperature was at 21.6 degrees Celsius at 4:20 p.m. Baltimore County's eclipse had an average degree of 20.2 degrees Celsius throughout the eclipse.
This chart shows the data collected from the day of the eclipse, on April 8th, 2024. The chart shows that there was a bit of a haze during the eclipse. The reason why there was a slight haze is due to the fact that the temperature dropped, which can lead to the formation of water vapor, which can cause a haze in the atmosphere.
For sky visibility, there was not enough sufficient data in Baltimore, Maryland, so everything within a radius of 99.3 kilometers was used when measuring sky visibility. Results. The results for air temperatures suggest that the type of eclipse, partial versus total, plays a significant role in influencing local air temperatures. The partial eclipse in Baltimore allowed more sunlight to penetrate through the atmosphere compared to the total eclipse in Dallas, resulting in higher temperatures in Baltimore. The total eclipse in Dallas led to a more pronounced reduction in solar radiation, causing cooler temperatures throughout the event. This study highlights the importance of understanding the climatic impacts of solar eclipses, which can vary significantly based on the extent of the eclipse observed. Upon comparing our findings, we discovered that the sky is approximately 16% clear during the partial eclipse and during the total eclipse. This observation confirms our hypothesis, as we initially predicted that sky visibility would be clear during a partial eclipse. The sky is hazier during a total eclipse because of the temperature drop, which can lead to a cooling effect.
We had the unique opportunity to conduct our own research project and come up with a topic of our own, and we were also introduced to vital data tools such as Globe Observer and ArcGIS, and we used those tools to create datasets. We worked with business professionals who helped guide our research.
For me, participating in SEAS has enhanced my research skills and deepened my understanding of solar eclipses. Through hands-on projects such as this, I have gained valuable experience in data collection and analysis and interpretation. Learning to use advanced tools like Globe Observer and ArcGIS has equipped me with practical skills that are essential for scientific research. This internship has not only enriched my knowledge in earth science, but it has also enhanced my confidence in conducting independent research.
I truly enjoyed getting to learn more about climate change, solar eclipses, satellites, and earth science. I felt like being able to speak with real NASA scientists made the experience even more interesting. I was able to apply the skills that I had learned before this internship, like communication and time management, to this experience. I felt like this internship helped me realize that no matter how impossible something might seem, there's always a way to figure it out.
Thank you to our solar eclipse impacts on weather mentors and our CSRC staff. Thank you to Mr. Oluwafemi Alawale, Kevin Sakauki, and Grant Wilson.
So we will hold questions until all three have completed. Here is the research from the Exploring the Effect of the Solar Eclipse on Wind Speed and Direction in Texas using a comparative diurnal analysis of eclipse wind.
Hello, everyone. My name is Bill Shu.
And I'm Sahar Shidabani.
Explore of the solar eclipse on wind speed and direction in Texas using a comparative diurnal analysis. The solar eclipse is a rare event where the moon blocks the sun, causing quick changes in solar radiation and temperature. This gives us a unique chance to study how the Earth's atmosphere reacts. One specific thing we looked at is the eclipse wind, where these changes affect wind speed and direction. Understanding the eclipse winds could help in studying how rapid changes in solar radiation affects weather patterns and atmospheric dynamics.
Our main research question is, how does the solar eclipse affect wind speed and direction along the path to totality in Texas? We explored this by comparing the eclipse day to the week around it. We use data from the GLOBE program, which promotes earth science understanding through data collection. Our dataset included 9,118 observations from 15 sites over 9 days. 8 surrounding the day of the solar eclipse, and 1 day of the actual solar eclipse, focusing on wind speed and direction.
This map shows where we collected data across Texas. Many of the points are within the path of 100% totality, and most of the others are within 90% totality.
We collected data on wind speed and direction for 8 days around the eclipse. We cleaned, filtered, and converted the data from Central Standard Time to UTC, Universal Time. Using the clean data, we graphed the wind speed and direction of the average diurnal variation against that of the day of the solar eclipse. Then, to analyze the graph and the data, we did t-tests to compare the eclipse day with the weekly average, helping us determine whether conclusions could be made from the differences or if it was a null hypothesis, which would be that there was no correlation, there was no significant difference between the wind speed and direction on the day of the eclipse compared to the average diurnal variation days. Some of the tools we used for this were the GLOBE dataset in the bottom left corner, Matplotlib, NumPy, and Pandas, which are all Python libraries, and Python, the programming language Python, and SciPy to help us do statistical analyses and t-tests on our data.
So these graphs compare the mean wind speed and direction on the eclipse day with the average wind direction and speed over the rest of the week. The top graph shows significant differences in wind speed, ranging from 0.4 to around 1.4 meters per second. The bottom graph shows notable variations in wind direction, where the average wind direction shifts from southeast to east of southeast.
The t-test results for wind speed showed a significant difference between the eclipse day and the weekly average, with a t-statistic of 20.3 and a low p-value. This means that the eclipse had a noticeable impact on wind speed, as the high t-statistic and p-value that is under 0.05 indicates that the results are statistically significant compared to regular weather patterns. The t-test results for wind direction also showed significant differences, with a t-statistics of 11.8 and a p-value of 3.91 to the negative 31st power. This also means that the eclipse had a noticeable impact on wind speed, as the high t-statistic and p-value that's under 0.05 indicates that the results are statistically significant compared to regular weather patterns.
In conclusion, our study found significant changes in the wind speed and direction on the eclipse day compared to the weekly average. The t-test results confirm that the solar eclipse do impact these variables, allowing us to reject the null hypothesis. These findings suggest that the solar eclipse can cause noticeable variations in wind patterns, likely due to the cooling effect of the eclipse, which stabilizes the atmospheric boundary layer. Understanding these changes can help improve weather prediction models and contribute to the broader field of atmospheric science. The observed changes in wind patterns provide valuable insights into how transient events like solar eclipse influence local weather conditions, enhancing our predictive capabilities and knowledge of atmospheric dynamics during such rare events. Here is our abstract. And I really enjoyed the C-SCAN because I learned a lot from the instructors. I gained a lot of experience in data analysis, especially in studying the wind patterns during the solar eclipse. The project and activities helped me understand atmospheric science better, and using advanced tools like ArcGIS and the Globe database was really fun. Working with mentors and peers made this experience really enriching.
The SEAS program was an amazing experience. I worked with significant data sets like the Globe Observer database, contributing daily to cloud cover and temperature data. Collaborating with driven interns in the solar eclipse impacts on weather group was inspiring, culminating in a research project that showcased our dedication and excitement. Lastly, we couldn't have done this without our mentors. We want to express our sincere gratitude to Dr. Oluwafemi, Dr. C, and the NASA guest speakers for their invaluable guidance and support throughout this project. We also want to thank the NASA SEAS program and all the instructors for providing this incredible learning opportunity. Thank you.
Excellent. So our next presentation is on analyzing the impact of solar eclipse on solar energy.
Hello, NASA staff and NASA interns. My name is Jaden.
I'm Ethan.
And our theme is analyzing the solar eclipse effect on energy generation. Our research topic is what effect, if any, does the solar eclipse have on solar power generation, and to what extent does it affect the solar power generation in the state of Texas? Our exigence was the increased interest in solar energy, as well as the need for effectively preaching the importance of solar energy.
Our research area is the state of Texas due to its extensive data and being covered fully by the solar eclipse. As you can see here in the data, the total solar eclipse and the 90% totality perfectly covers the majority of where our data set is providing the data for. The data source we used is the Electric Reliability Council of Texas.
So for our analysis process, we were conducting 3 t-tests for a difference of means. The first t-test was conducted using solar power from the 30-minute interval in which the April 8th solar eclipse was occurring, and it compared that to values for 30-minute solar power generation throughout the month of April. The next t-test was conducted using the total solar energy generated from that day and comparing it standard daily values for solar power generation, and the final t-test was conducted to compare the daily energy generation in all forms, such as gas or biomass, during the solar eclipse with the daily energy generation on normal days to see if any energy lost during the solar eclipse was compensated for. The results were evaluated on a basis of their p-values and standard deviation. So tests 1 and 2. Test 1 was testing for the difference in solar power generation for a 30-minute interval. The null hypothesis was the solar generation within the 30-minute eclipse interval would be the same as the solar generation within 30-minute normal intervals. The alternative hypothesis, however, was that the solar generation during the eclipse interval would be lower. The conditions were all met except for the large sample size, which was n equals 29. N equals 30 is usually considered.
Hello, NASA staff and NASA interns. My name is Jaden.
I'm Ethan, which was n equals 29. N equals 30 is usually considered a large sample size, but for our case of studying, and since there were no significant outliers, n equals 29 is sufficient. So for some results, we conducted the t-test and it was deemed statistically significant with a p-value of 9.99 e to the negative 16 and a standard deviation of 1.7 thousand megawatt hours. Now, as you can see here, this is a very significant p-value, so it would have been impossible for this to occur under normal influence. Test number 2 was testing for the difference in daily solar power generation. The null hypothesis being the daily solar power generation is the same, and the alternative hypothesis being that the solar power generation during the eclipse was lower. Now, the conditions were all the same except for the large sample size. This time, there were a few outliers, likely on either cloudy or rainy days. The results were still statistically significant. However, it was with a much higher p-value. This standard deviation was a lot greater, but this is total for the day, so it makes sense. And since the p-value was a lot greater, and as we can see on the graph, it was a lot closer to the middle, so it would be a lot more likely to happen under standard conditions. However, this is still a statistically significant result. In conclusion, for both tests, we are able to reject the null hypothesis and state that our data favors the alternative hypothesis, suggesting that the solar eclipse has a negative effect on solar power generation on both a 30-minute interval and daily level.
Now, as for total energy variations, our null hypothesis for total energy variation was that the daily energy generation is the same as the daily energy generation during a solar eclipse. And our alternative hypothesis was if the daily generation during the solar eclipse was lower, with our conditions mostly met with it being a random sample and one off from large sample, but that's close enough because of how extreme our result was, and it being an independent sample.
We could use t-test.
We got the result of p-value being 1.179 to the 10 to the negative 7th power, and our standard deviation being 77,187, meaning it's statistically significant. As a conclusion, we reject the null hypothesis. This data suggests that the total energy generated during the day of the solar eclipse is less than the energy generated on other days. This may mean that despite the lack of solar energy on April 8th, the state of Texas did not compensate for the energy lost.
So on to our final statement. So for our research conclusion, from this research, we learned that the solar eclipse of 2024, that there was a significant decrease in energy generation throughout the state of Texas. Solar energy generation was first notably lower, and this may have also led to decreased overall energy generation. We also noticed that this energy lost in the solar form was not particularly recuperated by increased energy generation in other forms, such as gas or biomass.
These were the ups and downs for us in this program.
Now on to our personal reflections. I'll start. NASA SEAS has made a big impact on me so far. I mean, throughout NASA SEAS, I've learned how big of a difference NASA makes and how many fields NASA studies just besides space. I've also learned about the history, its missions, and it has changed my perspective of the world entirely. As for how it might impact my future, well, throughout this research, I've learned a lot about data analytics, managing data, communication professionally, and all of these skills that I've learned from this project will definitely help me, especially since I'm planning to study environmental sciences in the future.
And as for me, as an aspiring engineer and a science enthusiast, this NASA internship reinforced my passion for science as well as giving me new perspectives on the climate and the environment. This program grew my interest in environmental science and aerospace, and I hope to use this experience in my future engineering journeys. And with our final statements, we would like to thank our mentors, Mr. Femi, Mr. C, Mr. Grant, as well as Globe Mission Earth for their great leadership and guidance. We would also like to thank our supportive teammates for their constructive feedbacks and engaging discussions. Thank you.
So we'd like for all three teams to please turn your cameras on and unmute your mics. So we have a question for team 1. Was the temperature different just during the eclipse time, or was it throughout the day?
There was a significant temperature shift during the eclipse time.
And why did you choose to study the April 8th solar eclipse compared to other eclipses that have happened in the past?
I can answer this question. I think we just thought it would be a bit interesting to see a recent eclipse and have data that was recently imported onto Globe Observer. So we can just, whereas the last eclipse that happened in the US was from 2017, we can actually look at more recent data from a few months ago instead. So
great. Team number 2, do you have any wind data for non-total eclipse?
Yeah, we had a few locations that were within around the 50% and even further less percentage totality. We got wind data from there, and then compared it to the day of the solar eclipse. And then we also used other days surrounding the solar eclipse where they didn't have the same blasting effects of the solar eclipse itself. So then those used as the regularized wind data standards controls essentially.
Another question for team 2. What might be an application for the data you have collected? In other words, can you use this data to explain or inform some other phenomena? Anyone from team 2?
So this data, it can be used to help gain a better understanding of how the wind responds to solar radiation changes and stuff, which can better allow us to predict weather patterns during times that aren't eclipses as well.
Great. Team number 3. Why did you use Texas data compared to other parts of the US?
We use go.
Okay, yeah, sure. We used Texas because, first of all, it was in the path of totality on the most recent total solar eclipse. And the data that we found was actually really useful, precise, real-time data. It included solar power generation and other power generation in other forms like gas and biomass within a 15-minute interval. And with that, we were able to just zone in on exactly the interval in which the solar eclipse was happening, and that helped us a lot. Also important to note, on one of our slides, we had this comparison slide, which included this schematic of the path of totality in Texas and the data source that we had in what fields it studied, and it was almost a perfect coverage of both. So our data set really basically had everything that the solar eclipse affected.
And also for team 3, is there any other data you would have liked to have collected?
I think if we could have specified on the region, let's say Texas, not just Texas, but Houston or Dallas or a specific city, and analyzed the change there, then it would have been more precise because we had to mix in data from 90% solar eclipse and totality, like we mentioned in the video. So we could have made it really specific and even compared 90% totality to 90% solar eclipse to a totality. But besides that, I think we had enough sufficient data to work on this.
Great. So you all did an excellent job. We appreciate your research. We'll be moving now to our next team, which is the Urban Heat Island Globe Mission Earth Project, led by Dr. C. and Tanzia Ahmed from the Department of Geography and Planning at the University of Toledo. We will have 3 presentations followed by Q&A. The first research team's presentation is on analyzing the relationship between urban energy consumption and the urban heat island effect.
Hi, this is Analyzing the Relationship Between Urban Energy Consumption and the Urban Heat Island Effect by Michael Raziel and Jason Liu. To start off, the urban heat island effect is the phenomenon in which urban areas experience significantly increased temperatures when compared to surrounding areas due to human development. Land surface temperature is the measure of the heat emitted from the surface of the ground. This type of data is important as it aids in urban heat island identification. Energy use intensity is a metric that is utilized to determine the energy efficiency of a building. It is calculated by dividing the annual energy consumption of a building by its gross floor area. The lower the energy use intensity, the more efficient a building's energy use is. Energy star score is the metric that takes into account the operations of the building in order to determine its energy consumption. The higher the score, the better the energy performance. This project aims to define the relationship between urban heat islands and the energy consumption of buildings. By analyzing the relationship between LST and EUI, we can better understand the factors to take into account when studying the urban heat island effect to more accurately model the effect and its plausible solutions. In this study, we had 2 main research questions. The first is, how does energy consumption in areas affected by the urban heat island effect compare to energy consumption in areas less impacted? And the second is, how does energy efficiency of buildings around New York City impact the urban heat island effect in the areas around those buildings? And here are 2 related papers to our research. The first is Urban Heat Island Impacts on Building Energy Consumption, a review of approaches and findings. This is a meta-study on the causality of UHI in urban settings on energy consumption. Since cooling technology requires energy, UHI leads to energy consumption. The second is Residential Cooling Loads and the Urban Heat Island Effect, the effects of albedo. This study investigates how increasing the albedo of surfaces can reduce the urban heat island effect, lowering energy demands that result from residential cooling. They suggest that surface reflectivity is a factor in cities that can help decrease energy consumption.
So for this study, we decided to use New York City as the study area due to its proximity and the extent of its available data. We used 2 main data sources. The first one was the Google Earth Engine. In the Google Earth Engine, we extracted LST data from New York City from the summer data from 2022 in order to avoid seasonal temperature variation and cloud coverage. We also used the NYC Open Dataset for EUI. We specifically used the 2022 NYC Open Data Property Dataset. Weather normalized source EUI was utilized as the energy metric, as it takes into account as many confounding variables as possible. This metric adjusts the energy use of a building based on typical weather conditions. We also used the Energy Star score to measure the energy efficiency of a building. After we had the data, we loaded it into ArcGIS. Using the geographic coordinates that each dataset provided, we were able to map the EY plus Energy Star score and the LST as 2 distinct layers. We then conducted a spatial join in ArcGIS to merge the 2 layers based on geographic proximity. The 2 graphs below show the LST and EUI, and the graph to the right shows the combined layer. We were able to extract this layer as a single CSV file with the paired LST and EUI based on the geographic coordinates. We loaded the CSV file into SPSS and got rid of any missing values. After cleanup, we were left with a sample size of n equals 5,284 viable coordinate location for each variable. We then conducted 2 bivariate correlation analyses, EUI versus LST and Energy Star score versus LST, to test whether these variables had significant relationships. So these are our findings. There is a significant positive relationship between the LST value and the EUI value for properties in the NYC area. As you can see, the Pearson correlation has a correlation of 0.59 and a significance that is less than 0.01, showing a significant correlation.
Our second finding is a significant negative correlation between the ENERGY STAR score and LST of a building. This indicates that the overall efficiency of the building's operations are also directly impacted by the overall average land surface temperature of its location. Again, we have a Pearson correlation of negative 0.56, which is a significance of less than 0.01.
All right, and in this study, there were several limitations. The first is that the Google Earth Engine CSV coordinates didn't match the exact location of the properties, meaning estimations had to be made for the locations. The joint, therefore, had to be defined by the closest rather than the exact location. Additionally, this study was conducted only in New York City, so it cannot be generalized to other urban areas or the general relationship between EUI and LST in urban areas, just New York City. This study cannot completely account for other factors that may affect energy consumption. For example, different buildings use types have different energy needs. Although the EUI is weather normalized, the LST dataset was for the summer months while the EUI dataset was annual, possibly causing other factors to influence the study's results. In conclusion, there is a correlation between the EUI and LST of areas within New York City. This indicates that the urban heat island effect has a direct impact on the energy consumption of buildings in the area. This likely is due to the increased heat the effect has, which leads to increased energy usage on cooling measures. Properties that are impacted by urban heat islands are therefore less energy efficient. To continue this research, we can take into account measures that reduce energy consumption, such as LED lighting, and the impact that the reduced energy consumption has on the average land surface temperature. We thank the NASA SEAS program for the opportunity to use real-world data and the guidance of field experts in studying the urban heat island effect. The mentors, guest speakers, and directors all were crucial in helping us reach our potential as young researchers. This hands-on experience taught us the importance of critical thinking and problem-solving in research beyond just understanding software. We developed essential skills for research, which we are eager to use in the future. And here is the abstract for our entire thing. Thank you.
So the next team focused their research on various colors of urban greenery and man-made materials effect on surface temperature.
Hi, my name is Chong, and this is Mithun, and we are studying how various colors of urban greenery and man-made materials affect the surface temperature.
Now imagine this. You're walking outside Belfort. You walk on the tan sidewalk and your feet are just boning. You walk towards the green gas and your feet are cooling down. But the moment you step on the black asphalt, the road, you recoil in pain. The ground here just scolds your feet, while the grass right beside us. Now, why is this?
Now, this is due to the urban heat island effect, which is when a metropolitan area is a lot warmer than the surrounding areas. There are some factors that affect the UHI, including reduced vegetation, material properties, dark surfaces, urban geometry, etc. And colors can play a big role as they can minimize or maximize the UHI. Scientists can use satellites, infrared thermometers, and local weather stations to measure UHI.
Now, before conducting the study, we went through some literature, popular literature, and what we learned is that some of the things we learned is that one, vegetation can bring down air temperature using either transportation, and trees tall vegetation and can also bring down surface temperature while also providing shade. And for another source, we realized that the effectiveness of methods to reduce UHI effect with greenery can often depend on local characteristics and changes from area to area. And from another source we found a lot of background info that was crucial to learn about the albedo effect with the color of buildings with the UHI effect.
So some goals and questions we wanted to answer was how to determine how color of plants and buildings affect the UHI, and also create a scale to see which colors create the highest and lowest temperatures. Some questions we wanted to answer included: how does local greenery affect the UHI compared to the color of buildings, and which colors for plants and buildings have the biggest impact?
Now, we had two hypotheses before starting. One of them being that darker shades of color or on the light spectrum have higher temperatures, such as black having as darker is the higher temperatures it has, and overall that the red objects that are red will have the least heat or the coldest, followed by orange, yellow, all the way to indigo and violet, being the warmest and attracting the most heat.
So the locations, for me, it was the Chicagoland area, specifically around my house and Peck Farm Park.
And for me in New Jersey, it was based in Atlantic County with the EHG PAL building.
So for our methodology, we wanted to compare and contrast the surface temperatures in our areas. We collected the data for a week, and then we also obviously used knowledge from GLOBE, and then we split them into two distinct groups, and then we graphed them to determine the effects. And then this is our data collection timeline. So for data processing, we basically just graph our data on a spreadsheet, and the data included minimums, averages, and maximums.
This is the open grid that we researched. The one side being Chicago, one side being New Jersey.
And then these are the man-made materials.
Now, one of the false correlations that we found was, in going with hypothesis, the darker the pigment is and the color is, the more heat that the surface has. As for both New Jersey and Illinois, for both our areas, the darker the pigment of the plant, the higher surface temperatures this is, and often this correlates with the amount of light that's reflecting off. Just like how with a darker shirt, it'll be more than a whiter shirt in the sun. Same thing effect happens here.
For urban greenery, for Illinois, the colors yellow and orange had the highest surface temperature, but all of them were lower than the dark green shade. And for New Jersey, pink and green had similar temperatures, but green was still warmer, and this is due to like pink being the mix of red and purple.
Now for man-made materials, while color does play effect in UHI, as seen here, it's not the only effect. As looking at New Jersey, theoretically the light gray concrete should be cooler than gray mulch and black or matte, as light gray being lighter than the other colors, but this is not the case. And just like in Illinois, theoretically the black wood should be darker, but in actuality, black woods are slightly lower in temperature than the gray sliding.
And then in conclusion, for urban greenery, our scale from warmest to lowest starts from green to yellow/pink to orange to purple.
And the hierarchy in man-made materials went from black to gray to beige to white.
But overall, our findings showed that man-made materials have a higher surface temperature than all urban greenery.
Now, just like any study, we had just some limitations. Some limitations are the textures of the materials, the geography of a study, the weather conditions as a study, time/budget, and the controlled environment.
Now, some next steps for us and for other people could include focusing on only urban greenery and the extent color plays within the same species, looking at how the tone of the color affects the UHI, and then looking over a larger time period and a larger range of species, and then looking at how the extent of materials and textures play a role.
Now, reflecting back on our experience with the NASA Seas and this program, my best memory was at work at EHG PAL, collecting research while on the job, and lots of my students/kids like coming up to me, watching me conduct research, them asking questions, them wanting to actually participate in the research and use the thermal thermometer. It was just like bringing kids into science and seeing how they loved it as much as I did.
And for me, it was just having a reason to be active and also collecting data for the first time. Thank you.
And these are references, and thank you.
So our next Urban Heat Island project is an assessment of the relationship between UHI and water quality in U.S. cities.
Hello, this is our study on the relationship between the urban heat island effect and water quality in United States cities. Since the beginnings of urbanization, the idea of the urban heat island effect has been present. In areas of high human presence, higher energy consumption, and less heat-absorbing materials, heat island effects are no new phenomenon. However, as time goes on, the severity of these heat islands has increased. Because of its use in commerce, many cities have been built on and around bodies of water. In our study, we sought to quantify the effects of the urban heat island effect on the water quality of said cities.
In our study, we assessed the relationship between urban heat island and water quality across U.S. cities. We focused on the Urban Heat Island Index, NDVI, and land surface temperature as our urban heat island metrics, and pH, oxygen concentration, and water temperature as our water quality metrics.
Moving on to our study area, we decided to choose the 25 most populous cities in the United States, as shown on the graph to the left. On the right, you can see we've ended up with urban cities all across the nation, each with unique climates regardless of urban or rural areas.
These are the papers we read prior to our research. Many of these papers emphasize the effect of urbanization on water quality due to runoff in specific and localized areas, which is why for our research, we wanted to assess the relationship on a more broader scale.
And now we'll be covering the methodology we use to perform our analysis.
Starting with our independent variables, our urban heat metrics were taken from 3 different areas. The Urban Heat Island Index was sourced from a 2020 U.S. Census tract. The LST data was sourced from satellite imagery from Band 10 from Landsat 8 from 2019 to 2023 through Google Earth Engine. NDVI data came from the same source and time frame, but calculated using bands 4 and 5. LST and NDVI were all taken from a 1-mile buffer for a precise measure.
Moving on to our dependent variable, all of our water quality data was collected through USGS Water Dashboard. By sorting by availability, we were able to find sites which recorded all 3 of our water quality metrics of water temperature, pH, and oxygen concentration.
USG data was accessible through their data retrieval R package. We utilized each waterway site number and corresponding parameter codes for each water quality metric to access and aggregate the needed data.
Because of the various environments our studied cities are located in, their pH, water temperature, and oxygen concentration would be naturally differing regardless of urban or rural conditions. Because of this, we also selected 25 control USGS sites, which corresponded with each city. We did this by selecting a body of water in a rural area in relative proximity to each city. This allowed us to account for the fact that we'd expect a body of water in Texas to be warmer than that of one in New York, regardless of whether it's in an urban or rural environment. Moving on to how we process and analyze the data, for each individual analysis, we removed the cities with incomplete data for the specific metric we were analyzing. Then we used ggplot2 to create a scatter plot and did a linear regression to try to model these trends. And in terms of the actual data we collected, we chose the highest data point for each of these sites in the past week.
Now we'll cover results and findings of our research.
So here are some of our graphs. As you can see, which I'll be flipping through, regardless of which independent or dependent variable we utilized, the data is all over the place. Because of this, we were not able to derive a model which could accurately predict the effects of UHI on water quality. In fact, for some of our graphs, the regression model has an R-squared of less than 0.01, indicating an average of all data points would be a better predictor than the model generated. As you can see, we plotted our various UHI metrics against the difference between our experimental and control group bodies of water.
Beginning with our findings, under our current selected metrics, we determined that there's no statistically significant relationship between the urban heat island effect and water quality as seen by our low R and R-squared values. This is due to other localized factors such as native wildlife and human pollution that have more impact and influence. Secondly, our limitations. Our urban heat island metrics were flawed as we couldn't account for localized factors. Because of the limited scope of our study, our water quality metrics were likewise limited. Some of our control waterways were connected to its respective urban sites due to the lack of availability on USGS's portal, which also reduced our calculated urban heat effects.
And now we'll be wrapping up with our conclusions. So from this study, we were not able to find any correlation between our urban heat island metrics of UHI index, land surface temperature, and normalized difference vegetation index, and our water quality metrics of water temperature, pH, and oxygen concentration. We believe it's possible that other localized factors we did not account for, such as local flora and fauna or human pollution, have greater effects on water quality. If one were to pursue a further investigation, we believe they would need to account for many more outside factors in order to accurately quantify the effects of urban heat islands on the water quality of surrounding bodies of water. In addition, a lot of this additional factors would have to be collected manually, as a lot of this information was not available on any resources we could find online.
To conclude, we'd like to thank the NASA SEAS program and our mentors at the University of Toledo for providing and supporting us with an authentic research experience. This internship has significantly impacted our academic and professional growth, which we will carry on into our future endeavors. Thank you.
Great job. So we want to invite all three teams from the Urban Heat Island projects to turn on their cameras and unmute their mics. So we have several questions for each of the teams. Our first question is for team number 1. Are you considering furthering your research in other urban areas?
Yeah, Jason, you can answer that one.
Okay. So yes, we have considered furthering our research into other urban areas, but currently we've been limited by access to EUI data because not every urban area has that data openly available.
The next question for team number 1 is, how would you recommend reducing energy consumption?
I can answer that one too. So to reduce energy consumption due to the urban heat island, you can take measures to combat it, such as increasing green spaces, because vegetation helps cool urban areas through providing shade and evapotranspiration. And then so this will reduce the heat and reduce cooling costs. And then also you can enhance building insulation, which reduces the need for cooling, which increases energy consumption.
Great. And Michael, what data collected surprised you the most?
Yeah, so we actually, when we did the data collection, we kind of just tried a few variables for fun. And I think what surprised me the most was the stark relationship between the efficiency, so the energy star score, and the LST. So it's not only about just the net energy output, but it's more about the efficiency, which is something I found quite unique when doing our research.
Great. Team number 2, looking forward, how can your research influence urban planning and or landscape architects to mitigate urban heat island effects?
Yes. Oh, go ahead.
Okay. Talking about the landscape architects and stuff, the main things that they would get from our research is, one, trying to instate more urban greenery. As looking at modern cities, with all them being hot, almost they have a very big lack of urban greenery, plants and parks. And if they need major infrastructure, look at the color of the infrastructure, as even though everyone wants to go with a modern, sleek, black look, it brings a lot more temperature to the surface, which then heats up the local environment as well.
And then also for team number 2, what material or color do you recommend together for use to reduce the urban heat island effect?
We recommend any colors that are super light. So white, beige, and light gray would be great. Man-made material colors that could reduce the UHI effect.
Great. Team number 3, do you think urban heat island indirectly affects water quality metrics?
Absolutely. In our literature review, we've read multiple different papers which all talked about theoretical effects UHI can have on the nearby bodies of water. However, as I mentioned in the presentation, it's hard to quantify just because there's so many other effects. so many other aspects that can also affect water quality.
And also for Team 3, what did you find most challenging to complete this research?
Christina, do you want to take that one?
Take this one. I think our largest challenge was definitely having enough data to create sufficient graphs, because for some of these graphs, even though we did conduct a study over 25 cities, some of these graphs had as little as 11 points. So I think our largest challenge was having enough data points to expand this project. We would like to conduct more research on further cities.
Great. You all did an excellent job. Thank you for sharing your research. So please welcome the Planetary Geology team led by Beverly Barakian, who is the 8th grade integrated science teacher and community college instructor. The Planetary Geology team focused their research on composition of asteroids and their formation and evolution within the solar system.
Our presentation is Composition of Asteroids and Their Formation and Evolution Within the Solar System. I'm Lily Myers.
I'm David Sluter.
I'm Noah Byers.
I'm Jade Park.
I'm Maya Freeman.
I'm Max Schweitzer.
I'm Rusty Lee McMurray.
And I'm Stella Ristich.
And together,
we are Planetary Geology.
The goal of our research is to determine the relationship between the mineralogical composition of various asteroid classifications and their role in the evolution of our solar system. By establishing that connection between asteroid compositions with their significance in our solar system's early history, we can further define and expand the knowledge on the separation of gaseous and terrestrial celestial bodies, the transportation and evolution of life on Earth, and the processes which occur in the formations of new solar systems. Our research can also answer questions about the creation and dispersion of the Milky Way.
To understand asteroid formation, we must first know about the formation of the solar system. The process of star system formation begins when a large dense cloud of molecular gas begins to spin, forming a disk. Materials from this disk are pulled by gravity towards its center, creating enough pressure to fuse hydrogen atoms together into helium. The balancing act of nuclear fusion pushing outwards against the inwards pull of gravity creates a star, such as our sun. The remnants of the stellar nebula begin to clump together and collide, forming early versions of the planets, moons, and asteroids we see today.
So, what are asteroids? Asteroids are classified as rocky celestial objects that maintain elliptical orbits around our sun. They are considered to be the material left over after the formation of the sun and all of the planets in our solar system 4.6 billion years ago. They are also pieces of space debris with insufficient gravity to form planets or moons. They can also be characterized as past celestial bodies that were destroyed by violent collisions occurring in the early stages of the formation of the solar system. The different types of asteroids are differentiated by their spectra, composition, structure, and location in the solar system. The types of asteroids that we chose to focus on for this project are C-type, which represent carbonaceous chondrites, S-type, which represent silicous, M-type, which represent metallic, B-type, which is a subtype of C-type due to the blue spectral slope being different, and V-type, which are basaltic asteroids and are pieces of vesta that broke off of the main asteroid. The graph included is a representation of the distribution of asteroids in the solar system based on spectral type and orbital resonance. It is shown that the M-type asteroids are exclusively found in the main belt, whereas C-type and S-type are found inside as well as outside of this region.
This leads us to the question of how asteroids form. Rocky asteroids with cores form similarly to the terrestrial planets. During the birth stages of the solar system, when everything was much hotter, spatial bodies were molten, and the denser metals, such as iron, sunk to form a core, and the less dense rock rose to the surface of these objects. These structures that did not form moons and planets are known today as the asteroids. Most asteroids form from the accretion of dust and metallic material left over from the formation of the Sun 4.5 billion years ago. In addition, some asteroids can also break off of other planets and celestial objects, an example of this being the asteroid Bennu. Asteroids can also be the product of large and small-scale impacts between celestial bodies. The image in the bottom right of the slide illustrates two examples of these collisions that spread debris throughout the solar system and form new bodies/asteroids.
Our data was obtained through various scholarly and credible sources such as Google Scholar and EBSCO. We chose to research the different classifications of asteroids, specifically the C, V, B, S, and M types. With this information, we studied the composition, location, and possible origin of the asteroids from these classifications in order to derive a conclusion which answered our initial research question of what does the mineralogical composition of asteroids tell us about their formation and evolution in the solar system.
We researched Vesta due to its unique characteristics. For example, 6% of all main belt asteroids are related to Vesta, granting the asteroid and its relatives their own classification of asteroids, the V-type. Bennu was chosen for the immense amount of data obtained during the OSIRIS-REx mission, including the asteroid's connections to a larger oceanic asteroid and its unique classification as a B-type asteroid as a result of its blue spectral slope. We studied Ceres due to its central role in the Dawn mission and unique core composition, which suggested its dwarf planet status. Itokawa was researched since it is a notable S-type asteroid that had been heavily studied in the Hayabusa mission, and because its small side adds diversity to our sampling. And finally, we chose Psyche because of its exposed nickel-copper composition that mirrored the building blocks of terrestrial planets in our solar system, as well as its relevance to the upcoming Psyche mission.
Our first three asteroids are Ceres, Vesta, and Psyche. Ceres is made up of a water ice mantle, sodium carbonate, ammonium chloride, organic compounds, and rocks with a composition of C1 chondrites. Vesta is composed of basalt, nickel iron, pyroxenes, and oxide minerals. Vesta and Psyche also both contain silicates, though Psyche's composition is more that of nickel, copper, and iron. Both Ceres and Vesta are around 4.5 billion years old, while the age of Psyche remains unknown. Ceres has a density of around 2,700 kilograms per meter cubed. Vesta has one of 3,456 kilograms per meter cubed, and Psyche's density is around 2,950 kilograms per meter cubed. Finally, both Ceres and Vesta have a homogeneous structure, as well as a core, while Psyche has a uniform composition and a porous surface with numerous craters.
Bennu is composed of various materials, including serpentine, magnesium sodium phosphate, organic compounds, and clay, which were formed 4.5 billion years ago. Bennu has a density of 1,260 kilograms per cubic meter. Itokawa is composed of silicates, water, and organic compounds. Similar to Bennu, Itokawa's rocks were formed 4.562 billion years ago. Itokawa has a higher density of 1,900 kilograms per cubic meter. Many large rocks of similar composition comprise Itokawa, while Bennu has a homogeneous structure with a metallic core.
The arrangement of asteroids is due to the way our solar system formed and the compositions of the asteroids themselves. During the formation, only rocky materials were able to withstand the heat of the sun, while icy materials and less resilient matter settled in the outer regions of the asteroid belt and solar system. This is why metallic and stony asteroids, S and M types, are found closer to the sun, having rockier compositions, while asteroids containing water or ice, such as C, V, and B types, are found farther away. Crystalline silicates are commonly found in C, V, and B types, and they're located at distances where the temperatures are too low for in situ annealing, which is a type of heat treatment used to alter the physical and chemical properties of a material. In other words, they are located too far from the sun for the necessary thermal energy. C, V, and B types asteroids are all composed of silicates, clay, pyroxene, basalt, and magnesium, and therefore tend to be found in the outermost regions of the solar system, located about 3.5 AU from the Sun. S-type asteroids are the closest to the Sun, only 2.2 AU away, and they're made of stony materials like nickel iron and magnesium silicates. M-types are located in the middle of the asteroid belt, 2.5 to 3.3 AU from the Sun, made up of primarily iron-nickel metal. The image on the left portrays the percent populations of C, M, and S-type asteroids and their respective compositions. It most accurately shows the immense population of C-type asteroids compared to S and M types, and the differences in rocky compositions versus organic. The image to the right is a graphical analysis comparing the primary asteroid classifications to their distance from the Sun, showing S types as the closest and C types as the farthest. The image above represents silicate and metallic asteroids and further breaks down their mineralogical compositions into specific elements.
Vesta, a V-type asteroid, is assumed to be formed from dust accretion because of the many simulations of our early solar system's protoplanetary disk. This formation process is also the reasoning behind Vesta's large size, because as it accreted more and more dust, the accretion process accelerated. The group of HED asteroids, Howardites, Eucrites, and Diogenites, are all believed to be pieces broken off of Vesta because of the similarities in their compositions and spectra. This ejection is shown in the middle of the bottom image. Both Howardites and Eucrites are made up of basalts, pyroxenes, and silicates, while Diogenites are just made up of pyroxenes and silicates. These small differences in composition, which you can clearly see in the images on the right, are due to the point in time in which they are ejected from Vesta, because as the core went through differentiation, the minerals on the surface changed. This process is portrayed in the top image.
Psyche is an M-type metallic asteroid composed mostly of nickel-copper alloy, silicates, and iron, and is a planetesimal, or failed planetary core, as most M-type asteroids are believed to be. This indicates that Psyche coalesced from dust and metals that were around during the beginning of the solar system after the formation of the Sun. Metallic asteroids such as Psyche start out fully molten. However, over time, they solidify and form a uniform, solid asteroid. Observing the surface of Psyche shows that it has been impacted various times, making its surface rough and porous. The image on the right of the slide shows a nickel-copper alloy, the very substance that makes up 60% of Psyche, and the image to its left depicts the launching of the Psyche mission in 2023, which will study the asteroid in depth.
Ceres is a C-type asteroid. C-type asteroids are known to be a source of carbonaceous chondrite meteorites, with the carbon composition resulting in a dark charcoal-like color. C-type asteroids have a very low albedo, which means that they don't reflect most of the light shown onto them, making them very hard to view. Most C-type asteroids are at least 3.5 AU from the Sun on the edge of the asteroid belt, being one of the more ancient asteroids of the solar system. These asteroids are the source of carbonaceous chondrite meteorites. Most C-type asteroids haven't reached above 50 degrees Celsius and are believed to be composed of around 22% water. Ceres itself is theorized to have formed from silicate rocks and silicate organic matter accumulated on celestial bodies with the surface water near Jupiter and Saturn, while also being formed of clay and dust. Ceres tried pulling all of these particles together to form its own planet but failed, resulting in it becoming a planetesimal. Some hypothesize that C-type asteroids may have delivered volatiles to the inner solar system, particularly the early Earth.
Bennu, a B-type asteroid, contains many different elements and compounds that are telltale signs of its origins. Magnesium sodium phosphate found in the samples collected from the OSIRIS-REx mission suggests that Bennu broke off from a much larger and aqueous, carbon-rich asteroid 700 million to 2 billion years ago due to a collision in the main asteroid belt. The scattered pieces moved in a near-Earth orbit due to gravitational interactions with the gas giants to form Bennu. This debunks common belief, as asteroids are not always monoliths or a singular rock. They can be what astronomers call rubble piles, boulders and debris that have coalesced under the influence of gravity. The current structure and measured bulk density of Bennu tells us that the asteroid is a conglomeration of clay and serpentine. OSIRIS-REx samples also show evidence of organic molecules, such as carbon, oxygen, and nitrogen. This implies the possibility of impacts from asteroids similar in composition to Bennu being the source of organic molecules on Earth, and thus the origins for life on our planet.
Itokawa, similar to Bennu, formed from debris resulting from an impact of another asteroid with Itokawa's parent body. The largest boulder on Itokawa, pictured to my left, is evidence of this formation because it is too large to have been formed by any collision displayed in Itokawa's impact craters. Itokawa's density, which is lower than what would be expected from a solid asteroid of Itokawa's composition, also supports ideas of a parent asteroid. Much of the ejecta from the impact on Itokawa's parent body gravitated towards each other, forming an asteroid, as shown in the diagram below. Itokawa had enough local gravity to agglomerate these rocks, but not enough to consolidate them into a solid asteroid without empty space. This led to the amount of empty space shown in Itokawa's density. Itokawa's low local gravity also accounts for its lobate shape, having many lobes around the asteroid, as seen in the final image of the diagram below. Itokawa's parent body was likely a C-type asteroid, as shown in the amount of water and organic compounds found in Itokawa's regolith. However, Itokawa itself is an S-type asteroid because its composition is predominantly silicates, such as olivine and pyroxene. This shows that Itokawa formed from a silicate-rich area of its parent asteroid's crust that underwent metamorphism. Dating of particles returned from Itokawa indicates that this metamorphosis occurred 4.6 billion years ago.
In conclusion, examining the different components of types of asteroids helps to further our understanding of the development of our solar system and potentially the development of life on Earth. The composition of asteroids helps us to understand their relative locations in the solar system. Rocky materials are closer to the Sun due to their tougher materials and composites being able to resist alterations from the intense heat and radiation from the Sun. A key indicator for this is the asteroid belt that divides the rocky planets from the gas giants. This is demonstrated in the image where there is a large population of asteroids in between Mars and Jupiter. Because of the proximity to the Sun, rocky planets formed closer to the Sun, and planets made from gas and ice are further away. This also leads to rust-resilient carbonaceous chondrite composites.
Psyche is a NASA mission to study the metal-rich asteroid it was named after, which is located in the main asteroid belt between Mars and Jupiter. This is NASA's first mission to study an asteroid that is more metal than rock or ice. Psyche launched on October 13, 2023 from the Kennedy Space Center aboard a SpaceX Falcon Heavy rocket in order to release the satellite. Psyche will orbit its target in 2029 and collect data about the surface, composition, and structure, which will help us understand more about the core of our planet and teach us more about planetary formation and all.
As a successor to the OSIRIS-REx mission, OSIRIS-APEX will reach the S-type asteroid Apophis during Apophis's close encounter with Earth in April of 2029. Our planet's gravitational pull is expected to alter the asteroid's orbit, leading to changes in how fast Apophis spins on its axis and could cause quakes/landslides. APEX will allow scientists to observe these changes and view the composition of material just below the asteroid's surface rather than just the regolith.
One area for possible future work is in the analysis of Kuiper belt objects. While similar to the asteroid belt in many ways, the Kuiper belt is much farther away from the Sun, as visualized below. This allows for additional investigation into the links between the locations and compositions of asteroids. Being much larger than the asteroid belt, the Kuiper belt contains many bodies, such as those pictured around me, which could be the basis for significant research. This research, similar to that which has been conducted on asteroids closer to Earth, would be particularly important to shed light on the formation of trans-Neptunian objects and the ice giants they encircle.
And these are our sources, most of which are images.
The NASA STEM internship offers a wide variety of activities and experiences that expose interns to a vast amount of knowledge and discoveries. A few of the highlights from the program include conducting geology field research, where we embarked on a journey to extract rock samples for analysis, research, and comparison to extraterrestrial samples. The Johnson Space Center visit, in which we traveled to Houston to go on a tram tour of the Center and Sea Rocket Park, the Astronaut Training Facility, and the Mission Control Center. We also enjoyed Six Flags Fiesta Texas, where we had a great time bonding as a team outside an academic setting, and the University of Texas Aerospace Engineering Department, in which we had the opportunity to tour the incredible aerospace facilities at the university. Finally, our trip to iFly, where we learned about wind tunnels and terminal velocity, and got to experience indoor skydiving.
We also had a few challenges with the internship. The first one was planning an experiment for our Z-Cube. This challenged our abilities to brainstorm, test, and narrow down the ideas for our project. This proved especially difficult due to experimental constraints, such as the camera angle, small space, and limited time in microgravity. Through teamwork and help from the amazing SEAS mentors, we were able to design an innovative experiment that will be successful despite these constraints. The second one was performing our planetary geology research, which proved just as rewarding as it was challenging. Every step forced us to stretch our abilities from developing a research question that everyone felt passionate about to analyzing asteroids at deeper and deeper levels to creating this presentation. We have learned various skills that will help us in our later careers.
Reflections. Growing up loving Bill Nye the Science Guy episodes and assembling NASA Lego sets fostered my love for understanding our universe. Thankfully, my experience with NASA Seas has not only nurtured this curiosity, but taught me that I have a future in this field. Whether listening to incredible guest speakers, studying various rock processes with Bev, or scribbling mission patch designs while sleep deprived, I've enjoyed every step of this journey with my fellow interns. I'll be sure to stay curious and achieve my goal of being an astronaut someday, but until then, thank you, Planetary Geology. Let's keep in touch.
I could have never imagined how much my life was about to change when I opened the NASA Seas exhibits letter. Getting to work with similarly minded people has truly been the highlight of my 2 weeks here, and I hope that my time here will stay in my mind for the rest of my career. The things I have learned here have only further cemented my love for space and science, and this passion will follow me for the rest of my life. My rewarding experiences here will continue to aid me in my journey from Earth to the stars.
My experience here at NASA Seas has been absolutely fantastic. There were still definite challenges, but I was able to get past them with the help of my team. Having the ability to conduct experiments, connect with professionals and experts in the field, and get true experience with the research was wonderful. I'm excited to see how this internship will help me with my goal of becoming an astrophysicist.
The NASA STEM program is utterly unique from every other. The people we have had the chance to meet and work with are incredibly inspiring and will forever leave a mark on our careers. The opportunity to meet students from all around the country while also indulging in once-in-a-lifetime experiences, including designing projects to be tested in microgravity and scientific research, has been deeply influential. I am so grateful to have had this opportunity and to meet my amazing team and mentor.
Throughout my time spent at NASA Seas, this internship has been a truly eye-opening experience. As someone who has only considered space a hobby, the idea of pursuing it as a career had never come to mind. After these 2 weeks, however, more than ever can I see myself as someone with a future in space. From our lectures with renowned scientists to our intricately planned experiments, I am so thankful for both my mentors, my fellow peers, and the NASA Seas team for making this once-in-a-lifetime experience truly rewarding.
NASA Seas has been one of the most transformative experiences of my life. From the friends I've made to the lessons and knowledge I've gained, being here surrounded by incredible peers, mentors, and speakers that share my interests in space exploration and aerospace engineering has not only been an eye-opening experience, but has also taught me so much about myself and my future career path. I am so grateful for my time at this internship, and I know that I will carry the knowledge I've learned with me throughout my personal and professional lives. Thank you to my incredible team for making my time here so memorable, and thank you to the mentors and organizers for making this experience possible.
This internship, while a new experience for me, has turned out to be both difficult and enlightening. Learning to collaborate with my team members under the guidance of a wonderful mentor in order to overcome challenges in both our research and experiments during my time at NASA Seas has strengthened my drive towards a future in STEM and my resolve when facing difficulties in the journey towards it.
My journey throughout my NASA Seas internship has been challenging. However, my team has made this experience not only successful, but incredibly enjoyable. I am grateful for this internship, and I'm excited for how it has helped me on the coming steps of my planetary research journey.
Thank you!
So we invite all of the members of the Planetary Geology team to turn on their cameras and unmute their mics. We have several questions for your team. First question is, do you think that the model you have of asteroid origin classification of asteroids can be applied to the formation of other solar systems?
Yeah, I think it can be applied, but it has to be done carefully. The main link we found between asteroid location and its composition was due to the heat it had during the early solar system. And so if you have a more luminous star, then that star system, you'd expect to see more stony asteroids, whereas a less luminous star than our sun, you'd expect to have more asteroids of chondrite composition.
And how are the ages of the asteroids determined, and how come Psyche is unable to be determined?
Okay, so the main way that scientists are actually able to determine the ages of asteroids, such as the ones we mentioned, is by either carbon dating or radiometric dating of samples of said asteroids. And the reason why we can actually get a good specific age of Psyche is because we don't actually have samples yet. Based on its type, classification, what it's made up of, we can give a rough estimate of its age, but we don't actually know a definite age until we're actually able to get samples back from the Psyche mission.
In the early solar system, how did the dynamics of asteroid formation and migration contribute to the distribution of volatile and refractory elements?
I can take this one. So, and as we saw in the case of Bennu, we saw that the reason why we studied Bennu is because we believed that asteroids that could have collided with Earth had brought the origins of life to Earth. And so what we wanted to see with Bennu, and is what we found, is that organic elements were present, such as carbon and nitrogen, on the asteroid Bennu, and therefore asteroids very similar to Bennu in composition could have impacted Earth and distributed those elements on Earth, which could have been the basis for life.
Among inner and outer solar system bodies, what implications does this have for understanding the origins of the terrestrial planets like Earth? Anyone want to take that on? I think it's right. It kind of follows what you were just saying, Rusty.
Yeah, so basically during the early formation of the solar system, we learned that more stony and rockier composition objects would form and remain closer to the sun because they were able to withstand the intense heat. And this is why gaseous and more aqueous and icy objects were dispersed farther from the sun. So this is why we have our terrestrial planets and our asteroid belts closer, and our gaseous planets are located more farther away. So this is why Earth, a terrestrial planet, is located close to the sun where it is.
Perfect. Thank you. Yes, you have something to add?
Oh, sorry. Yes, and building off of that, some of the asteroids we studied, such as Psyche and Vesta, were planetesimals, or failed planetary cores. So by researching and studying those failed planetary cores, we can actually we can put together a better image of how our planets, such as Earth and Mars and Venus, the terrestrial planets, formed under certain conditions, and what caused asteroids such as Psyche and Vesta to not form into actual planets.
Great. Y'all did an excellent job. Congratulations on your thorough research. So the success of SEAS is determined not only by the commitment and research conducted by student interns, but also by their mentors and our project assistants. To our NASA subject matter experts and project assistants, your passion for youth development, STEM learning, and NASA missions and opportunities is to be applauded. A special thanks to our SEAS project assistants and project associates and our summer interns. The SEAS education team thanks you for the time and the talent that you have shared with our student interns. I know the SEAS interns appreciate your guidance and advice as they conducted their research. And we have to give a special thanks to our communications coordinator who has prepared all of the social media, put this video of presentations together along with all of the slides and the videos from Asha Carmacher. We appreciate you both so much. We could not do this without you. So thank you for joining us for day one of the NASA SEAS Science Symposium. Please join us again tomorrow at 10:30 Central Time as we continue to share the research from the NASA STEM Enhancement in Earth and Space Science High School